of you to the national webinar on recent advances in solid-state chemistry and allied sciences, organized by Department of Chemistry, School of Physical Sciences, Central University of Kerala, in association with Association of Chemistry Teachers and Indian Association of Solid-State Chemists and Allied Scientists. Inorganic materials have made great contributions in the development of novel materials from the very early period. The current society emphasis on the sustainable development, and in this point of view, solid-state chemistry plays a significant role in recent technology, semiconductor, capacitor, electrochemistry, catalyst, etc. We hope that this webinar would help you to trigger and expose to the recent advances and progresses in solid-state chemistry. Every new beginning always needs the blessing of invisible power around us. Let us begin the webinar with the university anthem. I request all of you to raise for the university anthem.
Is it audible?
Hello. Okay, I'll just inform Shaktivel, no problem. Okay, right, sir. Right. Shaktivel, please allow Brijesh, na?
Yeah, we permitted, sir.
No, he is actually waiting. The host is not allowing him. That is.
No, included, admitted, sir.
He
All
just
are
called
admitted.
me and informed me.
He is inside. He can rejoin. He can. I will call him, sir. Nimisha,
Yes, sir.
proceed.
I now call upon Professor Dr. A. Shaktivel, Head Department of Chemistry, Central University of Kerala, who is also the convener of the program, to give the welcome address and introductory remarks of the webinar.
Very good morning to all of you. First of all, I like to thank our Honorable Vice Chancellor, Professor Venkateswaru sir, because whenever we want to conduct any scientific program or any program in university, he always support us. So uh, he also expressed his sincere wishes for the successful event of this program, and he conveyed his best wishes. In this option, I thank him. I welcome sir, and this webinar, solid state chemistry webinars, it is one of the motivation is by our solid state chemistry president, Professor M. Swaminathan sir, because he always telling that Satyal, can you try to organize a webinar or any conference on the solid state chemistry? He was talking for the last couple of years. So that was the motivation behind organizing this webinar. So I welcome our solid state chemistry association president, Professor Swaminathan sir, for this function. And we have a very eminent personality, Professor Dr. A.K. Tyagi, and also other speakers like Professor Ashok Ganguly, Professor Sambat sir, Dr. Kobinath, Professor Selvam, Ajay Veenu, and Ramasamy sir, and Dr. Supna, and other people. All the eminent people are will be joining these webinars. So I welcome all of them. And on behalf of Department of Chemistry, as well as Indian Solid State Association and Association of Chemistry Teachers, and special sincere thanks and welcome Dr. Prijesh Pare, who is the president of the Association of Chemistry Teachers, and also Dr. Prabhu. He is also the secretary of Association of Chemistry Teachers.
Thank you, sir.
Also supported immediately when we proposed this webinar. They are the one who immediately supported for the solid state webinar, and immediately they supported with the sponsor also. So I thanks and also I welcome both of them. And the most important thing is our Dean, Professor Pratap Chandra Krup sir. He is also here, and he is our colleague in the department, as well as he is the Dean of our School of Physical Science, and he always motivate and all the program he is behind us to inspire and do the best activity in the departments. I welcome you, sir, with kind support, and also I welcome all my colleagues, Dr. Bini George, Dr. Deepa Janardhanan, Dr. Ravi Kumar, and my colleague Dr. Bhagyalakshmi. She is also co-convener of this conference. All of them, I welcome you, and I also welcome the faculty members from various colleges and institutes, as well as research scholars from various colleges and institutes, our own college students, our own university students, and research scholars, and all the dignity members. I welcome all of you once again. And main thing is, you know that the solid state chemistry, the importance of solid state chemistry has been realized since the 1990s when it started the lithium-ion batteries. And also solid state chemistry has to play a major role in the case of petrochemical industry, because especially zeolite and zeolite-like materials has been shown as made a revolution in the petrochemical industry because of the zeolite kind of material. And you know that it is a expanding field of research and invention of new functional materials, and its application is vital in the advancement of technology and help move the society towards a high global standard of living. So solid state chemistry play a major role. So that's why our objective of the program is to familiarize what is the recent advances and its significance of solid state chemistry, field of chemistry as well as life science. So that is the main area of objective of this conference. And especially, I must express sincere thanks to all the members present in the Indian Solid State Association, like the President, Professor Swaminathan sir, then NP Singh sir, and Sarmaji, as well as Veer Singh sir, all their support for that. And I take opportunity thank all the eminent speakers who agreed for this webinar. And before concluding, I also like to give a brief overview about our university. Central University of Kerala has established in 2009 as per MHRD Act. And our department started functioning from 2013, although it is established in 2012. We started functioning from 2013. We have 6 faculty members, and we are offering both MSc and PhD courses. And the strength of our department is our faculty members are very young and dynamic, and they are having a lot of project and multidisciplinary research area. We are located near to the Mangalore airport. It is a north part of the Kerala. So uh, it is. We will be very happy to organize offline webinar in near future, so that all the eminent people can come and have an interaction. So we hope soon the pandemic situation will improve, and we will be able to conduct offline course. And these webinars, especially without the support of all these eminent people, it would have not ability to materialize. So I take the opportunity to once again thanks our Honorable Vice Chancellor, as well as the ISCAS President and Secretary, as well as ACT members, ACT President and Secretary, all of them. We expect that audience to interact maximum during the lecture series and post several questions to the fruitful interaction. We strongly believe that this event will bring the eminent personality from this audience as a solid state chemistry. So I wish you great success. I hope this webinar will be fruitful for many young generation. Okay, with this I welcome all of you, and I wish all the best, and thank you.
Thank you, sir. Moving on to the formal inauguration, I now invite Professor Dr. M.R. Pradapachandra Kurup, sir, Dean School of Physical Sciences, Central University of Kerala, who always stays along us, providing immense support and encouragement to conduct various programs. Sir, I welcome you to give the inaugural address.
Good morning, everybody. Today it is an important day for the Department of Chemistry, School of Physical Sciences, Central University of Kerala. We are organizing a 2-day national webinar on recent advances in solid state chemistry and allied sciences. I congratulate Professor Satyavelu, convener of this webinar, for making this seminar a reality. In fact, he was considering of organizing a seminar of this nature for the last 2 years. And we really wanted to have this seminar in the offline mode. However, due to the pandemic situation, we are making use of the digital utilities of this program. Anyway, this seminar, we have a very eminent speakers. This is sponsored by Solid State Chemistry and Allied Sciences, and also Association of Chemistry Teachers. We have a very eminent speakers will be speaking in the next 2 days. Professor Tyagi, Professor Ganguly, Professor Sambath, Dr. Gobinath, Dr. Supna Nair, Professor Selvam, Professor Ramasamy, Professor Ajay Pinu, and others. And we have also some oral presentations by young researchers. So all the young researchers are given time for presenting their recent advances in this webinar. And they also will be allowed time to interaction. I'm very happy that the department, under the leadership of Professor Saktivel and my colleagues, Dr. Binay George, Dr. Sagrishmi, Dr. Ravi Kumar, and Dr. Deepa Janardhanan, are always helping all the activities of the department. And also, we are one of the best departments visible in the whole campus. We have many participants registered for this, and I wish all of them very happy time during this webinar. And I am very happy to declare that this webinar on recent advances in solid state chemistry and allied sciences is inaugurated. Jai Hind.
Thank you, sir. I now warmly welcome Professor M. Swaminathan, sir, President SS Board, the Presidential Address.
Thank you. Audible now? Hello.
Yes, sir, you are audible, sir. Yes, sir.
So the patron of the conference, Professor Venkateswarlu, the Vice Chancellor of the Central University of Kerala, Ramachandra Group, the Dean Faculty of Science, and the President of ACT, Dr. Brijesh Pare, and General Secretary, Dr. D.V. Prabhu, and Professor N.B. Singh, Professor Sharma, and Professor Saktivel and his team, and all the delegates and the eminent speakers. Good morning to all of you. On behalf of Indian Association of Solid State Chemists and Allied Scientists, I am happy to welcome you all for this national conference on recent advances in solid state chemistry. See, the Indian Association of Solid State Chemists and Allied Scientists, this association ISCAS was established in March 4th, 1988 with its headquarters at Jammu University campus to popularize and promote teaching and research in solid state chemistry. And Professor Indubhushan Sharma took the initiative to form the association and was the founder president of the ISCAS. He was taking so much efforts for the growth of the association and also by organizing a number of conferences and other things. And later on, this association actually was sustained by the activities of Professor N.B. Singh and then by Dr. Suneja. So the association has been very successful in bringing together the practitioner of solid state chemistry in one platform. Since the inception, the association is doing various activities such as workshops, seminars, and invited lectures, particularly involving solid state scientists in the country. The first national conference of the association was held in University of Jammu in October 1999. Since then, a national conference and a symposium on solid state chemistry and allied areas was organized every 2 years. And particularly in the reputed institutions in IIT Kanpur, IIT Delhi, and Annamala University, Goa University, this RTM University Nagpur, Jamia Millia Islamia, and HS Gaur University Sagar, Delhi University, Delhi Technological University, and Kamala Nehru Mahavidyalaya. And recently, the 11th National Conference was organized in SK Borwal College, Nagpur. So in these national conferences, particularly the scientists in the solid state are being honored with gold, silver, bronze medals and sponsored special medals to encourage their research in the solid state. So due to COVID pandemic, we have to organize a webinar instead of a seminar. So this is the first online webinar organized by Professor Saktivel at the Central University of Kerala. I really appreciate the efforts taken by Dr. Saktivel because this is our long felt wish and need, as he had, earlier pointed out. So he has arranged Dr. Saktivel and his team have really arranged lectures by the experts mostly in the field of solid state. As we see in the program, 10 lectures are to be delivered by the eminent scientists, speakers from India and abroad, in addition to the oral presentation by the students and the scholars. So I cordially welcome the speakers, actually Professor A.K. Tyagi from BARC Mumbai, and Professor A.K. Ganguly from IIT Delhi, and Professor Sambat from IIC Bangalore, Professor Gopinath from NCL Pune, Professor Supna Nayak from Central University of Kerala, Professor P. Selvam from IIT Chennai, Professor Ajan Vinu from University of Newcastle, and Professor Ponnuthurai Ramasamy from University of Mauritius, and Dr. Vijay Shankar from Reliance Industries Mumbai, and Dr. Professor M.E. Reddy from the Institute of Hydro-Quebec, Canada. Certainly, I feel that these keynote lectures will be much beneficial for the participants, and they have an opportunity to interact with these experts. So I wish the conference a very successful and also beneficial to all the people. Once again, I thank Professor Saktivel for fulfilling our long felt wish to have a webinar. And this webinar is not the first one, I mean a virtual conference. And I feel that we may have some more webinars in the future years to come. And also we have to conduct the national conference in the 2021. And I think that Professor N.B. Singh and Professor Sharma and all the people, with the help of the people, we can conduct that next webinar in a recent times. Thank you very much. Thank you, one and all.
Thank you, sir. I now call upon Professor Brijesh Parekh, President, Association of Chemistry Teachers, for the felicitations.
Yes, sir.
Yes, sir. Sir, mic, please unmute the mic, sir.
Sir, unmute the mic, sir. Yes, sir. Dr.
Sir, unmute the mic.
Yeah, it is. Yeah, I'm trying. It is done now. It is done.
Now it's okay.
Yeah.
Yes,
Thank you very much. And very little. I mean, some glitches, like from internet side. I'm extremely sorry, but anyway, it's a very pleasant morning to all of you. It's a great occasion. The inaugural program of the National Solid State Conference, and I congratulate Professor.
वो बोल रही थी लेकर रखना वो शायद सुबह आएगी.
Can you unmute, Sunny?
Yeah. Professor Saxival and Professor Swaminathan for having envisioned such a wonderful program. And I mean the battery, and the eminent speakers we are going to have for both the days are really excellent. And I'm really very much sure that all the participants, particularly the young researchers and the faculty members of various colleges, those who have joined this program, they are going to be benefited. So, and on my personal behalf and on behalf of the Association of Chemistry Teachers, I'm thankful to the Solid State Chemistry Association for having given this opportunity to join hands with you. And I'm looking forward to have many more such events together. So once again, I congratulate you, the organizers. And solid state chemistry, as Professor Saktival has said, the many commercial and industrial applications, these days, right from the lithium battery to, through many other things. So it is really coming up very fast. And I hope, that solid state chemistry, and other than, the structural aspect, should be the part of the undergraduate and postgraduate chemistry syllabi of the Indian universities. So thank you very much once again. I congratulate the Association of Solid State Chemistry, and I wish all the best for the success. Thank you very much once again.
Thank you, sir. I now welcome Professor D.V. Prabhu, General Secretary, Association of Chemistry Teachers, to speak a few words on this occasion.
Prabhu, sir. I think he's not there. Swaminathan, sir. He's not there.
No, he is there actually.
No,
We
he
have
was
seen
there.
that
I
he is
saw
there.
him. I saw him. He was
He
there.
joined again. Sir, Professor, he joined again. Professor, can you unmute?
Sir, I think Sir has left the meeting. I can't find him right now.
No,
No, he's there.
He joined, but he is not now. Is not seen. I mean that.
his network issue is there.
Yeah.
He is there now. Prabhu sir. Sir, can we proceed further? Swaminathan sir,
Hello.
can we proceed further, sir? I think he's.
Okay, if he's not, I mean, seen that, you can go further. Or you can request that Professor M.B. Singh to say a few words on that.
Yeah. Sir, Professor NP Singh, sir, can you say a few words? The Secretary of ISCAS.
The only thing
Formal.
which I can say or convey is that I congratulate you for organizing such a wonderful event, not only by organization, but you have collected galaxy of people who are well known internationally in the area of solid state chemistry, particularly Dr. A.K. Tyagi, who is the gem of solid state chemistry, Dr. A.K. Ganguly and many others. So I wish you all the best on behalf of ISCAS and on my own behalf. Thank you very much.
I think the Prabhu has come, it seems that, you know.
Prabhu sir. Sir, I think. No, he left again. Okay, proceed, Nimisha.
To end up the formal inauguration, I now request Dr. M. Bhaglakshmi, Assistant Professor, Central University of Kerala, and also the co-convener of the program, to give the vote of thanks.
Thank you, Nimisha. Good morning, one and all. It's my privilege to.
Seems.
Sir, he joined?
Fine, you are audible.
No, whether Prabhu sir is talking like.
You know, Prabhu is coming now.
Yeah, I heard his voice.
Prabhu sir, can you say a few words, sir?
Professor Prabhu, I think his mic is muted. I mean that, it seems.
I think after Dr. Tyagi's lecture, you can ask him to say something.
Okay.
Sure, sir. Okay, Bhaglakshmi madam, please.
Okay, I will extend my vote of thanks. So it's my privilege to propose the vote of thanks to this national webinar on recent advances in solid state chemistry and allied sciences that is happening in Department of Chemistry in association with the Association of Chemistry Teachers, ACT, and Indian Association of Solid State Chemists and Allied Scientists. This program is, as our Professor Swaminathan insisted, is a first webinar on solid state through virtual mode, which is organized by our chemistry department, especially from the effort of our Professor Saktivel sir. So actually the idea behind this webinar is to trigger and expose the recent advances in solid state chemistry through the pioneers in the field of solid state. That's why we have carefully chosen all the speakers. So at the outset, so the thing, it came to true only because of our constant support by our Honorable Vice Chancellor Professor H. Venkateshwarlu. Okay, he is providing us great support so that we can do whatever we like, and there is a freedom so that we can freely do whatever we can do, and his positive spirit in all dimension, okay, for the growth of this department, not only department, for this university, is constantly encouraging us. So I thank our Honorable Vice Chancellor Professor H. Venkateshwarlu for providing us this support, and also for his constant encouragement. And the next, we have to thank the Association of Chemistry Teachers ACT, which is a platform which is connecting all the school teachers, colleges, university lecturers, professors, scientists, all whoever, not only that in academic, if from also from industry, they are connected through this platform, so that they are trying to strengthen the chemistry education in all means, either through academics or industry. So we have to thank ACT, and on that, in that regard, I thank Professor Bridges Pare, President ACT, and also Professor D.V. Prabhu, General Secretary ACT, for joining with us to conduct this webinar on recent advances in solid state chemistry and allied sciences. And we should also extend our thanks to ISCAS, that is Indian Association of Solid State Chemists and Allied Scientists. Okay, this is another platform which is constantly working to encourage the chemists who are working in solid state. So on that behalf, I would like to thank Professor P. Swaminathan, President ISCAS, for joining with us and also providing us an opportunity to conduct this webinar. So to execute this seminar in Department of Chemistry, the other pillars of our university, like our registrar, Dr. Rajendra Pillangeta, okay, he's paying a very careful attention and constant encouragement for especially this kind of webinar, all those things, because in this COVID situation, only this kind of things can make all person be active. So so I thank our registrar, Dr. Rajendra Pillangeta, and also our Dean Academics, Professor K.P. Suresh, he's for his valuable suggestion and the support for this webinar. And I also extend my sincere thanks to our Dean, Professor M.R. Pradapachandra Kurup, sir, for his continued support and also his encouragement for the Department of Chemistry. Whenever this kind of webinar is going to happen in the department, he immediately volunteers, and then he would like to give all sorts of suggestions so that we can make the webinar better way. And I also express our sincere thanks to our Professor Dr. Saktivel sir, head of the department, also the convener of this webinar. Without his effort, I think this cannot happen. And I also thank our department colleagues, Dr. Binny George, Dr. Diba Janardhanan, Dr. Ravi Kumar Kanpati, for their support extended to this virtual conference. And I also extend my thanks to the CUK faculties, all the faculties from all the department, and for their support. And very importantly, I have to extend my thanks, heartfelt gratitude for the speakers who accepted, who are the real actual pioneers in the solid state chemistry. They have come here to grace the function by just sharing their opinion and also triggering us in the field of the research field of solid state chemistry. So I thank Professor Dr. A.K. Tyagi from BRC Mumbai, Professor A.K. Ganguly from IIT Delhi.
Prabhu வந்துட்டு போறாரு. இல்லாட்டி நீங்க அவர்ட்ட போசி இன்னும் இன்ஃபார்ம் பண்ணுங்க.
From IIC Bangalore, Dr. C.S. Gopinathan sir from NCL Pune, Dr. Sapna Nair from our CUK, and Professor Selvam sir from IIT Madras, Professor Ramaswamy sir. The other person, they are going to give the lecture tomorrow. The first 5 people will be giving the lecture today. So I thank them all. And also Professor Adayan Vinu from University of Newcastle, Australia, Dr. Vijay Shankar from Reliance Industry, and Dr. M.V. Reddy from Canada. So all the pioneers are they're ready for with their stuff to fill us with the information on the solid state. So we have to be waiting for their lecture, and then we have to be enriched, I hope. And I also take this opportunity to thank all the technical committee, especially this Zoom coordinator, Mr. Sunny, and also our university technical, this IT section people for their valuable support to execute this virtual conference without any hindrance. And I also thank all the participants who take up this virtual conference on recent advances in solid state chemistry and allied sciences, and also about 24 to 30 oral presentations are there. The young presentation from young researchers are there to share their knowledge in the solid state chemistry. Let us hear from them, I hope. And I also acknowledge the financial support extended by ACT, ISCAS, and CUK for the successful process of this webinar. I also thank our research scholars, MSc students, administrative staffs for their help in making this inaugural function success. And once again, I thank you all, and we look forward for the extremely productive 2 days virtual conference. Let us go ahead, I hope. Thank you very much.
Thank you, ma'am. Here we come to an end of the formal inauguration. It's the time for the technical sessions of the webinar. We request all of you to actively participate and interact with the speakers and enlighten the program and make it a grand success. The first technical session will be chaired by Professor Dr. A. Shaktivel, who is currently the Professor Department of Chemistry and also the head of the department. I welcome sir for chairing the first technical session.
Thank you, Nimisha. Very good morning, all of you. And it is my privilege to introduce Dr. A.K. Tyagi, the gem of the solid state chemistry. So when we initiated this program, this webinar, the first name we got it Professor A.K. Tyagi sir, and second one Professor Ganguly sir, both of them, because even when I was talking to somebody, they said that they are the real solid state chemistry in India. So it is very happy moment for me, and I am very honored to introduce the eminent personality, Dr. A.K. Tyagi sir, to the audience. Professor Tyagi has joined in BRC in 1985. So he is almost 35 years experience from BRC, and he completed his PhD from BRC Mumbai University in 1991. And he spent some time in the postdoctoral research in the Max Planck Institute, Stuttgart, Germany. It is one of the prestigious institute in the world. And then currently he is director of chemistry group, Bhabha Atomic Research Center in Mumbai. And also he is a senior professor at Homi Bhabha National Institute, Mumbai. Because I suggest all the audience, one time you have to go to the BRC and see the culture. We have to see, because I could able to visit BRC when I was in IIT Bombay for 5 years. So it is one of the very good institute and a very disciplined institute. And his research interest is functional materials and nuclear materials and nanomaterials. And he has awarded he has supervised 32 PhD scholars, and currently under his supervision, there are more than 10 PhD scholars are working. And he has more than 500 research publications, 8 books, and patents, several patents. And to his credit, he has a huge number of awards and other things. I will highlight some of the few things, like he has a Max Planck Fellowship in Germany. He has been awarded Lakshmi Award by ISCAS. Then he has a CRSI Bronze Medal, MRSI Medal, and also he has a DA Group Achievement Award, and Professor C.N.R. Rao National Prize Chemical Science Award. And also he has CRSI Silver Medal also he has received. And he also Acharya P.C. Rai Memorial Prize from Indian Science Congress. So he has a many list of awards there, but since the time I am just giving only few of his achievements. And he also the fellow of National and International Science Academic, like a fellow of Maharashtra Academy of Science, fellow of Royal Society of Chemistry, fellow of Indian Academy of Science, fellow of Asia Pacific Academy of Materials. And he is also members in the DST Project Assessment PAC Committee. And also he is a co-convener of the Board of Studies in Chemical Sciences in the DAE. And he has been visited several international institutes in Germany, US, France, Canada, Japan, and Russia. So with this brief introduction, I request Professor Dr. A.K. Tyagi sir to deliver your keynote lectures. Sorry for the delay, sir, because of the initial, there was an internet issue in our university. It was delayed. So over to you, sir. Please, sir.
Okay. Thanks, Professor Shaktivel. I had known you right from your IIT Bombay days. It's always a pleasure to attend the conferences of faculty members organized by faculty members whom I have known when they were PhD students. That is an additional pleasure, definitely. I must thank you once again for the kind invitation. Let me also thank Dr. Professor Kuru, Professor Swaminathan, President ISCAS, Professor Brajesh Pare, President ACT, Professor D.V. Prabhu, whom I have known for last more than 30 years, General Secretary of ACT, Dr. Srimati Bhagyalakshmi, and other delegates sitting over there, and offline delegates from all over India. Professor N.B. Singh and Professor I.B. Sharma, good morning to you all. It's a pleasure for me to give a talk in this conference co-organized by ISCAS. He mentioned a number of awards which have been conferred on me, but I must share with you all that it was the year 2001. It was, I think, second ISCAS symposium where I got my first award. Dr. Lakshmi Award was conferred to me in ISCAS symposium. That's why I mentioned in the beginning that ISCAS is somewhat close to me because all these recognitions, they begin with ISCAS only. Now let me share my presentation on pyrochlor. Just bear with me, some technical hitch.
Yes, sir, we can hear.
We are trying to share the PowerPoint.
Yes, sir. Yes, sir, we can see, sir.
You can see now?
Yes,
so
sir,
title of my talk is pyrochlore-based functional materials, which according to me are incredibly rich examples of structural property correlation. You can see partial view of BARC. This one is 40 megawatt Cyrus reactor commissioned in 1960. Adjoining one is 100 megawatt Dhruva reactor commissioned in 1985. Same year in which I did my MSc and joined BRC training school. I remember extremely well. It was 20th October 1985, Monday, when then Prime Minister Rajiv Gandhi came to BRC and dedicated the reactor to the nation. So as a young boy of 20 something, it was a very exciting moment to see reactor being dedicated to nation by then Prime Minister of India. How perovskites are AbO3? Pyrochlores are A2B2O7. It is their general chemical formula. Out of 7 oxygen, 1 oxygen is different and 6 oxygens are similar in terms of Wyckoff notation. This 7th oxygen I am representing as X, and this is easily replaceable by anions like oxide. Of course, it becomes O7, F minus, OH minus, S2 minus. So you can indeed make mixed anionic pyrochlores also, but by and large, people work on O7 pyrochlore, that is mixed oxides. Its name is originating from a mineral which has got similar structural. Its formula is NaCa at A side, niobium tantalum at B side, and O6 fluorine OH. It also has some chlorine. Nature, when it makes minerals, nature is able to stuff many cations and many anions, and there is a reason for that. We can discuss afterwards at length why nature is very fond of making simple compounds with multiple elements. Nature knows thermodynamics better than you and me. It has got 2 types of polyhedra. A site has got cube, B site has got octahedra, BO6 octahedra, and by changing the relative size of A and B cations and by playing with oxidation states, you can induce all types of properties in this structure. Chemically, I call it very flexible, more flexible than perovskites. And that's one reason it has attracted the attention of solid state chemists right from the beginning. Pyrochlore structure is an ordered variant of fluoride structure. I will discuss concepts in my talk, very important that I share concepts with young generation. So how does a fluoride becomes pyrochlore? This slide gives this kind of mechanism. Fluoride is AO2, like CO2, PHO2, UO2, and so on. Calcium dichloride, of course, the prototype fluoride structure. You replace tetravalent ion by trivalent B ion. So you make A1 minus X BX O2. Because of charge balance, there will be anion vacancies. It will be O2 minus X by 2. You introduce half B ions in plus of half A ions. So 50% of A ions are replaced by B ions. You make A.5, B.5, O1.75. This is defect fluoride, and this is extensively defective fluoride. 0.25 is the kind of vacancy in anionic sublattice. And this is very high concentration, and the structure knows how to relieve itself from excess lattice energy. So there is an ordering of this 0.25 oxygen an ordering of A and B cations. I will show these things in a more detailed way as I proceed further. You get A2B2O7. This is chemical formula is same. Of course, you divide by 4. You get A.5, B.5, O1.75. This is disordered and this is ordered. That's why I say that pyrochloride structure is an ordered variant of fluoride structure. The common radius ratio of A and B cations for pyrochlore to be stabilized is from 1.35 to 1.6. If it is more than if it is less than 1.35, then you don't get ordering and you get a defect fluoride disordered structure. If it is more than 1.6, you can imagine the B site cation size is very small. To support 6-fold coordination, B site cations, if it is too small, it will go for tetrahedra, not for octahedra. And we know from basic physics that coordination number can be increased by applying high pressure. So by high pressure, you can extend the upper limit of pyrochlore radius ratio even up to 1.9. Very small B site cations also can be stabilized in octahedral coordination by applying high pressure of 6 to 10 or 12 gigapascal. We have made some compounds at high pressure. In today's talk, high pressure stuff I am going to skip. What are the different combinations of ions which can stabilize pyrochlore structure? The most common is 3-4 combination, trivalent ion and tetravalent cation. In trivalent A side, we can stuff rare earth ions, indium 3+, helium 3+, and bismuth 3+, most commonly. B side, you can have commonly 3D elements, 4D elements, 5D elements, titanium, zirconium, you can have very commonly. You can also have germanium, tin, lead. As I mentioned, out of 7 anions, 6 are oxygen, and 7th one can be fluoride or sulfur. So you can go for partial substitution. And as I mentioned previous slide, the small ions like V4, Cr4 do not form pyrochlore unless you synthesize them by high pressure in order to stabilize 6-fold coordination. If you can make pyrochlores of vanadium 4, chromium 4 by some trick at ambient pressure, be assured you are going to publish a paper in JACS. 2,5 combination is another common combination where A site can have somewhat large divalent cations like calcium 2+, strontium 2+, cadmium 2+, mercury 2+, tin, lead. Accordingly, for charge balance, at B side you will need pentavalent ions, vanadium, niobium, tantalum, ruthenium, etc. One more class is there, that is 1,6 pyrochlores, bit rare. So in 1,6 pyrochlore, A site is occupied by somewhat large alkali metal ions like sodium or potassium, and B site accordingly by hexavalent ions like tungsten, etc. or molybdenum. You can also make some fluoride-based pyrochlore. Only 3 or 4 of them are known. One of them is made by me in Stuttgart during one of the visits in 2000. Pyrochlore structure, I told you in the beginning, is chemically flexible. I'll spend some time on this aspect now. But to begin with, I must mention this important class of materials, solid state materials, can support ionic conductivity, catalysis, optical materials. They are used for high-end thermal barrier coating applications because they are exceptionally stable. They also have got futuristic nuclear-based applications. And you can go for magnetism. Pyrochlore show what is called as frustrated ferromagnetism. It is geometric ferromagnetism. We can spend time on these things if you want to know more. How it happens that one class of material supports a diverse range of applications. The answer of this lies in structure. Incidentally, all the properties are governed by structure and chemical bonding, and these two things cannot be delinked. They have got lot of one-to-one correlation. So we again go back to one of my earlier slides. This is pyrochlore, A2B2O7. A ion is at A site, this side, and B ion is at this side, and they are crystallographically distinct. If you randomize by some way, you get complete randomization of A and B. You can distinguish, you get fluoride. So A2B2O7 divided by 4, it becomes A.5, B.5, O1.75. And this disorder can be introduced gradually with utmost control by playing with Ra by Rb ratio. So you go on decreasing the Ra by Rb ratio to drive a fully ordered pyrochlore to fully disordered chloride. And by this, in my group, we have published quite well in last 15 years or so. I'm going to cover almost entire work of pyrochlores in our group, barring high pressure. I may show one example towards the end if time permits. So some old work you can see in literature. So first set of examples of functionality of pyrochlore is ionic conductivity. Here I show you RNDS formula. Sigma is equal to sigma 0, pre-exponential factor is E divided by KBT. At a glance, you will know that sigma DC can be increased by increasing sigma 0 or by decreasing activation energy barrier. Sigma 0 can be increased if you make structure more disordered, whereas activation energy can be decreased if you make structure more ordered. So you see the complication now. Sigma 0 increase needs disorder, activation energy decrease needs order. So it is truly a combination of antagonism. These two properties are not supposed to exist. Now cricket match is going on between India and England. It is as good as saying a bowler is doing bowling as well as he is doing wicket keeping. Well, it is not possible in cricket, but in solid state chemistry these things can be done. I will show how it can be done, how you can have best of both. So one old series made by one of my colleagues, ND2 minus Y, GD ZR 207, Dr. Balaji Mandal. Now he himself is a senior professor in our department. So Raman spectra is shown gradually on going from ND compound to GD compound, and pyrochlores have got 6 distant Raman peaks. So they become broad and broader, but still this compound has got 6 peaks, so it is pyrochlore. Chloride has only 1 peak. So at a glance of Raman data, one can say that on going from this end to this end, disorder increases, and this disorder has got tremendous bearing on property. Here I show you plot of activation energy and sigma 0 as a function of ND content in this series. So compound which has got no neodymium, that is gadolinium zirconate, it is disordered, it has got high sigma 0. That's what we want. But this compound has got high activation energy also. So whatever you gain because of high sigma 0, you lose because of high activation energy, and in combination, this compound shows somewhat poor ionic conductivity. Other members, ND compound, which is ordered, obviously this compound has got low activation energy. Sigma 0 is also low. So whatever we gain by having low EA, we lose by having low sigma 0 also. In between a composition where we have one ND and one GD, sigma 0 is not too low, activation energy is not too high. And together they give us a compound with highest ionic conductivity. So in this compound, we could have best of sigma 0 and best of activation energy. I'll give some more examples as I proceed further. So that's how you create antagonism in a compound. Very important. Otherwise, conventionally, people should think these things can't be done. That's why this paper gets good citations. Of course, solid state route has got a limitation of not having high sintered activity. They give us poor sintered structure. So same compound we made by combustion method, topic of different talk altogether. And you can see we could achieve 94% of theoretical density at somewhat low temperature. You can see it is very well paired microstructure, and we got excellent ionic conductivity in hydrogen atmosphere also. There was no electronic conduction because neodymium and gadolinium are very stable even under extreme reducing conditions. So far so good. Next comes, can we further go about? So far I have shown you the optimization of activation energy and optimization of sigma 0 in the composition NDGD0207 to get best ionic conductor in this series. Can we further increase the ionic conductivity? Answer is yes. In that case, you have to introduce some defects by aliovalent substitution. So replace zirconium 4 plus by scandium 3 plus. Why scandium 3 plus? Because by scandium 3 plus, we choose a dopant which has got ionic size equal to that of zirconium 4+. So we don't play with Ra by Rb ratio. Ra by Rb ratio remains same, but at the same time we make anionic sub that is defective of vacancies. We introduce oxygen defects, and oxide ion conductor is defects mediated, or for that matter any ionic conductor needs some point defects. So you could see the best compound made by interplay of disorder and pre-exponential factor and degree of order. We could introduce some defects carefully, and we could increase the ionic conductivity one order higher. You can see from this slide. Pyrophore structure, many people used to think, including myself 15 years back, that they are 9 compounds. It means in the phase diagram of Re2O3 and MO2, these compounds exist only at one composition, that is 50% in between of the phase diagram. If not correct, we have shown in number of recent papers that pyrofluors do support a deviation from composition of 1:1. So in this series, you can see Nd content and zirconium content could be varied from 40 to 55 mole%. You can make Nd deficient, zirconium excess, or other way around, Nd excess, zirconium deficient. All these compounds, as per XRD, their big peaks are ordered, and as per Raman spectroscopy also, we get characteristic features which are typical of pyrophore structure. By doing so, by making some compound where Nd goes to B side, zirconium come to A side, we introduce tremendous disorder in the lattice, because now we have minimized the ionic size mismatch at A and B side, and that's one reason we got a benchmark ionic conductivity compound. This compound has got ionic conductivity as good as yttria as stabilized zirconia, and it has got advantages also. So simple solid state chemistry concept can be used to make tremendous functional properties materials. We showed by TEM very carefully that compound is basically ordered. You can see these weak spots. Weak spots correspond to superstructure peaks in XRD. So it shows this is ordered domain, and ordered domain has got disordered regions also. Here you get only the main reflections of chloride type. You don't get weak spots which characterize the formation of pyrochlore. So in a predominantly ordered structure, you have got disordered domains. For this kind of studies, XRD is not a good tool. You have to resort to transmission electron microscopy and SEED. I now change the gear and I show some examples of cerium 3+ based pyrochlores. Why we chose to work on these compounds? Because from simple periodic table you would know that C4+ is 4F0 and C3+ is 4F1. So C4+ has no unpaired electron. That's why compounds of C4+ do not have many properties. Properties come from unpaired electrons. However, it is a challenge to make compounds of C3+ because we are working against the dictates of thermodynamics. So we developed a 2-step method. A young colleague of mine, Rakesh Shukla, he himself is now a senior person and doing extremely well. He made combustion method. He made compounds by combustion method. And by combustion, you know you can't make compounds of reduced ionic oxidation state. Subsequent step, we heated them under high vacuum. And vacuum was created by zirconium sponge. Zirconium is oxygen getter. So by this technique, we can get very low partial pressure of oxygen in this ampule when it goes to the furnace, because this ampule already has got -6 bar kind of pressure. And when it goes to furnace, zirconium sucks entire oxygen. Low partial pressure of oxygen was responsible for getting us compounds of C3+ against the concepts of periodic properties and the concepts of solid state chemistry and thermodynamics. So we made a compound C2O7. After making this compound, we oxidized to O8. So O7 compound, O7.5 compound, and O8 compound all turned out to be distinct. You can see this pyrochlore. This compound was known incidentally, not that we made for the first time. So this is the vacancy. I was telling you pyrochlores have got one vacancy. It should have been O8 as per fluoride formula, but it is O7 and one vacancy is vacant. It is lying here. So the trick was gentle intercalation of oxygen. Oxygen was loaded in this vacancy very, very gently, and this becomes O8. ZrO6 polyhedra becomes ZrO8 cube without any collapse of structure. If same compound, this is a new compound, it does not exist in phase diagram. If same compound you make by solid state, you can never ever make this compound. What you will get as per phase diagram, two compounds. You will get a phase separation into two fluoride type lattices, as you see it here. The gentle approach gives you this compound, and a brutal approach gives you a phase separation. And in your life and career also, gentle approach works much better than so-called brutal approach. Always go for gentle approach while dealing with your younger and junior colleagues. Well, what is the application? O7 becomes O7.5, it becomes O8. So clockwise it picks oxygen, anti-clockwise it loses oxygen, and this clockwise, anti-clockwise you can do n number of times without any collapse of the structure. So I will ask some questions to younger colleagues who are participating in the conference. C2ZrO7 shows this clockwise, interclockwise oxygen intercalation, whereas titanium analog does not show this kind of oxygen storage capacitance in which oxygen can be added or can be removed. So question number 1 to younger colleagues, please do answer this question. What is wrong with Ce2Ti2O7 compared to Ce2ZrO7 that it does not show this kind of cyclic transformation induced by oxygen addition or oxygen removal? I proceed further. When you make compounds like this, people show a lot of interest. Dr. Raja, a good friend from NCL Pune, he wanted to use this compound for what is called in organic chemistry oxidative dehydrogenation of organic compounds. By ODH reactions, you introduce unsaturation in organic compounds. So ethyl benzene, you introduce double bond, you get styrene. Styrene is highly value-added chemical. It is used as a monomer to make polystyrene, and we got excellent results. I will go a bit fast. We got excellent stability for more than 3 days compared to conventional compounds in literature. There was a high selectivity, there was a high conversion efficiency also, and catalyst does not degrade upon repeated use in ODH reaction. Likewise, another great friend of mine, Dr. Professor Gopinath, and I believe he's giving a lecture, I think tomorrow or today only at 4 o'clock. So he also showed a lot of interest in this compound, and he used this compound after decoration with palladium for Suzuki coupling. Suzuki coupling is a Nobel Prize discovery. It's a great piece of work, and the reason is that it is difficult to make carbon-carbon bond. CC bond is very difficult to make and very difficult to make also. Why they got Nobel Prize? Because now most of the drugs which one pops up in the morning are made by Suzuki coupling. This is a contribution of these people. The requirement is that you need a precursor which is nucleophilic and precursor which is electrophilic. So you do reaction, you do refluxing of say iodobenzene and phenylboronic acid with the help of this catalyst, and there will be an elimination reaction. You can create a new carbon-carbon bond. We made number of other combinations. This work also gets good citations. Probably I won't spend much time. Only one thing I want to share with you, those of you who work in catalysis, that slight excess of cerium 3+ was found to enhance the catalytic activity of palladium. So at times we have to engineer the support also. Mostly people take support for granted. That's not a good approach. Support also you have to engineer. This is one example. I may show some more examples if time permits. Of course, one example right now I will show you. This compound was used again by Dr. Gopinath and his younger students for oxidation of carbon monoxide to carbon dioxide. Here also we reported that slightly reduced cerium is a better support to host palladium as a catalyst because it activates the electron rich center is able to activate palladium in a better way. You can go through this paper to know more details. This slide probably I skipped because I have some more things to share with you. one more example of band gap tailoring in pyrochlores. As I mentioned at the beginning itself, that pyrochlore structure is quite flexible. And because of this nature of flexible structure in pyrochlore, you can incorporate many cations at A side and B side. In this case, we made a composition like samarium 2 minus X dy X Zara to O7. And you can see band gap was fine-tuned from 3.81 to 3.44 EV. It was used for a model catalytic reaction, namely xylenol degradation. We got the best results of 3.4. T half is the time required for half of the degradation. So a compound's catalytic activity is, arranged in terms of T half values. T half is the direct parameter which can be used to say whether compound is active or inactive or in between, etc. One more example of catalysis is on Bi2 minus X LaX SN2O7 series. This series was made by combustion, as you can see I am mentioning here, and we investigated for structure, phase transitions. Phase transitions probably I am going to skip in today's talk, and the band gap tailoring was done in this case also. So 2.55 EV band gap was for bismuth compound. As you incorporate lanthanum, band gap goes up to 2.95. So concept is bismuth 3 plus is a lone pair ion. That's why Bi2O3 has got slight yellowish color. So a lone pair ion, if you replace by another cation which has got zero field configuration, lanthanum 3 plus is 4F0, band gap can be increased. These are the concepts of tailoring of band gap, and this also was used for degradation of rhodamine B, a toxic dye. So under visible, rhodamine dye is degraded, and you can see there is a shift in the absorption spectra. Under UV, it degrades to fully, but no shift. So basically, under UV and visible irradiation scenario, the mechanism is different. In one case, it is dethylation, and in other case, it is cleavage of chromophore ring. So that's how we can propose the mechanism. We use a lot of NMR techniques to establish the mechanism in this compound. One very recent work, accepted just about 10 days ago. I'm sorry I could not make more slides because of lack of time, but still the entire paper, some 15-page paper, I have stuffed into one slide. So we made a series. Y2SN2O7 was N member, and other number was Y2Zeta2O7. On going from this to this, that is on increasing X value, we showed that in between pyrochlore becomes defect chloride, and this can be explained by Ra/Rb ratio. And we showed using 119 NMR, 10 NMR, solid-state NMR, that there is a peak broadening, and there is randomization between tin and zirconium is not there. They do have some local ordering. It was shown by NMR. It was also shown by EXAFS. It's a powerful tool available in RRCAT Indore. This compound we use for model reaction, namely degradation of methylene blue, a toxic dye. Compound in between showed the lowest T half. So the end members were poor catalysts compared to a compound where we had one tin and one zirconium. As you can see, activity decreases and then T half decreases and then it increases. So T half why this composition is the most active, and we showed this result. We explained this result based on an interplay of particle size, surface charge, and deviation from BOB bond angle. And BOB bond angle has got a bearing on electron hole separation. This is a good piece of work. I would encourage you to go through, and sometime else I will make a dedicated talk on this compound itself. So some more concepts. How to make new pyrochlores? Of course, one approach is that you can try new combinations of 3, 4, and 2, 5 cations. One more approach I want to share with you. Many compounds which are at the border of Ra/Rb ratio. You recall I mentioned Ra/Rb ratio for pyrochlore is 1.336. So all the compounds which are reported as defect chloride, because they are at the border of 1.336, friends, have to be reinvestigated by powerful tools. We made number of compounds which are at border and much lower than border, and we investigated using synchrotron radiation based XRD and also Raman spectroscopy, etc. So by lab source, XRD shows only peaks due to fluoride type. That's why this compound was reported as fluoride. Whereas Raman spectroscopy, so XRD could not prove that it is pyrochlore. Based on XRD, it is defect fluoride only. But Raman is more powerful. Raman spectrum you can see shows killer cut features of pyrochlore. So same compound we investigated by high flux synchrotron radiation, and you can see we get weak peaks which are characteristic of pyrochlore lattice. So if you want to make new pyrochlores, please do revisit the compounds at the border of pyrochlore and fluoride, namely 1.336. I am sure you will publish very good papers out of this. Now, towards the end, I will discuss some applications for nuclear. Pyrochlores are used for nuclear-based immobilization, radiation-stable materials, and we have developed burnable neutron poisons for some applications. This part I'm not going to skip. I'm not going to cover in today's talk as it is slightly of different nature. So, one approach of immobilizing nuclear waste is, of course, glasses, which are used in India and other parts of the world also. The upcoming approach is to immobilize nuclear waste in synrock. Synrock is nothing but synthetic rocks. Synrocks are found in nature and they are assemblage of zirconolite, perovskite, hollandite, pyrochlore. So you can see pyrochlore structure is an important component of synrock in nature as well as in lab. So we did a lot of work. We used this compound 020207 for immobilization of thorium. You can see thorium solubility was very less. It was about 3.75% only. Subsequently, you can see we see phase separation as we increase the concentration of thorium. Somewhat old work, but important work. Subsequently, we incorporated thorium at A site, aluminum at B site. Because in advanced high water reactor waste, we'll also have thorium as well as aluminum and fluorine. These three will be the additional constituents of ASWR waste. So by this approach, thorium solubility, which was limited as 3.75 mole percent, could be increased to 20 mole percent. Why it could be done? You can appreciate the concepts of solid state chemistry. Thorium at GD site, aluminum at zirconium site. So 3 plus ion is replaced by 4 plus, and 4 plus ion is replaced by 3 plus. So it is called as charge compensatory substitution. So you select two dopant ions in such a way that they do charge compensation. What we achieve in this case, we don't disturb the oxygen anionic sublattice at all. With thorium alone, we make it O7 plus X. With aluminum alone, we make it O7 minus X. So we make it either oxygen excess or oxygen deficient. By this approach, we make it exactly O7 even after incorporating 20 mole percent of thorium and aluminum. So simple approach could be used to solve some of the problems of department, as you can see in this slide. We also use this host material for uranium incorporation. Uranium was taken as surrogate for neptunium, and you can see a lot of work was done by XRD, XPS, because uranium, unlike thorium, can exist in 6 plus, 5 plus, 4 plus oxidation states. So pyrochlore structure, I told you in the beginning itself, has got tremendous stability. You can see here we have got minus 4,000 kilojoule per mole enthalpy of formation of this compound. Extremely highly stable compound. Whereas if you incorporate hexavalent uranium, it further becomes negative. So if we replace 0.15 of GD by 0.15 of uranium in hexavalent oxidation state, the thermodynamic stability of this compound, which was to begin with also very good, it further improves by 440 kilojoule per mole as compared to pristine compound. This is an excellent result for long-term storage of actinides in the lattice of pyrochlore with composition GD2, ZR2, O7. So of course, this part probably I will skip. This is also some of the synrock compositions. Maybe we will have more time for discussion. So I want to skip this also. One last example, why pyrofluors are finding a lot of applications in high end? The reason is that they have extremely high chemical stability. Number one, they have extremely high thermodynamic stability also, and they have got very high radiation stability as well. We did a lot of collaboration with Dr. Awasthi and Dr. Pawan. Now, incidentally, he's a faculty member in JNU Delhi. At IUSC New Delhi, we used the Pelletron. We made 3 compositions with these formulas. At B side, we have titanium, and here we have zirconium. In this compound, A side is neodymium, and B side is zirconium. We irradiated them by different heavy ions like 70 MeV nickel, 90 MeV iodine, 120 MeV gold. So you can see in this direction, the electronic energy loss dE by dXe is increasing from 10 kV per nanometer to 20 kV per nanometer. And we change the fluence also. So GD compound remains crystalline. ND compound remains crystalline, but there is some loss of crystallinity. You can see background has increased. And compound which has GD and titanium becomes fully amorphous. So you see how by playing with Ra by Rb ratio, you can make pyrofluors of exceptionally high radiation stability. This compound, for example. So as Ra by Rb ratio increases, radiation stability decreases. The reason is that in this compound, titanium has got tremendous preference for B side. This compound, zirconium, has got, of course, preference for B side, but zirconium is at the border. Zirconium can be driven to occupy A side also. So in this compound, upon irradiation by heavy ions, we could make pyrofluor into fluoride by anti-site formation mechanism by swapping of GD and zirconium ions. In this case, swapping of ions is not possible because titanium 4+ will never adopt qubit coordination, unlike zirconium 4+. That's one reason. Under same conditions, this compound undergoes lattice frustration. This compound releases excess energy imparted by ion beam irradiation by undergoing amorphization. This compound releases excess energy imparted by ion beam irradiation by undergoing a phase transformation from pyrofluor to fluoride. So if you want to make compounds, pyrofluors of high radiation stability, please do work on compounds which are at the border of Ra by Rb ratio between pyrofluor and fluoride, compound which can easily transform into fluoride. If you want to work on high oxide ion conductors, much better oxide ion conductors, please work on the compositions which are neither at this extreme of 1.336 nor at the other extreme of 1.6. You should work on the pyrofluors which are somewhere in between 1.5, 1.55 Ra by Rb ratio, because by this kind of in between Ra by Rb ratio, you can have best of sigma 0 and you can have best of Ea, and in turn you will have highest ionic conductivity. So these concepts I thought I will show you, and if you want to work on pyrofluors with magnetic properties, please go for B side unpaired electron ions like vanadium 4+, etc. Or A side you can go for cerium 3+. I give you a number of examples. Probably I escaped, as I can see my time is almost up, and I would like to have time for discussion. Some more work in which we showed you can play with composition, you can play with A and B site ions, and you can make compounds of exceptional high radiation stability. Work was published about 7-8 years back. One last example. Bear with me, some technical hitch.
No problem, sir.
Yeah, I'm not able to change the slide. It happened once earlier also. Okay, so it's okay. I think there is some issue. This was my last slide, incidentally. So I mean, just see if something is better. It happened earlier also, about 2 weeks ago. Could you remember in that talk which I was giving? So around this time, after 1 hour or so, 45 minutes, it hangs. Okay, so my younger students are saying that there is a serious problem. It happened earlier, 2 weeks back also. Towards the end of my talk, it hanged. So anyway, it was my almost last slide. The subsequent slide was only for summarizing my presentation, that how by knowing the concepts of the structure, you can fine tune the properties. I give number of examples. I give examples of ionic conductors, examples of oxygen storage capacitors, examples of magnetism, catalysis, etc. And one slide was for thanking my younger colleagues. In this one, we had number of colleagues like Balaji, Rakesh, Vinita, Maulik Patel. Maulik Patel, my PhD student, now he has become faculty in UK, and Rakesh Shukla, etc. I must once again thank all the organizers, Dr. Shakti Vail and other colleagues. Thank you very much. Now I'll be happy to take the questions. Can we go forward?
Thank you very much, sir, for a wonderful talk on pyrochloride. I think it is a kind of new materials. I think many of audience may not be even aware about it, but you have given a very wonderful introduction and how one can prepare and tune the electronic and ionic properties. So now it is open for the question. If any selective 1 or 2 questions, you can ask our eminent Professor A.K. Tyahi. Sunny, can you unmute everybody? Sunny, can you unmute? If anybody have doubt, clarification, you may ask Professor A.K. Tyahi 1 or 2 questions.
Sir, I have removed the forced mute condition. Now people may unmute themselves.
Okay, thank you. Anybody, you may unmute your audio and you can ask questions. If not, you can also put a chat box message if anything. Sir, it is a wonderful lecture, sir. I have one since student.
Yes.
Sir, why always we choose the lanthanides mostly for this kind of superconductor and other kind of ionic conducting properties? We choose mostly lanthanides, sir.
Yeah, correct. So let me first explain ionic conductors. See, it is like this. In ionic conductivity, if you don't have lanthanide ions, have got very stable oxidation state. The Gd3 plus, La3 plus, Y3 plus, okay, Nd3 plus, they will not be reduced so easily under reducing conditions.
Okay.
If in any compound you have bismuth, for example, bismuth-based compounds are there which are good ionic conductors, but they try to develop electronic conductivity under slight reducing atmosphere. Orvillez compound Bi4 Ti3O12 is one of the best compound. Delta Bi2O3. Delta Bi2O3 is known as super ionic conductor, but believe me, it is in the absence of reducing atmosphere. The moment we have got slight reducing atmosphere, all these compounds which have bismuth, etc., or antimony, etc., they develop tremendous electronic conductivity. Transference number for ion reduces much lower than 1. That's one reason that you take lanthanide-based ions with exceptionally stable oxidation state to make ionic conductors. Coming to superconductivity, of course, next speaker has done a lot of work on superconductivity, Dr. Professor Gowli, a good friend of mine.
Yes, sir.
See, you don't take elements which make excellent conductors. By simple concepts I can explain you, most superconductors are the ones which are not excellent conductors. You can't make a superconductor with, let us say, silver or gold, because they are excellent conductors. And some simple theories are used when you have this kind of slightly poor conductivity of electricity. They support the Cooper pair formation.
Sure.
That's why you have got yttrium compound, lanthanum compound, okay. Of course, you have bismuth compound also, but you will hardly come across a compound of aluminum metal or copper metal or silver metal or gold metal, because they are too good conductor to support the mechanism of pairing of electrons or holes.
Sure. Thank you, sir. Any other? Any one more?
Professor, very good morning. This is Stalin, Alapani Institute, Tamil Nadu.
Good, yeah, please ask me. Good morning. Good morning.
Good morning, Professor. Very excellent presentation. Really, I gained more knowledge from your presentation. Thank you so much. I have one doubt. Actually,
yes.
when we look solar cell fabrication, especially dye-sensitizer solar cell, some of the dyes can be act as a good light absorbing material. Is there any possibility to apply for your material to solar cell applications?
These materials?
Yes.
Yes. The materials which have got, I showed number of materials with band gap in the range of visible and in the range of border of UV visible. Okay. 3.1, 3.2, 2.99. Okay. So bismuth based series which I showed definitely has potential to be used for solar applications.
Okay, thank you. Because
since in my group we don't work on these things, so we have not explored.
Okay. Because the ionic conductivity is very essential things, can be act as a photoanode in solar cell.
Thank you, sir.
Thank you.
Sir, on behalf of organizing committee, I take up an opportunity to thank Dr. Professor A.K. Tyagi sir for accepting our invitation and coming and sharing a very novel idea of pyrofluorides and its importance. Thank you, sir. Thank you very much for your presence. We thanks for your all the audience. You may unmute and clap. Thank you, sir. Thank you, Professor A.K. Tyagi sir.
Okay. Yes.
Now,
so I will disconnect now.
Professor Kambli sir also here?
Yeah, I have joined. Yeah. So I will say goodbye to Dr. Tyagi. He will leave probably very soon. So
yes, sir. Kambli sir is here.
Thank you.
It was nice to hear your voice.
Nice to hear your last 15 minutes. I heard very nice. So thanks. We are not meeting for a long time, so we'll stay in touch.
Yes.
So yeah, I just wanted to say hello to you.
Thank you very much.
Okay. Bye.
Bye.
Thank you, sir. So with this, we are ending the first technical session. So Nimisha, are you there?
Yes, sir. So that was a great beginning for our webinar. We are moving to technical session 2. Our technical session 2 will be chaired by Professor M.R. Pradapachandra Kurup, sir. He has a teaching experience of more than 35 years, and currently he is the Dean of School of Physical Sciences in Central University of Kerala, as well as professor in the Department of Chemistry. I welcome sir to chair the session 2.
Good morning, everybody. I would like to introduce Professor Ashok Ganguly. He is currently Institute Chair, Professor of Chemistry, and Deputy Director, Strategy and Planning at IIT Delhi. He is also the founding director of Institute of Nanoscience and Technology in Mohali. Professor Ganguly obtained his PhD degree in inorganic chemistry from Delhi University, his MSc degree from Delhi University, and a PhD degree from Solid State and Structural Chemistry Units, Indian Institute of Science, Bangalore. In 1990, in the area of thallium-based high temperature superconductors, for which he got the Sudborough Medal of Indian Institute of Science. He has been a visiting scientist at the DuPont Company, USA, and a postdoctoral associate and visiting scientist at Ames Laboratory, Iowa State University, USA. His main areas of interest are design of nanostructured materials for applications in water purification, solar energy conversion, and microfluidic devices, and also high temperature superconductivity. He has published over 450 papers and also has filed five patents. He has successfully completed several research projects, including some with industries. He is a recipient of National Award of Nanoscience and Nanotechnology given by DST, Government of India, and CRSA of India, Silver Medal. Material Research Society of India Medal, and CNR Rao CRSA National Award. Excuse me. Chemical Excellence Award by the Indian Society of Chemists and Biologists, and Bangalore, India Nano Award won by Karnataka government. He is a fellow of Royal Society of Chemistry, London, Indian Academy of Sciences, National Academy of Sciences, India, and the Asia Pacific Association of Materials. He is currently an associate editor of Bulletin of Material Science and a member editorial board, Journal of Indian Chemical Society, ACS Materials Letters, and Chemical Physics Letters. He is a very keen speaker for science education and science popularization in schools and colleges, and has initiated an outreach program at INST, Mohali, for rural school students in remote parts of India. And he has visited more than 300 schools, and he has created several programs, especially for ST students, and involved a large number of students from J&K to Kerala and from Manipur to Rajasthan. Apart from above, he is a keen speaker in Inspire series of lectures supported by DST, and also helping research awareness in colleges through Science Academy. Professor Ganguly, it is now over to you for the talk. Thank you.
Thank you, Professor Kurup, and thank you, Professor Shaktivel, for inviting me to share my thoughts. And I am also thankful to my dear friend Sudarshan. I think he's there. You can see him. Nice to see you. Okay, we were in Delhi University sometime long back. So thank you for your kind invitation. And I will talk to you today about some materials which are called superconductors. I think most of the participants are university students, master's students of chemistry. And is that right? And teachers? Is there
teachers as well as
research students? Okay. And I'm speaking from to Central University mainly. It is organized by Central University.
The Central University of Kerala.
Right. I have not visited that, but I visited some other colleges in Kerala, where Sudarshan was there. I think one of the colleges, and of course several schools he organized in Trivandrum and nearby places. So I have some very nice memories of Kerala, where I gave lectures. So today I'll share my slide, and because we are running late and I have a meeting exactly at 12, so I will have to leave the moment at 11:55. I will have to leave. Can you see my? I'll just share.
Yes, we can see your screen, sir.
Okay.
Yes, sir.
Okay. Can you see this?
Yes, sir. We would be able to see, sir.
Okay. All right. So I'm going to talk to you about some new superconductors, but I'll give a little bit more general aspects because the audience is more master students and research students. So, but I will focus later on some new superconductors we have made in the last 4 or 5 years, and materials. That is the title, new superconductors with conducting bismuth sulfur or bismuth selenium layers, which we have been working over the last 5 to 7 years. But before that, I will tell you briefly what are superconductors and all. This has been done by several of my students. This particular work on bismuth sulfur and bismuth selenium has been motivated by my students Gohil and Ziba. They have finished their PhDs. Somenesh just finished his PhD, and some work of chalcogenide, I may speak, Momita, who is just finishing her PhD. And I have collaborated with Dr. Patnaik at JNU, Professor Armugam at Bharatidasan. Professor L.C. Gupta used to visit us, etc. The funding is from SCRB and DST. So just to tell you what are superconductors, all of you know in materials, you have heard of the word semiconductor, right? You have heard of the word metal. If you look around you, all materials will have some property. Something like a plastic will have a non-conducting property. It is not conducting. That means opposite of conducting is insulating, right? And a semiconductor is also has high resistance. So how do we differentiate? We look at one property which we call the band gap between semiconductors and insulators. The band gap difference changes. But metals and semiconductors, the resistivity itself changes with temperature. So as you go down in temperature, in a metal, the resistance decreases. For a semiconductor or an insulator, it is just the opposite. So metal, semiconductors, and insulators, all of you must have heard in your BSc or MSc, but superconductor is different. Though copper, silver, gold, platinum are all very good conductors, we use them for in our electric wires, etc., for transmission, but they are not superconductors. Very good metals are also not superconductors like gold, platinum, because they don't go to zero resistance. Okay, so that is one important difference. Semiconductors, you know, silicon, gallium arsenide, indium antimonide. These are world famous semiconductors used in solar cells, etc. All of you know these are semiconductors. Insulators are like dielectrics, are used in capacitors. It is just the opposite of a good conductor, a very bad conductor like wood or plastic, right, or rubber. They are very bad conductors of electricity. So those are very high band gap materials, and those are like sodium chloride or diamond or silica like sand. So these are all the different classes of materials. In terms of resistance of the material, you know, and you are taught in school, college, etc. So superconductivity is different. It was discovered in 1911 by Kamerlingh Onnes. He was trying to liquefy mercury, and he liquefied mercury. You know, all of you us know today that mercury, becomes superconducting at 4.2 Kelvin. So he was studying the properties of mercury, and he was liquefying helium. Okay, sorry, I was saying mercury. Mercury he was studying using liquid helium. So he was the first person who liquefied helium. And because he could liquefy helium, which is very difficult, he could study low temperatures. At till 4K he could go. 4.2 K is the superconducting transition of mercury. So what is this superconducting transition? So normally, if you plot resistance versus temperature, if you can see here, my cursor I am moving, resistance versus temperature. A metal, the resistance keeps decreasing as you lower the temperature. But in superconductor, it behaves like a metal, but at a particular temperature, the resistance just goes to zero. That is a very different behavior from any normal metal. Semiconductor behaves just the opposite. The resistance keeps increasing as you lower the temperature. So this is the difference. There is a point, there is a temperature below which there is no resistance you can measure by any known instrument in the world. Okay. So that is why we say it is zero resistance. Okay. And so mercury was the first material, it's a metal, as you know, it's a liquid metal, and it was studied to be a superconductor by Kamerlingh Onnes, and he got the Nobel Prize for this in 1913. This is the first Nobel Prize of superconductivity. There are 5 Nobel Prizes given in the subject of superconductivity. There is no other subject in which so many Nobel Prizes are given. Okay. Now, what is the physics? As people started understanding, it was found that superconductivity is a quantum phenomena. It is the only 2 quantum phenomena which you can show in classroom easily to even school and college students. You cannot show normal quantum phenomena. You have to use gadgets, or you have to use technology like very high vacuum, etc., to show quantum effects. But superconductivity and superfluidity are 2 such macroscopic. What do we mean by macroscopic? It can be seen with the eyes at the large size of the object. So it can be seen in a large chunk of a material which is a superconductor. So these are basics of physics. What is a quantum phenomena? What is macroscopic quantum phenomena? And superconductivity is one such thing. There are many other properties of superconductors. Zero resistance is one property that was found by Kamerlingh Onnes. But associated with it, there are many properties found over the next 30 years. For example, levitation is one such property, that you can lift a material on top of a magnet. So a magnet and a superconductor, if you bring together, below the transition temperature, the superconductor will remove the lines of magnetic force, and hence there will be an opposing force and the material will be lifted. This is called levitation effect, and it's shown by superconductors in the presence of magnets. So based on that, magnetic levitating trains are known in the world. Okay. So as you see, I'm showing a non-superconducting metal or a normal metal like copper or silver never goes to zero. There is always a residual resistance. It may be very small. This number is very small. It may be 0.000 some ohms, but it will be very small. But in a superconductor, it will go to zero resistance. So these are all plots to show how from a semiconductor one goes to a metal, but none of these are superconductors because they are not going to zero resistance. Using superconductors, one major important is that it can store energy. So many people in the world, especially in Japan, they work on superconducting magnetic energy storage. It can store electrical energy. So because this is one of the important things, what do you do when you generate electricity? How do you store it? So either you store in the form of batteries, or you store in terms of storage rings, which are called magnetic storage rings. And here you need superconducting wires. So in a normal superconductor, there is no band gap between the conduction band and the valence band. In a semiconductor, there is a band, but it's very high. It's like 1 electron volt or more. In a superconductor, a very small energy gap is generated at low temperatures, which is order of 0.0001 electron volts. It is 1,000 or 10,000 times smaller band gap than a normal semiconductor. So semiconductor has a band gap. A superconductor has a superconducting gap, which is 10,000 times smaller than a semiconductor gap. And so it is very different from a metal, because a metal has no band gap. A metal has a zero band gap. The other important property, which I said on the basis of levitation, what happens is the Meissner effect. What is the Meissner effect? In a normal material, like a metal, magnetic lines of force will go through it. It's called a paramagnetic thing. But in a superconductor, all the lines of force will go out. This is called flux exclusion. This is also called Meissner effect. Okay. There is one more term, property, which is called persistent current. A superconducting ring never loses energy. If you put a current in a ring of superconducting coil, the current will flow for infinite time. It will never dissipate. That is the importance of a superconducting ring. That is why it is used for magnetic storage. The energy doesn't dissipate. There will be no loss of energy in superconducting wires. Whereas in our copper wires, which we use at home, there is energy loss. That is why we pay electricity bills, because we use energy. Whereas if you use superconducting wires, there is no loss of energy. But why we cannot use them? Because we don't have room temperature superconductor. Otherwise, we'll have to cool our house to very low temperatures to use superconducting wires. What is the theory of superconductivity? There is no perfect theory of superconductivity. The best theory was given in 1957, which got a Nobel Prize in 1972, which is given by Bardeen, Cooper, and Schrieffer, but it doesn't explain the superconductors of today. So it is a good theory, but it is not the perfect theory. People are still working on what is the perfect theory. So how superconductivity happens? The theory said when electrons move in a material, when one electron comes close to another electron, through the lattice, it gets connected and two electrons form a pair. This is called Cooper pair. This theory said you need electron pairs to form in a superconducting material. Then you can explain the superconductivity, then you can explain all the properties, but it does not explain all the superconductors known today. This theory was given by Bardeen, Cooper, and Schrieffer. It is based on coupling or two electrons coming together forming a pair. And so what is the difference? Once electrons are there, it forms one kind of physics. It's called the Fermi-Dirac statistics. When electron pairs are there, it follows a different physics. It's called the Bose, S.N. Bose gave this theory. So it's called the Bose-Einstein statistics. All of you should know about it. He was an Indian who should have got a Nobel Prize because using his theory, half of physics is explained. That's called the Bose-Einstein statistics. Einstein did only translation. The theory was given by Bose. Einstein translated into German. That's all his contribution. Okay, otherwise Bose should have got the Nobel Prize, but those days India was not independent and all that. But this theory today is all over the world. It is used in half of physics is explained. Entire light, photons are explained by that. Okay, so 5 Nobel Prizes have been given for superconductivity so far, from 1913 till the last Nobel Prize in 2003. I don't want to tell you in detail. These are all the applications of superconductors used in medical. All of you do MRI. If you fall down, you will do MRI. You need superconductors. In the maglev trains, the fastest train in the world for passengers is run in Shanghai, which runs at 450 kilometers. Okay, then you can store energy, etc. That's for energy storage. You can use in your brain, etc. the quantum devices based on superconducting coils because they are the most sensitive in picking up nerve signals. Okay, so that is why they are used in squids, etc. I don't have time. Okay, the 3 properties of importance in superconductors is critical temperature, critical field, critical current density. So there are hundreds of materials. You need to know which material has high critical temperature, high critical field, and high critical current density. So you need a material which has a high critical temperature, a high critical field, and high current density. What do you mean by critical field? Suppose you apply a field and the superconducting transition is destroyed. That means you don't see superconductivity. That means it cannot work. So you can only work at some field. Below that, it will work. Above that, it will not be superconducting. Similarly, you can pass current through a coil. Below a certain current, the superconductor will work. Above a current, the superconducting property will be destroyed. So you need a material which can take high currents and high magnetic field. Okay. So what are these materials? Coming to materials, because that is what chemists understand. Over the period of time, if you look at the periodic table, there are so many metals which are superconductors. The blue ones are superconductors at normal pressure, but the superconducting transition temperature is very low. 1 Kelvin, 2 Kelvin, 0.5 Kelvin. So they are difficult to use because they are very low temperature superconductors. The green ones are also become superconducting at high pressure. So you see, lot of metals are superconductors. But as I said, their TCs are very low. 1 Kelvin, 0.1 Kelvin, 1.4 Kelvin. We don't want to use such materials because you have to use a lot of energy to go to low temperatures. the world will, you won't have a commercial establishment or an industry using these metals because the transition temperature is very low. You want high transition temperature, so your energy for cooling is not wasted. So for that, people started searching for superconductors. And over the last 100 years, what has happened? For nearly 70 years, from 1911 to 1986, only metals or alloys were known as superconductors. So the highest TC was 23 Kelvin in niobium-3 germanium. These are the materials, niobium-3 tin and niobium-3 germanium. These are like alloys or intermetallic compounds, which are used in all the NMR machines of the world. And all the MRI machines of the world use niobium-3 tin or niobium-3 germanium with slight doping of titanium to make superconducting wires. Entire world uses it. Even today we use it because these are the most advanced or developed industries in the world. But the superconducting transition is still 23 Kelvin in this. You need liquid helium or compressed helium to cool to that temperature. Whereas in 1986, the world saw a change. For the first time, people broke the barrier of 23K and came to 30K superconductors. And then within 4 or 5 years, the world of superconductivity changed because we got materials which were 90K superconductors. What is the importance of 90K? Once you have 90K, you can cool by a reagent which is very cheap. And what is that? That is liquid nitrogen. It is very easy to produce liquid nitrogen. I can do experiments. I have done experiments in high school also with liquid nitrogen. I do regular experiments in colleges and high school when I show superconductivity with liquid nitrogen. But you can't do that in a school or a college with liquid helium. That means only after 1986-87, you could show this even in a village school by carrying some liquid nitrogen with us. But carrying liquid helium is very difficult, okay? So the world of superconductivity changed after 1987. So between 1987 and 90, you see so many classes of oxide superconductors were discovered. Today, the world has superconductivity known in some cases even in 230, 240 Kelvin. But still, we have not achieved room temperature superconductivity. So what are the materials which are superconductors? Elements, as I showed you, so many elements in the periodic table. Highest TC is 9 Kelvin. Intermetallics, highest TC is 23 Kelvin, right? But liquid nitrogen cannot be used for them. Borides are there, chalcogenides are there, but oxides show the highest TC. So the highest oxide TC known for a long time was in mercury-based superconductor of 133 Kelvin. Now there are other materials, but still the most standard material the world uses is bismuth-based high-temperature superconductor at 120, 115 Kelvin. Otherwise, they use niobium-3 tin, which is 23 Kelvin. Because the industry has developed over 40, 50 years, they use those wires, they make those wires. Even carbon-based superconductors are known. You know, you can make carbon-based C60-based superconductors. These are all studied today. These are the world's best known superconductors, which are in all NMR machines. Their structure is like this. They are made of niobium-3 tin and niobium-3 germanium. And these are called A15 structures. No crystallography. It is taught different classes of crystal structures. One of the structures is called A15 in this German nomenclature, which is called structure Berish. And it has a 3:1 molar ratio of two metals. One is copper, one is gold. The gold is at the corners of the cube and the copper is at the face centers. This will give you a ratio of 3 coppers to 1 gold. It is called Cu3Au. In niobium-3 tin or germanium, which are superconductors, niobium is sitting in copper sides and tin is sitting in gold side. So that is why you have 3:1 ratio, and this is the simple structure. Okay, and I won't tell you more about this, but this has copper-copper dimers along one of the axes, which causes superconductivity. In this material, copper one does not show superconductivity, but the niobium-3 tin does show superconductivity where there is tin diamer. So this is the ceramic superconductors. which made a big difference in 1987, which brought about 90 Kelvin. And these are the structures. This is 30K superconductor, which was 1986, for which the Nobel Prize was given. This is called the La2Cu O4 type of structure. You have copper O6 octahedra. In between, you have lanthanum. These octahedra are corner shared. So CuO6 octahedra are there. This is not superconducting. You add small amount of barium or strontium, it becomes superconducting. Why does it become? Because when you add small amount of barium and strontium, you add some extra holes in the system. So the superconductivity is caused because you change the copper oxidation state, which was divalent. Now small amount of copper trivalent is there, which causes some extra holes, which causes charge carriers, and it creates superconductivity. This is the 90K superconductor. This has copper CuO5 square pyramids and CuO4 square planes, and these square planes are supposed to cause superconductivity. This was given a Nobel Prize. Basically discovery of oxide superconductors was given a Nobel Prize to Bednorz and Muller in 1987. So now we know many copper superconductors. This is the 30 Kelvin. Then this is 90 Kelvin. The common thing is copper oxide planes are there in this as well as this. There are two planes of copper oxygen, and you can go to bismuth sulfur, bismuth strontium superconductors, where you have two such planes. Thallium barium superconductors, again two planes of copper oxygen. So these are the copper oxide based superconductors, which show 90 Kelvin, 105 Kelvin, 110 Kelvin. This was all the discovery between the period of 1986 to 1991. All this was known. In 5 years, a lot of work was done in the entire world. Moving along, so if you look at the history of superconductivity, found by Kamerlingh Onnes in mercury in 1911, then lot of metals and alloys till 1986, when this oxide superconductors were formed, and then between 86 to say 1993, 95, lot of oxide superconductors. The transition temperature on the y-axis you can see is increasing, and the maximum was till 2008 around 164 Kelvin at high pressure. But in 2008, new materials were discovered. These were based on arsenide based on superconductors. Arsenic is an element in the periodic table which we teach in class as the pnictides. In class, we teach the oxygen group as chalcogenides and the nitrogen group as pnictides. So nitrogen, phosphorus, arsenic is the pnictogen family. Okay, so antimony is also there. So bismuth is also there. So these are pnictides. So chalcogenides and pnictides became famous after 2008. And that is what is the current research I'm talking. So we did also a lot of work on this lanthanum, oxygen, iron, arsenide based on superconductors, which were found around 2006-7. Not much was known at that time. Then around 2008, 26 Kelvin superconductor was found in fluorine doped sample of this. Here also you see, instead of copper oxygen planes, now you have iron arsenic tetrahedra. So in superconductors, you have to be good at structures. And we all understand three-dimensional structures very well. You are all students, you know. The world is very, very advanced in solving structures. I can solve this structure in 1 hour if I grow a crystal. And these are not very difficult to grow. And with modern machines and modern software, these structures can be solved in 1 or 2 hours. And this was superconductivity. We made a lot of superconductors in this. So you see, you can use the superconductor based on lanthanum, but I can use entire rare earths. Instead of lanthanum, I can use dysprosium, terbium, gadolinium, samarium, neodymium, residuum. And you see we plotted how the transition temperature changes for the same series of compounds just by changing the rare earth. And there is a theory that how the TC changes is based on the ionic radius of the rare earth. Okay, and this we have published in 2010, 11, lot of papers we published in this area. Something similar we published in 95 on transition temperature varying with ionic radii in the 90K superconductors. This was published in 95 or something. Now we did similar thing in 2010, 11 on these oxynictides, and we showed similar behavior of these things. So these are all the papers we worked in the recent 2008 to 13 on how these iron-based superconductors, you know, why we are writing iron-based superconductors, why we are emphasizing on iron, because for nearly 80 years, people thought iron or such metals which have unpaired electrons do not give superconductivity. Now we see for the first time iron-based superconductors. In earlier days, in 60s, 70s, the world was working and there was a theory that magnetism destroys superconductivity and all things like iron, cobalt, nickel destroy superconductivity. Now we are showing that iron also has superconductivity. Iron-based compounds can give rise to superconductivity. That is why this title, iron-based superconductivity, we have a review article on this in 2011 in Chemical Society Reviews, where we have talked about all these structures. You see so nice, beautiful structures. And these structures have some common thing. See, all of them have this band of layer. I have put a band and they are colored in the same. They all have iron and arsenic. The structures are different and we call them by names like 1111. If you work in this field, you will know what I mean by 1111. Actually, one layer lanthanum, one of oxygen, one of iron and one of arsenic. Here there are 1, 2, 2. One layer of barium, 2 irons, 2 arsenic. And then we do a lot of design. We design new structures. Sometimes we combine a 1, 1, 1, 1 layer with a 1, 2, 2 layer and come up with a new structure. This is like making a building with bricks. What are our bricks? The layers are our bricks. And we try to put bricks on top of each other, but nature always does not allow you to put some bricks on top. So you will not get new compounds always. You may design, you may put one brick of 1, 1, 1, 1 on top of 1, 2, 2. You may get a new structure. You have to work hard to get those crystals. Sometimes you will get, sometimes you will not get. But these are our design elements. Like an architect designs a building, a chemist designs a structure, knowing by fundamental concepts of these layers. So what are our layers? We have a layer of iron arsenic tetrahedra, and then we have another layer of A atoms, which may be barium or lanthanum, etc. So this is one new compound we made at that time, just a simple one I wanted to show, a new 1, 1, 1. So what is 1 here? It is copper. What is the other layer? That is iron arsenide, which is a tetrahedra. So we made a new compound and we showed its structure, etc. But it is not superconducting. And we measured its magnetic properties, etc. Now, and we compared that why it is not superconducting. Then you have to go into details. We measured the bond distances, etc. And we showed that to make it superconducting, the height, the bond distance, you know, from the iron to the arsenic has to be small. Then it becomes superconducting. If it is large, like in our compound, copper, iron, 1.74 angstrom, it is not superconducting. And we explain through these bond distances. And bond distances come from overlap of orbitals. What is the basis of conductivity? The basis of conductivity for a chemist explain through overlap of orbitals. Physicists explain through bands. But the bands come from overlap of orbitals. If you have good overlap, you have high bandwidth. So chemists and physics, the language is slightly different, but we can explain if you understand the basics of orbitals, orbital overlap, bands, band structure, etc. These are all the materials now you see. I'm now in the period 2015. A new material was discovered with chalcogens, LaOBIS2, 2015. So I'm showing you how the history of superconductivity moved in one lecture in half an hour. I've told you from Kamerlingh-Onnes how we have come to 2015, LaOBIS2, on which we have worked and related materials in the last 5-7 years. So this is now a new series of compound which the world is working after 2012. See, science is not static. What Kamerlingh-Onnes did was now in textbooks everywhere. But research scientists have to do every day new things. So science is dynamic. So even 2012, new materials were found. And what is there? Instead of copper oxygen layers I was talking, now you can see bismuth sulfur layers. Very similar to that compound of copper oxide. So if you understand, if you do a PhD in copper oxide superconductors, you will easily understand bismuth sulfur superconductors. The structures are very similar. You have square pyramids of bismuth and sulfur, and there is bonding, there is conductivity in these layers, which causes superconductivity. So these are some of the compounds which we studied. This is another way of showing this compound, which was related to a 2012 compound discovered in Japan. And then a lot of work has been done on these type of compounds later. So I show you the common point. This is bismuth sulfur. This is copper oxygen, which I was showing. These are the 90s compounds. These are 2012, 15. So 20 years apart. You have to understand what is common in these and then build and understand these structures. Okay. So based on that, now there is new chemistry. Earlier we were talking of copper oxygen overlap, DP overlap of copper 3d orbitals with oxygen 2p orbitals. Now we are talking of bismuth 6p orbitals and there are 3p orbitals of sulfur. Okay, this is the chemistry of it. How these overlap cause conductivity. Won't go in detail. Now I'll give you examples. This was one of our first papers in this area on this BIS2, in which we showed a new samarium-based compound with grew single crystals. These are how the crystals look like. And then we measured the properties. Of course, they are not superconducting, the samarium compound. But what we did, we doped some electrons or holes. So how do we do that? You have to add something, like we added lanthanum. So if you add lanthanum in samarium site, what it does a pressure effect. It gives you a chemical pressure, an inbuilt pressure. Based on that, the superconductivity is seen. So this becomes superconducting at 4 to 5 Kelvin if you add lanthanum in samarium sites. Pure samarium is not superconducting. So how do we know that? We measure the resistance. You see the resistance goes to 0. And if you apply pressure, the superconducting transition temperature changes. So when high pressure, atoms come together closer in the lattice. When atoms come closer, orbitals overlap better and that superconducting transition improves. Okay. So we also do other things, other papers we have measured in these compounds, similar things with lead, etc. And using high pressure, we show how the superconducting transition changes. Okay, I will not go there. Go to a new compound, europium fluorine BIS2. Now, europium fluorine BIS2 is a superconductor at very low temperatures. You see the layers. What is important is all these superconducting materials have BIS2 kind of layers, and this is superconducting at 0.3 Kelvin. What we did, we applied high pressure. When you apply high pressure, the transition temperature goes up to 10 Kelvin. This is the work of Gohil, who is right now in Max Planck. He's doing his postdoctoral work. And Ziba is an assistant professor now in Jamia. So this is that work where we published in 2015. Put high pressure on this EUF BIS2 and you get enhanced transition temperature. So you can see this is a plot the black one not superconducting, and you keep applying the pressure. As you apply pressure, the superconducting transition comes, the resistance start falling, but it's not going to zero here. In this case, it goes to zero. So more the pressure, it goes to zero. GPa means gigapascal. So how much pressure are you applying, etc. So in this compound, we show that by Mosbar and other studies, we have shown that you get mixed valence. So it's all chemistry. Whenever what was happening, EuBFBIS2 is not superconducting because it does not have mixed valence. As you are adding the pressure, it creates mixed valency. Mixed valency creates charge carriers. It is called electron self-doping of electrons. Okay, the mixed valency means EU2 plus EU3 plus exists, and this mixed valency creates superconductivity. How did we show mixed valency? We did solid state NMR to show that these, what are the oxidation states of europium and bismuth. So today you have lots of techniques. We can do solution NMR easily, but solid state NMR needs a little different probe, but it can be done in many labs in India as well as abroad. But some of the work we collaborated in Japan on high pressure, etc., and NMR. So this is Mosbar studies. As you see, Mosbar is a technique by which you can find out oxidation states. So as you see, U3 plus has an isomer shift at near zero. So if you have studied what is Mosbar spectroscopy, is a different kind of spectroscopy, not available in everywhere. It's a gamma ray spectroscopy. It's nuclear transitions, what you observe, and it gives, you can explain that here is europium 2 plus and this is europium 3 plus. The europium 3 plus component increases as a function of temperature. Lower the temperature, this component increases. So you can explain valence fluctuations. This is from NMR, and from NMR also you can explain the valence fluctuation. This is called the Koringa effect. This linear plot, which is shown by the 209 bismuth NMR. As you go along, linear plot in an NMR signal shows metallic character. So the metallic character in bismuth layers shows that is the conducting layers. That's what I told you in the BIS2 layers is conducting layers. So the superconductivity in this structure is in these layers and not in these layers. And how did we prove? By using solid state NMR. You can use other techniques also. This is another structure, more beautiful structure of crystal chemistry. How from this structure you build this structure from common chemistry. If you understand solid state chemistry, what are we doing? In our mind, we decided to add a layer of EuF2. When you add a layer of EuF2, this compound should form, and it forms, and it was published. And there are two sites of europium, and what we did, we knew that one of the sites has to be 2 plus. So which is an ion? How do we prove it? Put a 2 divalent ion like strontium. All of us know strontium will never be 3 plus. It will be 2 plus. And we showed that strontium 2 plus goes in only this site and not in this site. And we do crystal structures and find the structure, and we show all that. And this was our paper in Inorganic Chemistry in 2017, where you show these kind of structures. So we did a lot of work, again, Mosbar explaining these things because time is very less. I'm going to close now in 2 minutes. XPS, Mosbar, it's all that in these kind of compounds. I'll go to the conclusion. So conclusion in these kind of materials, very new materials we published, showed superconductivity in this bismuth sulfur layers. High pressure is important to get higher TCs. You can show the mechanism because of valence fluctuation between europium 2 plus and 3 plus. Valence fluctuation in some cases is due to doping from outside, or sometimes by self-doping when you apply pressure. Okay. And these are other materials we made, some more materials. Again, what we are doing as chemists, crystal chemistry, we put selenium in sulfur site, knowing very well that there are only some sites where selenium can go. and we could make new materials and show by crystallography that which site does selenium occupy. We showed only one, because there are two sulfur sites, but only one site selenium will occupy. And we show that, and this was published in 2016. Very interesting property, first time published, where you can see a ferromagnetic signal along with a diamagnetic signal. This kind of plot you will never see in a book in superconductivity. So we published this in scientific reports in 2016. I don't have much time. There's a lot of chemistry and physics, solid state chemistry and physics, XPS, understanding XPS, mod square, solid state NMR, to prove these kind of theories, which, for example, was known earlier days in this compound, etc., which is called metallic ferromagnet. Very unusual term. This is very hot topic in physics, metallic ferromagnets, okay? Normally ferromagnets should be insulating, but metallic ferromagnets are today known. So I will not talk about that, etc. So I will stop here now and close. I have only 2 minutes to leave. I have another meeting to go. So I will, if you want, you can ask me 1 or 2 questions.
Oh, one. Okay. Professor Ganguly, very interesting talk. We have Bhavishya. Can you unmute and ask?
Sunny, can you unmute all of them so that they can ask the question?
I just show some of my students.
Bhavishya.
Sir.
Bhavishya, yeah, please ask her. Unmute.
Sir, is it audible, sir?
Okay.
Sir, I have a doubt that how to stabilize this copper or nickel in higher oxidation state.
Yeah, so normally in solid state, copper tries to be in divalent state, okay, and nickel also divalent. But in the solid, you have to see if you can add a metal which gives more electrons or less electrons. And then this transition metal, because it has possibility of variable valency, if the ability of the other metal is such that that releases more electrons, then what will happen? This metal will get suppressed and it may exist in the lower oxidation state. To put in higher oxidation state, you have to put in some metal which does not give that many electrons. So this metal will have to be forced to give more electrons. Okay, so nickel 2+ going to 3+, okay, it will be happening along with a metal. Say it was forming a compound with barium. So barium nickel is forming a compound. Now instead of barium, you add something like potassium. So half of barium you change to potassium. So what happens? Barium is divalent, but now you are adding potassium, which is only monovalent. To balance the charge, nickel will change its oxidation state. Chances are it will change its oxidation state, right? So that is how solid state chemists work. They try to work on the structure and try to dope something in the other metals which are present, or I can dope in the oxygen. Suppose I have a compound of barium, nickel, and oxygen. If I change oxygen with fluorine, that means I've changed the oxidation state. Then the metal will try to change its, it will try to accommodate that. Okay. So I have to stop now and I have to leave. I have been called for the meeting. So thank you, everybody. Okay, bye-bye. In some other time, I will answer your question.
Professor Ganguly, thank you very much for your very interesting talk.
Yeah.
We understand your difficult time limits, sir. Anyway, we, on behalf of RNCMT, we thank you. I request all of you unmute and give a big you may post that and we can communicate through email, sir. I understand. Because of his limited time, he has to go for another meeting. Thank you once again, sir. So we have end of second session, keynote lectures. Now next session will be Professor Sambat sir. He already joined. Nimisha.
Yes, sir. So we are moving on to the technical session 3. It will be chaired by Dr. M. Bhaglishmi. She has served as an assistant professor in various institutes like CU Tamil Nadu, University College of Engineering and Anna University. She has been a recipient of a DST Young Scientist Award in 2013 and has published more than 24 national and international research articles in peer-reviewed journals. She is specialized in material chemistry, photosynthesis of materials for carbon dioxide capture, electrochemistry of carbon dioxide reduction, energy storage, and fuel cell applications. Currently, she is working as an assistant professor in Department of Chemistry, CU Kerala. I welcome her for chairing the technical session 3.
Thank you, Nimisha. I welcome you all for this technical session 3. I am very much grateful to introduce the next speaker, Professor S. Sampath sir, from Department of Inorganic and Physical Chemistry, IISc Bangalore. So to talk about Professor Sampath sir, he is involved in research on interfacial properties of materials and surfaces, and he has done extensive work on development of supercapacitors, nano bimetallic materials, and he has studied all the applications. And not only that, he is also involved in doing research in transition metal nitrides, carbides, and chalcogenides, organic thin films, graphites, graphene oxides, nanostructured materials, and some organic electrode materials. These are all the things which I got from the his web page. And he is very interesting thing about our professor is like he is a elected fellow of Indian Academy of Sciences and Indian National Science Academy. And he has also received the bronze medal of Chemical Research Society of India in 2005. And he has also received one of the highest Indian Science Award from Council of Scientific and Industrial Research in 2006, that is Shanti Swarup Bhatnagar Prize for Science and Technology under Chemical Sciences in 2006. Not only that, he is also a recipient of CNR Rao Award for Nanoscience in 2018. For his credit, he has published more than 250 research articles, journal articles in a peer-reviewed journals, and he has about 4 granted patents and several book chapters, several research projects from DST, GE, and many other funding agencies. Very interestingly, to talk about his one of his 1,000. Somebody has unmuted. Okay, so more than 1,000 citations. You can see that his
Sunny, can you unmute everybody and give the cost permission to Professor Sampath sir?
So to talk about this, his research findings are excellent. I think we can have a very good refreshment on solid state chemistry from our Professor S. Sampath sir. Sir, over to you, sir. Thank you very much, sir.
Morning. Thank you very much. You all hear me?
Yeah.
Yes, sir.
Yes, sir. We can hear
you. You can see my screen as well, right?
Yes, sir. Yes, sir.
Yes.
I have difficulty in sharing my video. It doesn't come on. Otherwise, I would like to keep the video on. But anyway, you're able to see my screen and you're able to hear me. So let me just start. Okay?
Sure.
All right. Thank you very much and good morning to all of you again. It's indeed a pleasure to be a part of this particular meeting, which is titled Recent Advances in Solid State Chemistry and Allied Sciences, organized by the Central University. Let me acknowledge and thank the organizers, particularly Dr. Shaktivel, for this invitation to be part of this meeting. What I would do in the next 45 minutes or so is to give you a glimpse of solid state electrolytes, which is coming up in a big way in recent times, particularly with respect to energy storage and batteries. As you know, when I talk of electrolytes, everything related to solution and salt is what comes to one's mind. But can I have a solid electrolyte? Can I have a solid which is conducting? Can I have a piece of paper which is conducting, for example? And that's very important. Why is it important? And I'll take you through a lot of basics, fundamentals. In fact, this particular meeting, as I understand, is attended by lots of MSc students and research scholars. So what I have is about 30-35 minutes is quite pedagogical. So I would just talk about fundamentals, basics, in this particular area, and then go on to certain applications and then talk about certain materials, both from the literature and also from our own work on what is it that we talk about as solid electrolytes and how it can actually help. Okay, so the way I'm just going to go about is what's given here. There's a plan. So I'll give you an introduction, go on to certain history related to solid electrolytes. Solid electrolytes actually has been in the literature for a very, very long time, since the time of Michael Faraday. And it was indeed being looked at for a long time and sporadically, time and again. But then of late, in the last 10, 15 years or so, there's a lot of interest in this particular area. I would talk about the conduction mechanism, which is different from what you see in a liquid-based system, classification and certain applications, and references are very, very important. So if you want to really understand any of them, one needs to look at some basic textbooks. I've just given you two of them. I'm sure you're aware of both these books, one by J. Gopalakrishnan and C.N.R. Rao, and the other one is by West. These two books actually give you plenty of information on solid electrolytes. And I've also given you one particular paper, which talks about, it's more like a review article. It's about 18 pages, where it talks about material development of fast ion conductors, which otherwise people call it super ion conductors or fast ion conductors, solid electrolyte. Quite, they're all synonyms in some sense. Let's get to the introduction part of it. When you talk of electrolyte, typically, what comes to one's mind is something that actually gives rise to species that conducts. Let's take something like sodium chloride. If I put sodium chloride in water, it ionizes and I have sodium ions and chloride ions. And these are the ions that actually give you conduction. But then if I take a metal, it's not these ions, but they're going to be electrons that actually conduct. If I take pure water, does it have conductivity? If I'm just talking to you straight, I would have just waited and then asked you guys as to answer me. But then now I can't do that. So pure water, if you take, you still have protons and hydroxyl groups, dissociated ions, but they are very, very small in number. If you're aware of your bachelor's chemistry or even high school chemistry, you have what we call as dissociation constant of water. They are 25 degrees Celsius, you have 10 power minus 14, which tells you about 10 power minus 7 molar of H plus and 10 power minus 7 molar of OH minus. Too small a concentration for the ions to give sufficient conductivity. So if I take sodium chloride and put it in water, it gives you ions and it conducts. I put more sodium chloride, it conducts more because it dissociates and you have more concentration of sodium plus and Cl minus. I just go on adding. Sodium chloride, actually, the salt that we use for cooking, is soluble in water to the extent of about 18 molar. So I just go on adding sodium chloride until I saturate the solution. If I try looking at the conductivity doesn't go on increasing. It goes through a maximum and then it comes down. It increases and it comes down. You still have a solution. It is not saturated. It is still going into the solvent. But the conductivity still decreases beyond a point. Why does it decrease? It's because as you go on increasing the concentration, you have more and more of these ions getting into the solution and they cannot be independent of each other. It's like in a small room, you have 5 people who can be independent of each other, particularly now when we have to have all the social distancing. And if we have 50 people in the same room, we cannot be independent of each other. We need to bump into each other. Like that, the ions also start to kind of collide and then start to become ion pairs and aggregates. So instead of having one Na plus and one Cl minus, you'll have 2 Na plus and 1 Cl minus going together. Essentially, you have only 1 plus. If I have 1 Na plus and 1 Cl minus going together as a pair, the charge on that is 0. So they don't really contribute to conductivity, and that's the reason why the conductivity comes down when you increase the concentration of sodium chloride in water. By the way, if you know about Dead Sea, which is basically between Israel and Jordan, which separates Israel and Jordan, it's not really a sea, it's a huge lake. I've been there. You jump into that, you can't commit suicide because you start floating. That's because it has a huge concentration of salt. So a very high concentration of salt, which makes it highly viscous, and the density is much higher than the human density. So we literally start floating on it. So conductivity, if you try looking at it, conductivity is not really much, even though the concentration of the salt is very high. All right. So when it comes to this kind of electrolytes, one can think of liquid and molten, as you see, but then you also have solid and polymer. Most of the talk, I'm just going to stick to the solid electrolytes, and then towards the end, I'll just talk about polymer electrolytes. Both of them get classified as solid electrolytes in recent time. So what I have actually given here is the kind of properties that you need to have for any of these electrolytes. Any electrolyte that you would like to have, you need to have a high conductivity if you want to use it. So you have a battery, for example, you have 2 electrodes and you have a separator which has an electrolyte. And that electrolyte is the one that plays a role in terms of the redox species moving either towards anode or towards cathode, these 2 electrodes. So there are various advantages that are given here. I'm not going to read out all this. You will be able to read what's written there. So you need to have a fairly high ionic conductivity that one should have. If you look at ionic and electronic conductivity, metals have a fairly high range of conductivity. But then you try looking at the conductivity in solution. For example, sodium chloride. If you try looking at the sodium chloride conductivity, what you see here on the right is the solution ionic conductivity as a function of sodium chloride concentration. Look at it, it's about 10 power 1, it's 10 mole. And the conductivity is still about 100, a little more than 100, few hundred Siemens percent. So not really very high. When it comes to metals, the solution conductivity is not really high. But then is that enough to use? Yes, it is enough. Even if you have something like 10 power minus 3, which I have given a solid electrolyte conductivity range, and that's quite sufficient in order to carry out any of these processes and develop applications based on that. This is what I just gave you a while ago. So you also have mixed ion conductors, a material which can have electronic conductivity and ionic conductivity. And that's very, very interesting. And is it possible to separate them out? It's possible to separate them out and then use both in some sense. So these are electrolytes that are used quite heavily in energy storage devices, particularly in batteries these days, and in sensors and many other applications. What is the motivation to look at all solid state batteries? All solid state batteries is because what you see here is on the left bottom, you see a plane where there's a lot of smoke and the laptop that's actually in fire. And that's all implicated to batteries where you start to see the fire. And very often, because of the liquid electrolyte, you see some buildup of pressure as you go on charging and discharging. You can possibly feel that when you charge and discharge, particularly your phone as well as the laptop, you will start to feel that it's getting hot. And that's okay up to a point, but beyond a point, you will start to have this kind of issues. And they are all implicated to batteries and very often to the electrolyte, liquid electrolyte. And very often these liquid electrolytes are organic based and they can easily catch fire. And that's one motivation as to why people start to look at solid electrolytes. So when you have a solid electrolyte, that problem can definitely be solved. But then nothing comes for free in this world. I mean, like you can solve one problem, but then you just have to really look at many other issues before you start using it in the actual device. So people have been actually looking at solid electrolyte for quite some time. Let's just look at the history. I mean, I'm just going to give you some history and then possibly go back to introduction a little bit. As I mentioned to you, solid electrolytes have been there for a very, very long time. As you see here, Faraday, 1838, started talking about silver sulfide and lead fluoride as conductors of electricity. As you see here, lots of developments that have happened time and again at different stages. And there is a transference number measurements that's mentioned just below that, which is very important if one wants to appreciate anything to do with electrolyte. And that is related to the current carrying capacity of the ions. If I take, for example, a salt containing lithium and an anion, say lithium perchlorate or lithium nitrate, if I put it in water, it is not that both lithium plus and nitrate, NO3 minus, conduct current at the same rate. So the possibility of lithium plus conducting more is high. One would want to have something like that if I want to develop a lithium battery based on this electrolyte. So this becomes an important parameter, the transference number. You see Nernst, sometime in 1900, it has stabilized zirconia, which is quite well used in fuel cells, and then several other things as you hear. Everton Wagner, 1957. It's an important name. If one really is interested, just try looking for the papers by Wagner. He is the person who started looking at how one can address and understand the current carrying capacity of ions and solid electrolytes. And you go to further down, you have several of them. I have just given sodium beta alumina. Below that, you have these two little dots. And then more recently, not very recent, but then in 70s, 80s, Goodenough and Hong, they actually started talking about certain new class of solid electrolytes, Nasicon, Lysicon, sodium superion conductors, and lithium superion conductors. These are all solids, but then they conduct. The conductivity is mainly due to either sodium ions or lithium ions. And they do have certain structures which are pretty conducive for this kind of a movement. I'll tell you about the conduction mechanism. At that point, you'll be able to appreciate what it is. So there are different classes of materials, as you see. It could just be ceramic, oxides, for example, sulfide polymers, glass, many different things. I mean, like, what you see on the left is a graph wherein you have different classes of materials, and then put a little star there, and that star is the one that we have been actually working on, and that's why that star is. So the material that we work on actually gets classified at that particular point. And I've also given another composition just there, lithium lanthanum zirconium oxide, and that's one of the most recently studied solid electrolyte, particularly for lithium batteries. I shall give you some data and also results based on that as we go on. Essentially, when we look at solid electrolytes, you need to have good conductivity and good electrochemical stability, and of course, mechanical compatibility and transport of ions in the interface. And the last one, which is written in small fonts, is the most important thing. If you have a liquid and then put, say, something like a metal inside the liquid, there is hardly any interfacial resistance. Liquid completely wets the solid, and you hardly have any interface. But the moment you replace the liquid with a solid, you have a metal and a solid, and they don't really get in contact with each other nicely. So you have interfacial problems, interfacial resistances associated with this kind of devices. And that's one of the major issues in using solid electrolytes, particularly for battery purposes. This is the expansion of what I had just shown you in the last slide. You have different classes of materials, and this is basically the conductivity 1/T Arrhenius type of plot, which tells you about the conductivity as a function of temperature. Don't bother too much about what kind of materials we are talking about and how the conductivity. What you need to take home from this slide is that there are different classes of materials. It could be sulfides, it could be oxides, it could be other kinds of materials which are available in the literature, and they also have certain disadvantages associated with that. If people have all the conductivity that's already solved, and we would have batteries with solid electrolytes in the market, but it is not. But they all come with certain issues as well. What I would like you to appreciate is that you have different classes of materials that are possible to kind of look at in terms of solid, in terms of conduction. Again, coming back to a bit of introduction in terms of ionic conductivity, and they should have a low electronic conductivity. That's how we can use it as an electrolyte. If you want to use it between two electrodes, it should not have a high electronic conductivity. So you have a few other aspects that is actually talked about. So again, the graph that I just mentioned is written in the form of a table. You have different oxides, sulfides, hydrides, halides, then polymers and things like that. Look at the conductivity. It actually varies. Sulfide 10⁻⁷ to 10⁻³ centimeter per centimeter. So these are all at certain temperature. So we also have Nasicon, Lysicon, and a few other classes of materials. Anytime we talk of this kind of solid electrolytes, if you want to use it in, say, a device, you try to look at the performance, and there are performance matrices. And this is called the radar plot. If anybody is working in the area of batteries, particularly lithium batteries, he or she would have definitely come across this particular thing. It looks like a spider web, but then what you see here is you have different properties that are given. If you take, for example, sulfide, take the B, ion selectivity, reduction ability, oxidation ability, chemical stability, thermal, mechanical, processing cost, device integration, and then the series resistance, electronic as well as ion. We just see that in certain cases, if you look at the chemical stability, it is actually lower. It's pretty small. It should actually be much higher, but then it's small. On the contrary, if you take up the chemical stability of oxide, that's higher than what we have for the sulfur, but still that is not there yet. Oxidation stability is pretty high, ion selectivity is pretty high for oxide. Look at hydride, it has certain properties which are advantageous, certain other properties that are not so advantageous. You also see F, which is polymer. I will talk about polymer towards the end, polymer electrolytes. Coming up in a big way, essentially people try to kind of have salt in a polymer matrix and then try to use that as an electrolyte. And these polymers are soft materials. They're not really hard. They are kind of still prone to certain fire hazard, but they're not like lipid, organic solvent-based systems. So when we talk of any of these solid electrolytes, we can think of different parameters that actually comes to one's mind. And that is what is important to appreciate if this is going to be a good material. I'm just going to give you a little more information on this, and particularly one material. I have written lithium lanthanum zirconium oxide, LLZO, Li7, Li3, ZR2O12. And there is some Indian connect to this particular material. This has actually been proposed and then worked on by Indians. I mean, like there's a faculty member at Canada, Dr. Tangadurai, and then there's one Dr. Murugan at Pondicherry. They have been actually working on this, and they are pioneers in this particular area. And this LLZO is a material that is coming up in a big way in terms of polymer solid, not polymer, solid electrolyte. Look at what I've given just above. Lithium, LLTO, LLZO. Lithium is lithium superion conductor having a conductive lithium power -4. The LLTO, which is lithium lanthanum titanium oxide, has 10 power -4. And LLZO, which I just mentioned, is about 10 power -3. Came in about 2007, and people have been very thrilled about it and working on it in a big way. I look at the structure of it, and they all have garnet type of structure. This LLZO actually has two structural polymorphs, and there is a low temperature tetragonal modification, which has a completely ordered arrangement, and then there is another modification, which is cubic, and the cubic one is much better than the tetragonal modification. And these are all based on garnet type structures, garnet related frameworks. Okay. Just go a little further. The ion conduction mechanism, I'm going to talk about it in detail, but what I would like you to take home from this particular slide is look at the activation energy. I talked about LLZO, but LLZO, you can have conduction mechanism in different ways, which gives you activation energy that is different. In one particular case, the activation energy is 0.8 eV. In the other case, it is 0.26 eV. So this is the activation energy for the lithium ion movement. Mind you, when it is in a solid, in a crystal, in a lattice, this ion, which is charged, has to actually push through its way to another site. So there has to be a vacant site, so it hops. When it hops, it's not free. It's not in an open space where it can just hop the way it wants. It actually pushes or moves through other ions. So you do have Coulombic repulsion, Coulombic attraction that comes in addition to the size of the ion that we talk about. So solid state conduction, ionic conduction, is not as simple as what you would have in a liquid. I'll talk about that. So essentially, again, all the classes that you have and different types, and then I've given some examples of this polymers I'll talk about later, lithium perchlorate and polyethylene oxide. And then we need to actually look at all this, the oxide-based electrolyte stability. Some are stable and some are not so stable, and the ionic conductivity and things like that. This is actually related to the plot that I just mentioned earlier. As you see here, again, the history is given in terms of vertical thing. You have Faraday, and you see the Tangadurai is there somewhere in 2003. Garnet type lithium ion conduction, and that's actually coming up in a big way. Just below that, you see wooden Nasicon. And on the right, what you see is the structure of LLZO. And LLZO, lithium lanthanum zirconium oxide, has other modifications. People dope it with, say, tantalum, LLZTU. That has certain advantages in terms of conductivity, in terms of stability, and also the interfacial resistance. Also, given the cubic and the tetragonal form, cubic has a structure wherein, the more open structure, wherein you'll be able to have the lithium movement much faster than in the tetragonal case. Let's look at the conduction mechanism. Conduction mechanism is something which is very, very important. And if you go through this particular paper, Journal of Chemical Sciences, which is published by the Indian Academy of Sciences, a colleague of mine from another department has written this review. It's a fantastic review. You guys should go through this and then understand. So whatever I have taken is all from that particular review. So essentially, you need to have good ions. I mean, first of all, the concentration of ions that you should have in a solid should be high. And if you take an ideal crystal, they're all nicely organized in a regular periodic fashion, and they're all in a closed packed form. Very little space for an ion to diffuse or move. By the way, transport of any of these things can happen by different mechanisms. It could be diffusion. There's a concentration gradient, for example. It could be migration with charged species under, say, electric field gradient. And it can also be convection. The convection doesn't hold good here in the solid phase, but then for a liquid, yes, you shake it and then you start to remove the ions. So we essentially talk about diffusion and also migration as far as the solids are concerned. Very often the available space is just enough for vibration around this equilibrium position, the ions in a lattice. It's very difficult to really kind of move around. But then for conduction, it has to move around. But then any finite temperature that we're talking about, you have defects that are existing. And they can be positional disorder due to deviation from ideal stack. So this essentially depends on doping, this depends on the way you prepare the material, this depends on temperature and whatnot. So the degree of disorder, if you actually look at, varies from one material to another. And when you change the temperature, it's going to change. And I just mentioned to you, these ions can actually vibrate. If there is a vacant spot, vacant site somewhere, it's possible for it to kind of move to that vacant site. Of course, there is an energy associated with that. The cost associated with that movement that comes either in the form of a thermal energy or in the form of an electrical energy. So when we talk of a conduction, ionic conduction, it is under electric field gradient. So there is an electric field that's available, which makes the ions actually move in the solid. Take zero temperature, free energy is dominated only by the potential energy. So you look at the arrangement of ions in a crystal at that temperature, the total energy system is the lowest. So you hardly see any movement, and even the vibrations are pretty low. And there is no vibration beyond a certain temperature at lower level. As the temperature increases, the contributions to free energy from entropy becomes important. It's a very, very important point, the entropy. The entropy is a measure of disorder. So that's the one that contributes as the temperature increases even within the lattice. So the origin of crystal defect is actually something to minimize the free energy, but then in turn increasing the entropy. So the entropy increase in a crystal is the one that's going to give rise to whatever I have just written here, kind of defects. I'm going to talk about only the point defects. I'm not talking about the line defects here, because most of what we are talking about in this particular case is all related to the point defects. Let me talk about the Schottky and the Frenkel defect. I've given excuse me, 1 minute. So there are two kinds of defects that we're talking about. One is the Schottky and the Frenkel. I've given two examples here. You see on the left, where I've given as NaCl, you have both of them have sites that are available, Na plus as well as Cl minus. Okay. But in the Frenkel defect, you just see only one site that I have, and that is important in some sense. So the Schottky defect actually refers to the crystal imperfection, where you have pair of ions disappears, leaving the position vacant. So these positions are available for the ions to kind of move. That's the Schottky defect. And if talking about the Frenkel defect, essentially one single ion missing from its position, and then it has to wander in the interstitial sites. So essentially, you will have one particular ion that is possible to kind of move in the solid. Interstitial sites can have different environments. The moment it goes to another interstitial site, you may have the neighbors being different, and the charge can be different. And if you look at the interstitial sites, they are not energetically very favorable. Again, the entropy actually comes, and the occupancy is driven by the entropy enhancement, as I just mentioned earlier. The entropy enhancement makes sure that the free energy comes down. Ion migration, if you really look at what exactly happens. So movement of Na plus in HCl. So it's a Schottky defect, and essentially you do have Na hops from one place to another, but when it actually hops, it's squeezed by chloride and other sodium ions. And that is a transition state that determines the ease of migration. And I have written E, and I have not given the x-axis here. So you just have, reaction coordinated. Look at it, I have given 2 minimum. So it has to go from one to another, and then there is an activation barrier for it to cross. And when it actually goes to the other energy barrier, goes through the barrier to the other energy state, it can either be at the same position or at a slightly higher or at a lower level, depending on the surroundings. And it doesn't have to actually hop, it can also kind of back hop. So it's not very easy. There is always a probability of back hopping. It just tries to kind of move towards the barrier, but then it comes back to its original position, which means there is no migration at all. So the sodium ions, if I talk about sodium chloride, that's to squeeze through the lattice, which induces a lot of local distortion, relaxation. So that limits the mobility of the ions. So see how difficult it will be to work with solid electrolytes. It's not like a liquid electrolyte where you can just put sodium chloride in water and then you have the Na plus and Cl minus, which are available freely moving around. That doesn't happen in a solid. So there's also a probability of back hopping. So one should actually work around to reduce this kind of back hopping events, make sure that there is a hopping which comes to picture in terms of increasing the conductivity. So this can happen by various ways. If you look at the Frenkel defect, the previous one is the Schottky and this Frenkel defect. The Frenkel defect, it goes from one interstitial site to another interstitial site. That's a direct interstitial jump. That's what's given here on the left top. So this Ag1 goes to Ag2. So it exactly goes from one place to another. If it happens, fantastic. But then there is an indirect phase as well. I mean, what you see at the bottom, the middle center part, Ag1, there is a blue arrow and then the red. It doesn't go from Ag1 to Ag2 straight, but then it comes through another site in between. That is the interstitial migration. So there is an interstitial jump and there is an interstitial migration wherein it goes to Ag2 in the red and then goes to Ag1. So this kind of interstitial mechanism, which is basically cooperative because they just have to cooperate. One has to go here and then this jumps. Okay? And this is observed in an ionic conductor like sodium. So these kind of electrolytes are pretty useful, as I already said, in batteries, fuels, and sensors and all that. Wherever you have a solid electrolyte and where is an ionic conduction that's required, it's possible to separate, we replace that with the liquid. Because the electrode may have ionic and electronic conductivity, that has to be needed to avoid what we call as an open circuit. If anybody is interested, I should talk about it more in detail, but we will not go into that at this stage. Now, anytime you have a solid electrolyte, I just mentioned to you, what I'm given here is Li and then LLZO. LLZO is the electrolyte, and that's supposed to conduct lithium ions. And then I have a lithium, and on the other side, it's a battery, for example. At the interface, you will not have a pretty nice, interaction wherein the interface will not be like what you will have in a metal solution, where it is completely wetted, the metal surface. Look at what I have given on the right, where I mentioned interfacial contact, insufficient interfacial contact. So if I have a solid and then try to put on another solid, it doesn't have to exactly get onto it, unless it is kind of an epitaxial film. So you have little gap here, and that is the interfacial contact which leads to resistance. And that also leads to what we call as dendritic growth and things like that, which happens in lithium batteries, and that is an issue. So on one side, we are able to solve probably the fire hazard related to the liquid, but then you introduce other problems related to the interfacial contact. On the other hand, you have grain boundaries, which are given on the left bottom, and then the existing defects in the solid, which also plays a role. All these things actually lead to what we call as a dendrite formation when we use it in a battery. The dendrite formation is nothing but when you discharge and charge. Essentially, when you discharge a battery and then charge a battery, let's talk about lithium battery. The lithium actually gets oxidized and goes into the electrolyte, and then during charging, it goes back onto the surface and then gets deposited. But then when it gets deposited during charging process, it doesn't deposit as a smooth film, but it deposits like a needle. What I have given on the right top, like a needle, it starts to do. And that is not okay. If the dendrites actually start to get formed, it will short the two electrodes after certain charge. And that's another cause for fire hazard and burning. So one needs to work around and then try to understand what they are. Let's look at the classification before we go on to certain applications. The classification, if you really look at, essentially you need to have defects. If you don't have these defects, ion transport cannot happen. So in a solid, you need to have defects. Very often they're point defects, I just mentioned to you. So you need to have the defect concentration. The defects per unit volume should actually be very high. And what does it depend on? That depends on the structure, temperature, and the dopant that you have, which we call as impurity ions. It should be writing impurity ions, it should be dopants, and the nature of bonding between the constituent ions. So if I just try looking at any of the classification, it is based on the type of defects and the disorder as well for the conduction. And that's how you classify. So you classify them into actually 3 of them. The type 1, where I have actually given ionic solid with low concentration of defects. So essentially you have only about 10 power 18 per centimeter cube as the defect concentration. So look at this. I mean, like, you do the diffraction pattern, you'll see a pretty nice pattern with a good intensity and all that. But then they all have defects. Unless they have defects, you will not be able to kind of have conduction associated. Second one, ionic solids with high concentration. High concentration is 10 power 20. A little more than what you see for the type 1 at room temperature. So they are pretty often fast ion conductors, stabilized zirconia, calcium fluoride. Now, these 2 types of ion conductors actually have the mechanism of conduction based on vacancy migration. I just mentioned to you about vacancy migration earlier, as opposed to the interstitial C mechanism. So essentially, these things have Schottky defect type of mechanism. But then you also have a type 3 type of conductor, which is sodium beta alumina and a few others as well. I have the defect concentration fairly high. It's about 10 power 23. It's very high. In fact, you look at the electron density in a metal, it'll be 10 power 23. So it's very, very high defect density that you have. So if you have a mobile ion, it's easy to kind of have good conductivity there. So one ion at least, if you take a compound, will be highly delocalized over the sites available, so the conductivity can happen fairly well. The free energy associated with these interstitial sites are pretty similar. And see, that is important. The difference in energy at the interfacial sites should not be varying too much. Otherwise, the conduction will not happen. So it is already at a low energy point. If it has to go to another point, which is at a fairly high energy, then it is not going to feel comfortable. So it will try to come back to the low energy state. And that's very, very essential. But that essentially depends on the dopant, that depends on the way you prepare the material and whatnot. Conduction mechanism in all these cases are mostly what we call as interstitial C migration, unlike the previous one. A little math before we go to the applications. So essentially, the factors that influence the conductivity, as I told you, is concentration of charge carriers, temperature, availability of the vacant sites, which are controlled by the density of defects. Essentially, the ease with which the ions jump from one site to another is what is actually looked at. Very often, these are all based on the Arrhenius type of behavior. So the conductivity, you know about this equation, you don't have to really explain. So you have the activation barrier, which is the Boltzmann constant at temperature, and then you have the pre-exponential factor associated with this. Now, if I look at the sigma, it is also related by this Nernst-Einstein relationship to the diffusion coefficient. You just see what's written on the top. Sigma is proportional to the diffusion coefficient. The diffusion coefficient can come into play when there is a difference in concentration. If there is a concentration gradient, you start to have diffusion. But then diffusion cannot happen just like that. Even though I have a concentration gradient, I have a way to kind of explain diffusion. It has to still pass through certain charge because there are other ions in its way. When it goes through those ions, they will actually start to screen the charge. So it's not very easy. Even though there is a possibility because of the concentration gradient being present, it's not going to be very easy. So you do have sigma related to D, and also this N and Q square. N is the number of ions per unit volume, Q is actually the charge. The D, if you try looking at, that's related to Z and C, within bracket 1 minus C, and then A square nu KB. So essentially, if you look at Z, this is actually the number of nearest neighbors, and C is the concentration of ions, and AI, what I'm talking about, is actually the distance between the sites, and that is very, very important. How far the sites are when one ion has to hop from one site to another to give you conduction. And of course, there is a frequency of jump. I told you, it has to be a positive event. But then if it is going to be a back hop, it is not going to be okay. So the frequency, jump frequency should be high, and the jump frequency is given by the last relationship that's given here, whereas nu equals nu zero exponential EA by kT, and the site frequency and the free energy barrier. So in all these cases, that put together, when you carry out an experiment, you get an activation energy which involves all this stuff. One possibly can find out the conductivity as a function of temperature and plot it in the Arrhenius plot, and then try to get the activation energy associated with that. This activation energy has all these components. So it is related to the jump frequency, it is related to the diffusion, it is related to ultimately the conductivity. So the density of mobile ions should be high, availability of vacant sites should be high, and the activation energy should actually be good. And what kind of ions do we see? I mean, like very often you see monovalent solid ion conductors. It could be lithium, it could be sodium, things like that. But then there are a few anions as well, oxide ion conductor and the fluoride ion conductor. And in this particular case, oxide ion conductors, one advantage is that the ionic radii is small and it's easy for it to move. And that's how you see this. So the multivalent ion conductor, for example, magnesium, for example, aluminum, they're not very easy. And for them to move in the crystal lattice. High valent ion, there's a lot of Coulombic attraction and repulsion, and that actually comes in the next 10 minutes or so. I'm just going to talk to you about the applications related to it with one particular material, LLZ2. Before I just go on to LLZ2, I'm just giving you a schematic of where you can have this kind of solid electrolyte. This is solid oxide fuel cell. I mean, fuel cell, as you all know, you have certain reactions on the anode side and the cathode side. And if it's related to hydrogen and oxygen, on the anode side, you have the hydrogen oxidation, and the cathode side, you have oxygen. So in between, you can have an electrolyte as a liquid or a solid. In this particular case, you have a solid oxide, which is basically the conduction of the oxide. And if you look at the lithium battery, I already mentioned to you, this is something which we all know, all of us use a mobile phone, and very often we have, I think all the mobile phones have lithium batteries. By the way, I just have to tell you one particular thing. When you buy a mobile phone, you put all the apps and everything is running fantastic, and you probably will have the battery charged, and the battery will come for about 2 days before you have to recharge. And it'll all be great. And after about 6 months, what will happen is you may have to charge the battery every day, if not every 2 days. After another 6 months, you may have to charge the battery every 10 hours. After another 6 months, you may have to charge the battery every 2 hours. Do you know why it happens? It's not so much because of the battery, but because of us. We abuse the battery. We abuse the battery in a way that we charge the battery at the point when we should not charge, and we discharge the battery up to a point where we should not discharge. We always wait for the charge to be completely going down. Oh, there is the single line. Oh, it's come to 5%. Then I'll just put it in the plug. I plug it in the mains. And when I plug it in the mains, very often what I do is I just plug it in the mains when I go to bed, and I sleep. In the morning, I just get up. I'm happy that it's all 100%. I take it. That's very bad. I'm actually overcharging the battery. Many of these batteries, depending on the chemistry, of course, should be charged up to 95% and discharged up to 50%. So it has to be back and forth between 95 and 50, and that is it. But we take it all the way down to 5, and we don't keep it at 95. We take it to 100. Not only that, we take it to 100, we keep it for a long time in the night for it to charge. So there is something called state of charge in all these cases. It's just a piece of information. It doesn't have necessarily anything to do with solid electrolyte. So please be careful when you charge and discharge the battery. And these are all responsible for whatever we find in terms of fire hazard and the heating up and things like that. Now, coming back to what is there on the screen, you do have this lithium battery. In between, instead of a liquid, you just have a solid. That is all you have as far as the lithium battery is concerned with solid. I'm just going to go to one particular material and explain to you this material and then give you some additional data. What you're seeing here is actually lithium, lanthanum, zirconium, tantalum oxide. I talked about lithium, lanthanum, zirconium oxide, but then I just mentioned about tantalum doping as well. The moment you have a tantalum doping, things become much better, and particularly with respect to the temperature at which all these things are to be prepared. These are all to be prepared very high temperature. You see the preparation procedure that's given. And as I said, You have either a tetragonal or the cubic, and what you see here on the right is the cubic phase with the Rietveld refinement, pretty nicely formed cubic phase. But the thermodynamically stable one is actually the tetragonal phase. And the moment you have the tantalum in it, the cubic phase gets stabilized, and that's an advantage here. And you have a pretty nice cubic phase, and the cubic phase is the one which has a higher conductivity. Various ways of doing it, and then you just see the last one, a particular thing that we were actually working on at some point, which gives you a fairly good conductivity. And anytime you have any of these electrolytes, electrochemical stability is important. When I say electrochemical stability, we just use the battery in certain potential ranges. If you take lithium, lithium can actually go up to 3 volts. If you use lithium battery, say in an aqueous medium, not with metallic lithium, but with lithium-based compound, say in aqueous medium, you can't really take it all the way there because water will decompose. Water thermodynamic decomposition potential for water is 1.23. So with certain additional extra energy or potential, it will go up to say 1.4 or something like that. It will never go to say 3, even though the metal is capable of going up. So one needs to actually work around that. So these are all related to different electrolytes, which are given in terms of stability based on the electrochemical window that's available. I just mentioned to you about the interfaces. There are various ways of improving the interface. So if I try looking at the LLZO as the electrolyte, in presence of lithium is what I'm going to use. And in presence of lithium, the interfacial resistance has to be very high. There are various ways of doing it. You can just have a look at this particular reference where I've taken it from and understand how they go about. I mean, this is a review, but then these papers are all given in this review. And there are various ways of doing it. And we also try to kind of have an interface made in a particular way and reduce the resistance associated. That's the most important thing in getting the solid electrolyte in a device. As such, a solid electrolyte, you should have a good conductivity with a low activation energy. And second one is actually the interface. Some data that you see here. What you see on the right is all the electrolyte that are prepared in our laboratory. What you see here is a little thin sheets, pretty nicely conducting. And what you see on the other side is the center. What you see here is a pretty good stability window that we're talking about. It's the lithium deposition and then the dissolution. And that has to go on back and forth as much as possible. Because one understands the interfacial resistance is based on the impedance that are given on the left. And the actual stability is also looked at, electrochemical stability, in using what we call as a cyclic osmogram. You just see here in the osmogram that I've given at the right corner. So you see that it can go from 0 all the way to 6 volts. And what you see here as a large increase in current and the little spike, I mean the peak that you have, we understand what it is that's related to the lithium deposition and then the oxidation associated. These are all at different current densities, which are very, very important. These only tell you about the rate at which you can cycle the batteries. So with this kind of a solid electrolyte, if I use a battery, if I'm using it in a toy, for example, I need to have very little power. But when I'm just going to use it in an automobile, I need to have bursts of power. So the rate at which actually I discharge and charge will be different depending on the application. So one needs to actually look at how they discharge and charge at different current densities. That's what's here. And on the right, what you see is the electronic conductivity. I just mentioned to you earlier when we talked about certain fundamentals that the electronic conductivity actually should be low. And that indeed is low. And that's a very, very important point whenever you try to develop solid electrolyte. And whatever I just showed you is all some pellets. I mean, it's easy to have a die and a plunger and then make a pellet and try to use it. But then that's not what it is when you want to actually scale it up and then use it in big battery packs. You need to do what we call as a tape casting. What you see here is actually a nice little paper-like thing, which is done using what we call as a doctor blading technique. And you can have a very thin sheet. So literally, it's like a piece of paper. So you have a piece of paper that is conducting. And that is ionically conducting, which can be used in a battery. Lots of challenges. I told you the interface, and that I just want to kind of quickly go through this and then get on to other things. What you see in the middle, where I've written poor wettability, undesirable SCI, dendritic growth, and dendrite linkage. These are all processes that happen in a battery during discharge and charge. So if there is a poor wettability, you will have what we call as undesirable solid electrolyte interface that gets formed during charging and discharging. And that leads to dendritic growth, and then you have other issues that associated with this particular device. So the solid electrolytes are prone to some of them, so one needs to actually understand this. Okay, this is actually the full cell data. See, anytime you know the proof of putting it in eating it, you can just say that, okay, I have made this electrolyte, all that, but then you need to literally look at and then see whether it works in a cell. And that's what this one is. So you try to kind of make a cell and then do a discharge in the first cycle, 100 cycle, and then you would do a charge at certain voltage limits, and you get a capacity associated. In the next about 4 or 5 slides, quickly, I talk about gel polymer electrolyte before I just close it. Gel polymer electrolytes are different from solid electrolytes. As the name suggests, they do have a polymeric gel associated with them. So essentially, you have a polymer like polyethylene oxide, and you can have a polyethylene oxide itself. We can just buy from the market as a polymer. The powders, depending on the molecular mass. So you have it in a solvent. It goes into it at certain temperature. Along with that, you add a salt. So after that, you cast it on some glass slide or a petri dish and evaporate the solvent. So what happens? You form a nice thin film. It's still a polymer film, and it's a polymer film having the salt. And depending on the salt that you have, lithium perchlorate or lithium triplet, you will have conductivity associated with it. If it's going to be lithium triplet, you will have a nice lithium ion conductivity. But mind you, these are not like the solid electrolyte that I just talked about until now, which is all inorganic and they're all rock solid. And these are all soft material, that's what I'm talking about. But still, they are classified as solid electrolytes because they don't have the viscosity like that of the liquid. If I try looking at the solid, gel polymer electrolyte, you do have a schematic that's given here. You have all these cross-linking of the polymeric gel, and then you have the salt associated with the conducting material. This conduction mechanism is different from the conduction mechanism that you have in a solid. So this can very often be the polymer segmental motion, because the polymer at that finite temperature can actually have movement of these segments. And when they have segmental motion, these ions can hop from one segment to another. And of course, this kind of movement will also be dictated by the melting temperature or the glass transition temperature of the polymer. So that has to be a free volume in the polymer. So everything revolves around the polymer right now. So how the polymer characteristics are. So one can work with different polymers. I just mentioned about polyethylene oxide. It can be polymethyl methacrylate or polyacrylonitrile. I'll give you one set of data and then close this lecture. So this is a magnesium-based battery, which was some time ago introduced by this person by name Orbach. He's an Israeli scientist who's contributed immensely to this particular area of magnesium-based batteries. Next to lithium is magnesium in terms of the voltage and also energy density associated with the battery. But then it's not very easy to work with magnesium. Magnesium 2+, conductivity, and also particularly in solid, is not going to be very easy. And intercalation of magnesium 2+ in a host and then deintercalation is the most difficult thing. It will go into, see, if you take graphite and try to intercalate, it will go in, but then it will not come out at all, stays put as such. And that's true with many of the multivalent ions, and particularly with magnesium. There's a lot of work that's been happening in this particular area, and Doron Orbach is the pioneer in this particular. Well, this is some of our work that we did quite some time ago on the gel polymer electrolyte with magnesium triplet. What you see here, evident preparation of SP, it's a solid polymer electrolyte with magnesium triplet using polyethylene oxide. Now people work on it quite a bit. This is pretty old work that we did some time ago on magnesium. I thought I'd just give you some information on the gel polymer electrolyte as well. That's how I take it. So you do have a fairly good conductivity. With just the conductivity of the polymer alone is very small, and then when you have the magnesium perchlorate, conductivity actually. You try to kind of use this and then show a battery. As I said, anytime the proof of all this is to make sure that you have a battery and it works. So you have a magnesium metal and then corresponding cathode, which in this case is a manganese oxide, and try to use that as a you just see the cell voltage as a function of time. You just see that pretty nice plateau that you see here, which all can actually be explained based on the redox reactions that are given on the right. Because what you see as the ultramogram is the current voltage curve. which gives you information on the deposition of magnesium and the resolution of magnesium deposition. So this is one of the things that was done by a colleague of mine, where he developed a battery based on certain other polymers. So you see the charge and the discharge. Pretty nice charge and discharge with a pretty good capacity. The capacity information is not actually here. I'm almost coming to an end. I just have the last slide here. I'm not going to give you a big conclusion. All I'm saying is solid electrolytes, which have been there for a long time, have been having a resurgence, particularly in electrochemical storage. And after people started looking at, for example, the Boeing, I mean, I'm sure some of you would have at least read, or some of you would have even traveled. 787 Boeing, very often it flies from Bangalore to Delhi, one of the longest routes in India. Air India actually uses that flight. It is a double-decker flight. And when it was actually introduced in many places in Japan and also in the US and in Europe, they found that there was smoke when they were up in the air. And immediately they grounded all these flights and then tried looking. This is one of the very, very fancy aircrafts. I mean, you just go on and then you have a nice electrochromic window and all that. And as you go up, the color changes and not much of noise and things like that. And they found that it was the battery that was a problem. And of course, laptops and other things like mobile, I'm sure all of you have come across this kind of fire. So because of all that, solid electrolytes have been having a resurgence. And challenge is actually it's a very challenging problem to obtain good interface. It needs to actually reduce interfacial resistance. There's been a lot of work right now in the literature on lithium-based ones, but then multivalent things is still elusive. Plenty of scope if one wants to really get into this. And as I said, a lot of Indians have contributed to this, and we should take pride in that. Thank you very much, guys. And it's a pleasure talking to all of you. If you have any questions, please go ahead. Thank you very much.
Thank you very much, sir. I hope everyone would have enjoyed this session, because you have started from the basics. Like you just talked about what is electrolyte. From that, you just move on, and then you just very nicely you have transformed the subject towards the solid electrolytes. I think many of the people who are really interested in working in this electrolytes, solid electrolytes, especially this kind of lithium materials, they would have enjoyed this, I hope. Let us hear from the participants. Any participants, would you like to ask any questions to our professor?
Sunny, unmute everybody.
They're all probably hungry.
No, sir, I have enforced a force mute condition. Now, participants, you can unmute yourself.
Anybody like to ask a question? Hello?
Are you guys there, or you all have gone away for lunch?
No.
I think too early, sir. I think they are here, but
No, I'm on the lighter wing. Yeah, I'm sure they're all there. Come on, guys. You should at least ask one or two questions. Otherwise, I'll feel bad because, I've been talking for the last 15 minutes and
Let participant, please. Participant.
I see 158 numbers.
Yes, sir.
Nobody wants to say anything.
Hello, sir.
Yes. Yes.
Sir, I am Manor Jople from Maharashtra.
Yes.
I want to know, lithium is bind with some polymeric material, but if I will use the lithium with copper and nickel, then it is possible to any form new material or other.
It depends on what one would want to do. See, if I talked about electrolytes. In the electrolyte, you need to have conductivity. Anytime you need to have a battery, for example, in the outer circuit, we take the current which is through electrons, and within the electrolyte, you have ions that complete the circuit. The ions that should conduct is something that you decide a priori. For example, if you want to work with lithium batteries, you want a lithium ion conducting electrolyte. If you want to work with magnesium batteries, you want to work with magnesium ion conducting electrolyte. Aluminum batteries, you want aluminum ion conducting electrolyte. Like that, you predetermine what is the conductivity that I should have in the electrolyte. What is it that should be due? You may or may not achieve immediately. As I mentioned, that magnesium and aluminum are not easy to do. Now, coming to your question of, can I just add copper? Can I just add another element or the compound to it? Yes, people have been having this kind of idea in terms of increasing the conductivity of lithium itself by adding another salt. But it may not be the conducting ion per se. It might possibly increase the conductivity of the lithium. If you want to use it in an electrode, it's something different. But if you want to use it in an electrolyte, it's good to stick to one particular ion where you want to have the conductivity to be used. So that's the answer to the question.
Okay. Thank you, sir.
Any other would you like to ask?
I have, Professor Sambat sir, I have one, just like to have information. Suppose if you want to have the water splitting,
yes,
or if you want to generate the hydrogen from the hydrocarbons, so what kind of electrolytes will be more suitable? Especially, suppose if I want to convert from the hydrocarbon to this hydrogen generation, without carbon deposition, which will be the best one? Because normally that carbon deposition will be some problem in the, especially I am a conventional catalyst person, so I'm not so familiar with electrolytes. But if you use in the electrolyte for the splitting and water splitting as well as these two processes.
Yeah, this is actually something that has been in the literature. People have been actually trying to do, and particularly using a lot of solid electrolyte. I mean, you're trying to kind of look at something wherein, I mean, it's not a liquid electrolyte. You're not working with aqueous medium, for example. If you have aqueous medium, you have protons that will actually involve hydrogen. But then your interest is to kind of look at something like a hydrocarbon, and then I just want to electrochemically, decompose and then have hydrogen coming out. But anytime you have this kind of hydrocarbon, see, when it actually happens, naturally the carbon has to be there. It will come out. So the carbon will participate in the system. Now, there is something called carbon nitride people have been actually looking at. Graphitic carbon nitride. This graphitic carbon nitride, C4N4 or whatever, is a semiconducting material which has certain band gap, and that's a nice photocatalyst. In those cases, they try to combine this kind of either hydrocarbon or any other source to go to hydrogen. In those cases, the carbon, even if it comes, the carbon has to come out anyway. It is not going to just stay there. So when you put the hydrocarbon, the carbon has to come somewhere. So when you use this kind of a material, the actual efficiency doesn't come down. You still have fairly good hydrogen that comes out, but then the carbon also is taken care of by the other materials. So there are certain materials that people are looking at. Sodium beta alumina, I understand, is one of the electrolytes that was used for this particular purpose.
Thank you. Thank you. Any further questions? Anybody?
Sir?
Yes, please.
Sir, I am. Yeah, sir, can we combine this solid electrolytes with any other like graphene oxide or CNTs to enhance the connectivity? Because already connectivity is there, but still, if you want to enhance more, whether can it combine with that?
Yes, it depends on the application. For example, if you put CNT, it is going to increase not just the ionic conductor, but then the electronic conductor. So you'll have a mixed conductor that will get formed. And there are applications where one needs to have a mixed conductivity. I just mentioned it right at the beginning. You can have conductivity of the ions, you can have conductivity of the electrons in the same matrix. Wherever such an application is required, yes, there is a possibility. People have been using it in sensors where there is a possibility of having this kind of material along with, say, CNT or graphene oxide. Yes, it is possible.
Okay, sir. Thank you, sir. Any other questions from the participants?
Sir, I have one more relevant to that same question.
Please.
Normally, the hydrocarbon, mostly the for me, the electrolytes means normally the electrochemistry, normally they do in the aqueous medium, often. But then when you go into the hydrocarbons to fuel or gasification, it's like a gasification of hydrocarbons, which normally required conventionally very high temperature.
Yes.
But if we can do it in the, as you mentioned, if you can do it into the electrochemically at room temperature, that is a good alternative for the fuel. So in that sense, normally the electrochemistry work in the presence of aqueous mediums. So how we can tune this kind of process when you have the non-aqueous electrolytes, or can we have it, or
Yes,
how it's
yes.
possible? Is it possible?
It is possible, and there has been some work going on in this direction. See, aqueous medium, aqueous solvents are good for certain application and certain studies only. But certain other studies require non-aqueous medium. I mean, even lithium batteries actually require a non-aqueous solvent only. You cannot put a lithium metal in water, so it has to be a non-aqueous medium, and it is an organic solvent. Now, in the same tone, what you're talking about as hydrocarbon to hydrogen, yes, non-aqueous solvents are being used, liquid solvents, and as I just mentioned, this kind of solid electrolytes are also used to do that. So it is possible to have non-aqueous solvents which have a fairly high potential window. People have been trying to look at ionic liquids in this direction, particularly for the problem that you mentioned. There are some ionic liquids that are actually tried out for hydrocarbon to hydrogen, which give you a fairly large electrochemical potential window, unlike in water. You cannot use water, but then it's possible to use ionic liquids or a mixture of solvents that one can use. Alternatively, a solid electrolyte can also be used. A solid electrolyte can be used under conditions wherein you have the gaseous analytes that can actually be taken through what we call as a gas diffusion electrode. So you can pass the gas through the electrode surface and then get the reaction happening at the interface of the electrode and the electrode. Yes, ionic liquids can be used if you want to have a liquid, or solid electrolytes can be used.
Thank you, sir. Madam, we can come.
So, sir, I think, yes, sir. Thank you very much, sir. Thank you very much for being with us. I think most of them has given the information that it is very informative. You have enlightened their knowledge on the electrolytes, like that. Many things are there in the chat, but no questions are there. Anyway, I think we can conclude the session. I think almost done, and we need to join by 2 o'clock. Sir, I think.
First of all, I thanks, thank you, Professor Sambat sir, for joining with us for this webinar. It is a wonderful session. We had today we had 3 eminent people, Professor Dr. A.K. Tyahi, Ashok Ganguly, and Professor Sambat sir. All are in different types of solid state chemistry. We enjoyed the session, sir. Thank you for joining with us and sharing. Thank you, Professor Sambat sir.
Thank you very much. I'm sorry I could not get the video on. I would have liked to.
We found very happy. It's okay, sir. We understand the difficulty. Actually, we have an afternoon session. We have a oral presentation, as well as in the evening we have the Professor Gopinath sir and Dr. Swapna Nair is from our university. They are giving in solid state chemistry.
Fantastic.
Different perspective. So
it's really nice. It's really nice that I could talk to you guys, but I mean, if it's in person, one can interact with the participant. It's very important.
Yes, sir.
When you see the person, and then talk, you also know whether it goes across, it gets across, and what is their interest and things like that. We'll do that at some point. Okay?
Yes, sir. Yes, sir.
Yeah.
We'll try to have offline in near
No
future.
problem.
Sir.
No problem.
Thank you.
Thank you. Thank you very much. Thanks a lot. Okay.
Thank you very much, sir.
Thanks.
Thank you very much, sir.
All the participants, please join at 2 o'clock for the oral presentation, students and faculty oral presentation. And 3:50, we will have the keynote lecture 4, that is by Dr. C.S. Gopinath sir from NCL Pune. He is the Catalyst Division Head and NCL Pune. He will be talking on XPS. Okay, so all of you are requested to join at for oral presentation at 2 p.m. And oral presentation, there are 2 sessions. those who are in absorption and membrane chemistry, they have been given in a separate session, which will be handled by Dr. M. Bhakyalakshmi Madam, along with Dr. Sandpak from Purnapraja Institute. So that will be by the Google Meet link, which we have shared already. And those who are in the today theoretical aspects of solid state chemistry and theoretical aspects of chemistry, allied science, which will be at 2 o'clock using the same Zoom link. So all of you requested to join, and all are you requested to join at 3:50 p.m. for the invited lectures, which will be by the Dr. Kobina sir, then followed by a keynote lecture by Dr. Kobina sir and invited lecture by Dr. Sopna Nair. Okay, all of you are requested to join. So you may leave for now, and then after the invited lecture, we will have the again oral presentation on the inorganic materials and organic materials, which will be at 5:30. Okay, thank you, all of you. Keep join at 2 o'clock. Sunny?
Thank you very much.
Yes, sir.
So we can close the Zoom now, but the YouTube will be remain same, isn't it?
Sir, YouTube will be remaining the same. I'm not closing the YouTube live stream right now. For an hour, it will be a blank screen, and
Okay.
then we can restart it by 2 o'clock, if you say.
Yeah, 2 o'clock. There is a.
Okay, sure, sir, no issues.
2 o'clock. 2 o'clock. There are a list of 7 students are there. They have to present.
Okay.
Yeah.
Sir, I am also not closing Zoom also. Zoom will be remain activated so that it should not create any chaos. So I'm just switching off the recording for this session right now.
Okay, thank you. Thank you.
Yeah.
Dr. Reddy, are you there? From Canada? Dr. Karthik?
Sir, Zoom link, Google Meet link, shall I post it here?
Yeah. You post it here for the oral presentation.
Yes. Maybe they can join.
It is oral presentation 1 to 8.
Yes, sir.
Okay.
Hello, there is no sound, na? Hello.
Hello, sir. Sir,
No sound.
it is now at 2 o'clock, sir. Oral presentation.
Okay, it's going on now. Or okay.
Oral presentation at 2 o'clock. 2 o'clock, sir. Now it's lunchtime, sir. We are.
It is not coming in this one, na, right?
Yes, sir.
இதுல வராதா அது oral presentation?
2 o'clock. 2 o'clock. 2 o'clock. Two o'clock, sir.
கேட்கலையே.
நீங்க சொல்லுங்க, அது சொல்லுங்க. 2 p.m.
Sir, now we have break for lunch and we will be joining by 2 o'clock, sir.
Okay, right. Thank you. Okay, right. Thank
2 p.m., sir.
Thank you.
Mm.
Good afternoon, Dr. Naveen. Good afternoon, Dr. Deepak.
Good afternoon, sir. Can you hear me?
We are given a 2:10, I think, schedule, if I'm correct. Sorry.
Yes, sir.
So we'll try to start after 5-10 minutes. Nimisha, are you there? If all kind, then Dana is there. Hello, hello, Dr. Shankar. How are you? I am in the other, I will be in another meeting. So, but Manish will be, there will be parallel session. So, yeah, how are you? Everything fine? And our students coordinated of Dana and research scholars again will be there. So, she will help. She will help. So I will also ask the next student. All the speakers are total 7 students. 5
present here. Today, we are here for the oral presentation.
Nimisha, are you there?
Yes, sir. I'm here.
Neetu?
Yes, sir. I'm here.
The oral presenter is there? First one?
First one is Binimol Mary Matthew.
Dr. Binimol Matina?
Yes, sir. Yes, sir.
You are there? Okay, fine, fine. Then next,
Deepa
Dr. Deepa Rachel.
Yes, sir.
Everybody is present? Janisha? Neetu, who is absent?
Yes. Third one is Janisha.
Huh?
Janisha.
Janisha will be absent, no?
No, sir.
Janisha.
Is Ramutai. Ramutai is absent.
Okay. So, Nimisha, can you initiate?
Yes,
so,
sir.
Dr. Kulkarni, welcome. Dr. Deepa, madam, are you ready? Dr. Deepa? Deepa, madam?
Yes, I am ready.
You are ready. Dr. Kulkarni?
Yes, sir. Yeah, I'm ready.
We have to, before 3:50, we have to finish it. So, I think we can start in. Nimisha, can you introduce?
Yes, sir.
Yeah.
Good afternoon, everyone. Welcome back to the oral presentation. So here we have the oral presentation and we have two judges, Dr. Deepa Janardhanan and Dr. Naveen Kulkarni. A brief about both of them. Dr. Deepa Janardhanan completed her PhD from IIT Bombay and has attained the postdoctoral research from Hebrew University of Jerusalem. She is specialized in computational chemistry like modeling reactivity and selectivity of chemical reactions using computational tools. She has authored more than 17 publications in high-impact peer-reviewed journals. Currently, she is working as assistant professor in Department of Chemistry, Central University of Kerala. Dr. Naveen V. Kulkarni currently serves as assistant professor at the Department of Chemistry, Amrita School of Arts and Sciences, Amritapuri. He completed his PhD degree from Department of Chemistry, Karnataka University, Dharwad. He also worked with renowned organometallic chemists like Professor Morris S. Eisen as a postdoc at Technion, then Professor H.V. Rasika Des as a postdoc research associate in United States, and Professor William D. Johns as a scientist at University of Rochester, New York, and contributed in development of several valuable catalysts and methodologies. He joined the Department of Chemistry at Amrita in 2017. His current research interests include coordination chemistry, organometallic chemistry, catalysis, and sustainable chemistry. On behalf of the webinar committee, I welcome both of the judges for the judgment of this oral presentation session.
Thank you, Nimisha.
Thank you, Nimisha. Thank you very much.
I request the first participant to begin the presentation. The presentation will be for 8 minutes and there will be 2 minutes for question and answer session.
Yeah. I think Dr. Deepa and Naveen, kindly restrict them in time exactly. Okay.
Yes, sir. Is anybody keeping time for us, or I can keep it?
Yeah, you can because she will help it. Nimisha or Neetu can help you people. So you can. Okay.
If Neetu or Nimisha can keep the time and then tell us when it is up.
Neetu, can you tell them whenever? Yes, okay, just note down the time and exactly you tell them. Okay.
Okay, sir.
In 7 minutes, you say that 1 more minute is there, then they can take care. Okay. Dr. Naveen and Dr. Deepa can take care. Okay, is it fine, Dr. Deepa and Naveen?
Yes, sir. Yeah, sir.
Okay, sir. Okay.
Thank you.
Yeah, please carry on. I'm in another session also. Please carry on. I am there in the board. Okay. Okay.
Are you there ready for the presentation?
Yes, yes.
Okay, you can begin the presentation.
Okay, thank you. Is it audible and visible?
Yeah, it's audible. It's visible also.
Okay. First of all, good afternoon, everybody, and thank you, Central University, for giving me an opportunity for this presentation. I am Binmol Mary Matthew, presenting the topic Structural Characterization and Theoretical Studies of an Organic Adduct 8-hydroxyquinoline sulfosalicylic acid. We know for the past decades, the supramolecular chemistry has been fastly growing, utilizing the different non-covalent interactions like hydrogen bonding, pi-pi interaction, van der Waals interaction to form multi-component systems which find extensive applications in pharmaceutical chemistry, energetic materials, optical and semiconducting materials. Here, I report the synthesis and characterization of an adduct 8-hydroxyquinoline and 5-sulfosalicylic acid. We know 8-hydroxyquinoline is a versatile ligand for the use in metal complex chemistry and also possesses diverse bioactivity. And 5-sulfosalicylic acid also possesses polydentate function, which can utilized for the synthesis of supramolecular structures, and also it possesses antibacterial and antifungal property. Here, this compound is prepared by synthesized by dissolving together 1:1 stoichiometric amount of 8-hydroxyquinoline, that is 5 millimole. 8-hydroxyquinoline is dissolved in ethanol and 5-sulfosalicylic acid is dissolved in water. The two solutions was continuously stirred for 2 hours in room temperature, and the resulting solution was filtered in a glass vessel, and after 2 days good quality yellow colored single crystals was obtained. And the crystal structure of this compound is already reported in literature, and they have prepared this compound by using another method, that is reflex method. Here we prepared this compound by grinding method. And this is a synthetic route, 8-hydroxyquinoline sulfosalicylic acid results in the formation of this proton transfer compound. And here from the crystal structure, it was evident that a proton from the SO3H group, SO3H group, it is transferred to nitrogen of 8-hydroxyquinoline to form this proton transfer compound, and this asymmetric unit contains one water molecule also. These are the studies we have done: experimental single crystal HRD, FTIR study, photoluminescence study, thermogrammetry, NLO study, and theoretical Hirschfeld surface analysis, NBO analysis, and HOMO-LUMO analysis. This is asymmetric unit, and this crystal system is monoclinic with space group P21 bar N, and ABC values and alpha, beta, gamma values are presented here. And the asymmetric unit contains one 8-hydroxyquinoline, one sulfosalicylic acid, and along with one water molecule. And important bond length and angle is presented in this slide. And it is already said that this nitrogen of 8-hydroxyquinoline is protonated, and this is evident from the NH distance, bond distance 0.90, and this OH group from SO3H group is deprotonated, and we can see that almost all sulfur oxygen bond lengths are equal, indicating the resonance. And there is a carboxylic group in this sulfosalicylic acid. It is not deprotonated, and it is evident from the distance that CO distance, one distance is COH distance, that is CO distance in COH group. One is 1.319 Armstrong and the other is 1.213. If it was deprotonated, the distance almost same due to resonance. And one important bond angle, this is the bond angle in 8-hydroxyquinoline, that is carbon-nitrogen-carbon bond angle. In the neutral 8-hydroxyquinoline, this angle is 119 degree, but in this adduct, this bond angle is 123 degree, indicating that is this enhancement of internal bond angle is also an evidence for the protonation at nitrogen. This is a packing diagram of molecule, one with hydrogen bond and one without hydrogen bond. And here the important bonds present are NH, that is nitrogen is protonated, that NH is hydrogen bonded to oxygen of sulfonate group. Then water molecule is hydrogen bonded to OH of 8-hydroxyquinoline. And furthermore, this water hydrogen atoms, it is the main contributor, that is this water hydrogen atoms extends the crystal structure through hydrogen bonding to sulfonate group. That is the main important bond present in this crystal structure to get the three-dimensional structure. And from this packing diagram, one intramolecular hydrogen bond is present here. This intramolecular hydrogen bond results in the formation of a cyclic structure. That is, this intramolecular hydrogen bond is formed from CO group of COH and the OH group of the acid to form a cyclic ring structure, which is represented as S6, and S represents intramolecular, and the 6 represents the total number of atoms present in that cyclic structure. The FTIR spectrum of this 8-hydroxyquinoline, sulfosalicylic acid, and the proton adduct is reported here. And the important assignments, first one is 3,388 centimeter corresponds to OH of COH group. One COH group is present in sulfosalicylic acid, and that OH group is assigned as 3,388 in the parent compound. But in the adduct, it is red shifted to 3,366, indicating that the presence of hydrogen, that is hydrogen after the formation of hydrogen bond, this OH is red shifted. And the CO stretching frequency in the parent compound, that is in the acid, it is 1,690 centimeter, and in the adduct it's approximately equal 1,688 centimeter inverse, indicating that the COH group is not deprotonated. If it was deprotonated, that results in the formation of CO minus stretching, symmetric and asymmetric stretching vibrations. And this NH stretching vibration, this 8-hydroxyquinoline is protonated. So NH stretching vibration is assigned as 2,648 centimeter inverse, a broadband. The PL emission spectrum of this compound excited at a wavelength of 370 nanometer, and the emission maximum is obtained as at 551 nanometer. The thermal studies was performed to analyze the thermal stability of the compound, and this is found it is stable up to 90 degrees Celsius, and at that temperature there is a weight loss corresponding, or it is an indication of the presence of water molecule in the crystal structure. And this is a Hirschfeld surface analysis of the molecule, and this Hirschfeld surface, it's a three-dimensional surface that defines the volume around the molecule in a manner similar to van der Waals surface. So it is defined by the molecule and the proximity of the nearest neighbor. So this encodes information about intermolecular interactions present in the molecule. And if the atoms make internal contacts closer than the sum of their van der Waals radii, these contacts were represented as red spots on the surface. Longer contacts, that is larger than van der Waals contacts, it is represented as blue color, and white color indicates almost equal to the sum.
Sorry to interrupt, you have 1 more minute, so you have to be quick.
Okay. So this red color indicates the presence of OH bond. That is, it is an important bond present in the molecule. So that red color indicates OH group. So this is a fingerprint plots that gives the percentage of contacts. That is, OH contact contributes about 45.5%, and HH contact, that is an important contact, weak contact, but 29.8% contribution. And CC contact is an indication of pi stacking, that about 11.3%, and CO contact about 4.5%. This NBO analysis was performed to analyze the delocalization or charge transfer present in the molecule, and these are the different interactions, donor-acceptor interactions present in the molecule. And here HOMO-LUMO analysis was performed. And this HOMO-LUMO, and HOMO is mainly localized on 8-hydroxyquinoline, LUMO is mainly localized on sulfosalicylic acid. So this this suggests the possibility of charge transfer interaction in the molecule, and the energy gap is found about 1.05 electron volt. And SHG efficient second order NLO study was performed, and this compared with the reference material urea, it is found that this compound 8-hydroxyl sulfosalicylic acid, 83% NLO efficiency, it is 83% of the parent compound, and we compared with another compound 8-hydroxyquinoline salicylic acid, and that compound we have prepared.
Can you please go to the conclusion part?
Okay. Conclusion. So synthesized product of 8-hydroxyquinoline salicylic acid, characterized by these studies, Hirschfeld surface analysis gives the intramolecular interactions present in the molecule, NBO analysis reveals charge relocalization, and SHG studies shows that NLO efficiency is 83% of the reference material urea. Thank you.
Good presentation. I think we have time for maybe 1 or 2 questions. Any questions from the audience? Please try to be quick on and crisp on questions.
Audience can put in chat box also question.
Okay. If not, Vinny, can you tell me what is the purpose of this study? Like, and is this compound new? Is it not been reported before?
Yes, sir. The crystal structure is reported already in literature, but the other characterization studies, it's not reported. Theoretical studies and the other characterization studies not reported in literature.
Okay, so what you wanted to show? Actually, you wanted to see how the characterization stuff and theoretical things can be combined to get some new information about the properties of the molecule. So I did not quite understand what is the conclusion.
So in this ADEC, the important interactions are non-covalent interactions. Okay, so we have performed the theoretical studies to analyze the percentage of different intermolecular non-covalent interactions that forms the stabilization of crystal structure, and that's why we performed the Hirschfeld surface analysis and NBO analysis.
Okay, yeah, thank you.
So I have a question. Vinimol, can you hear?
Yes, ma'am.
Yeah. I have a question regarding this charge delocalization using NBO. Can you go to that slide? Okay. So here different ranges of energies are obtained in kilocalorie. So what is the reason behind this high amount of delocalization in the case of entry number 1, then 4? Then there is so much 100 kilocalorie for the C6C1. So can you?
These are different. This high amount of energy delocalization energy corresponding mainly to pi to pi star interactions and lone pair to pi pi star interactions, which are mostly intramolecular interactions. Okay, intramolecular interactions, and here one intermolecular interaction between water molecule and lone pair of sulfonate group. In the crystal structure, I have said that this is one of the important interaction that stabilizes the crystal structure, that is between one oxygen of sulfonate group to water molecule. Okay, and that is also evident from the NBO analysis. Interaction energy is about 2.30 kilocalorie, but it is an indication of or it supports the experimental evidence.
So already some NBO values of this kind of system is reported, and how is your values correlating with the reported data?
NBO
not for same molecule, similar kind of system.
The values are not much high. So from this value we can conclude that some delocalization interactions takes place in the molecule. Even though the values are not much high, intermolecular interactions takes place in the molecule.
Okay, thank you.
Okay, thank you. I think maybe we can go to the next presenter.
I request the second participant, Deepa Rachel Koshi, to begin her presentation.
So presenters, be on time and try to maintain the timing, because you see, if you spend more time in introduction part, then you won't be getting enough time to explain the actual research and conclusion part. So you can kind of skip the introduction and then go to the actual studies.
Hello, sir. Is it visible and audible?
Yes, please go ahead.
I am Deepa Rachel Koshi. I am doing my MSc Chemistry program at St. Gregorius College, Kottarakara. Today, I would like to introduce my topic, in silico study on anti-inflammatory properties of phytochemicals present in Quassia indica stem. So, Quassia indica, popularly known as Carinota in Kerala, is a species belonging to Cimarobaceae family, also known by the name Samandera indica, and is an evergreen shercoat tree growing up to 10 meters tall, and is widely used for Ayurvedic preparations in Kerala for skin eruptions, skin diseases, also used for the treatment of malaria, rheumatism, etc. And the useful part of this plant are seed, bark, and leaves, and the propagation of the plant is mainly by seeds, and is found in India, Myanmar, and Sri Lanka, and is widely distributed on damp forest and deciduous forest. And we have to focus on the phytoconstituents on the Samandera indica. It has mainly alkaloids, flavonoids, saponins, carbohydrates, proteins, phenols, steroids, etc. In our study, we have to mainly focus on the quasinoids, that are the diterpenoids in Quassia indica, and are regarded as the taxonomic marker of the family. They are mainly the Samanderins and the Indiaquasins. Samanderins XYZ, DCE, and the Indiaquasin XC, AD, and E. So before moving on to the anti-inflammatory properties of these selected phytochemicals, we have to discuss about the inflammatory disease. That is, it is an array of disorders and conditions that are characterized by inflammation. It is normally the action of the body, the action of the immune system, but it becomes harmful when it itself affects the healthy tissues of the body. So it may be short-lived or long-lasting, and the examples include allergy, asthma, autoimmune diseases, and the symptoms include swelling, joint pain, joint stiffness, redness, etc. And therefore, anti-inflammation is just opposite to that of inflammation, that can reduce inflammation or swelling. So the cyclooxygenase enzyme is a receptor in which the natural compound arachidonic acid binds to the active site and produces prostaglandins that is responsible for inflammation. So if we have a drug or any other phytochemical that has greater binding affinity than that of this arachidonic acid, the formation of prostaglandin can be reduced and the inflammation can also be reduced thereby. So one such non-steroidal anti-inflammatory drug that counteracts with the cyclooxygenase enzyme is aspirin. As we all know, it is acetyl salicylic acid and is a non-selective COX inhibitor and has anti-inflammatory and is a widely used medication for antipyretic effect. And the 3D structure from PubChem database is given on the right side of the PPT. So the objectives of the present study is to list out the phytochemicals, mainly quasinoids, Samanderin DCE, Samanderins XYZ from the Quassia indica, and to find out which is best suitable for the anti-inflammatory activity. So in order for that, proteins are selected on the basis of the target where the commercially available NSAIDs are active. That is, the proteins are COX receptors. The proteins selected are 6PL3, 1PXX, 4PH9, 5W58, 4M10, 5F19. Then these proteins are docked with the selected phytochemicals using molecular docking, from which we get the docking score or the binding affinity. Molecular docking is nothing but the computational mimicking of the binding of the ligand to the active site of the protein. And after that, the toxicity and the drug-like score of the phytochemicals were studied using PreAdMET and the MolSoft software. So the methodology includes protein preparation using pi mode. That is, we have to remove the heavy water molecules, add the missing hydrogens, and to remove the natural ligands if they need. And the ligand preparation by Avogadro software, and the conversion of these PDB files to PDB-QT using Autodoc tools, and to give the input file as conf.txt, and to run the molecular docking file in the command prompt of the Windows system in Vina software, and the output analysis using Discovery Studio Visualizer, in order to study the absorption, distribution, metabolism, excretion, and toxicity study of the phytochemical using PreAdMET software, and to know whether the ligands obey the Lipinski rule of 5 or not, and to find out the drug likeness score using the MolSoft software. So the result that we got is that among the phytochemicals, that is the quasinoids from Quassia indica, Samdar Z got high ligand receptor interaction with the 5F19. So we selected Samdar Z as our target ligand and 5F19 as the target protein. The Samdar Z has a docking score of -11.3 kilocalorie per mole, which is even comparable with that of the non-steroidal anti-inflammatory drug aspirin, which only have -6.4 kilocalorie per mole with the same target protein 5F19, which is a COX-2 receptor. And the ADMET properties of the ligand Samdar Z was also studied using the PreAdMET software, and it has been found that it is non-toxic in nature, and it obeys the Lipinski rule of 5 from the drug likeness properties using MolSoft software. And the conclusion that we have obtained is that the docking score, the best docking score from the molecular docking, indicates that they are the best inhibitors, or they can bind to the active site of the enzyme exactly. So here Samdar Z has a binding score of -11.3 kilocalorie per mole, can exactly bind to the active site of the enzyme 5F19 or the COX receptor, and therefore it can act as the best inhibitor of COX enzyme 5F19. Therefore, it can prevent or reduces the prostaglandin formation, and thereby can act as the best anti-inflammatory agent. And it also shows drug likeness properties, obeys the Lipinski rule of 5, and is non-toxic in nature. It is non-mutagenic and non-carcinogenic. And therefore, we can conclude that from the medicinal plant Quassia indica, the ligand Samdar Z has better anti-inflammatory properties like existing drugs. So this is the docking output analysis figure of 5F19 with Samdar Z using Discovery Studio Visualizer. And the circles indicate the active amino acid residues, and in the center we can find the Samdar Z ligand, and the interactions are given on the PPT on the top, on the bottom. So I would like to thank Dr. Disha Kea for her guidance and support, Assistant Professor, Department of Chemistry, St. Gregorios College, Kottarakara, and also Dr. A.B. TG, Assistant Professor and Research Guide, PG and Research Department of Chemistry, for his technical support and guidance, Head of the Department, Principal, St. Gregorios College, Kottarakara, and thank you, Central University, for giving me this opportunity. Thank you all. Hello.
Good presentation. So we still have, I think, two plus minutes for the question and answers. So if anybody has any questions, please go ahead. Any questions from the audience? You can post your questions in the chat if you don't want to answer. Okay, Deepa, one short question. So are these experimentally verified, like these molecules have been isolated, or do you know if any kind of experimental work using these phytochemicals is being carried out?
So from my experience, there are no experimental works based on this phytochemicals yet. Only the antimicrobial effect such that are studied, but based on this phytochemicals, not studied yet.
Any other questions?
Sir, I have one question.
Yes, ma'am.
Deepa, in your result you showed this one Samdarin Z only selected for the docking ligand. What about the other compounds? Whether on which basis you have selected only one this one as the best for interaction with the target protein?
We docked all the ligands, Samdarin B, C, X, Y, Z, Indaquaz, and E with the target proteins, 6 proteins selected. Out of these docking scores, Samdarin Z was the one ligand which has high docking score with the ligand 5F19. At the same time, we compared the docking result with that of the standard aspirin. Aspirin has given only this much score, minus 6.4, only with 5F19 protein. So we selected 5F19 as the target protein. On that protein, Samdarin Z got the high docking score.
No, actually, when several compounds are compared, you can show like a tabular data which is having which value. Like based on that, based on the values you select, you say this is the best one. So you have included only the best result. Other things are only one sentence is written there. Other things, what are the values? We don't have any idea. So that would have been better.
It is almost long table.
No, it is okay. Values are good, score is good, but why the others are not selected? It is not clear to us. That's why.
I tried to include this, but it is a long table. The resulting will be long table. That is why I excluded the table.
Okay, good.
You would have been like maybe short it and then put it, because audience would like to see what you all have done. You don't have to explain it anyway. So just by putting it on the PPT, make things clear.
Yeah, picking some of them which are having some high activity like that, selected things you should have.
Okay, sir.
Okay, thank you.
Okay, sir. Thank you.
So if there are no more questions, then we'll go to the next presentation. I think it is Janisha.
Sir, shall we move next presentation?
Janisha is not here.
I request Janisha to begin the presentation.
Okay, ma'am. Screen on down. Good evening to all. My presentation topic is molecular geometry.
Hello, Janisha ma'am, are you using two devices simultaneously? If you're using two devices simultaneously, please deactivate one device and use another device. Or you can do one thing. You can just mute the speaker as well as mic of the other device from which you are not speaking up, and then you can unmute yourself. In that case, the humming sound which is coming it's not going to come.
What happened? Is it fine? So what happened, Dr. Deepa?
Sir, Janisha needs to be presented, but there is some issue.
Some issue with her mic, noise was coming.
Sir, actually, she's using two devices at a same time, the same place. So that's why though it is creating a humming sound. She needs to just mute the mic as well as speaker of the other device from which she is not talking. In that manner, she can present her.
Neetu, can you coordinate with her? And meantime, we can go for the next one if she is ready. Next candidate is this.
Yes.
Okay.
Yes, sir. Next,
so you can tell
next candidate is Anusha, sir.
See, if needed, Janisha can share the, Janisha now sharing. Is it Janisha is presenting?
It's okay, no. Slide service.
Sir, is it audible?
It is visible and audible.
Okay, ma'am. My presentation topic is molecular geometry, HOMO, LUMO, and DFT calculations of 4-NAF, 2-chlorophenylamino thiazole. Introduction. Density functional theory is most important methodology for theoretically predict the behaviors of organic compounds utilizing B3LYP 631G basic set. In recent years, among the computational methods, calculating the electronic structure of experimental values of molecular geometry, vibrational frequencies, atomic charge, dipole moment, thermodynamic properties, etc. The determination of the electronic parameters of a molecule is an efficient tool to predict and interpret its reactivity in several types of reactions and remain a powerful technique to explain the biological activity result. The main objectives of this paper is to present more accurate vibrational assignments, bond length, bond angle, atomic charges, and HOMO-LUMO of 4-NAF2-I 2-chlorophenylamino thiazole. Computational details. The geometry and vibrational frequencies of the title compound 4-NAF2-I 2-chlorophenylamino thiazole has been optimized with the help of B3LYP 631G density functional theory method using Gaussian 09 software package. This is the optimized structure of 4-NAF2-I 2-chlorophenylamino thiazole. This is the bond length data of 4-NAF2-I 2-chlorophenylamino thiazole. In this data, the SC bond length is higher than other bonds. This is the bond angle data of 4-NAF2-I 2-chlorophenylamino thiazole. This is the HOMO orbital of 4-NAF2-I 2-chlorophenylamino thiazole. This is the LUMO orbital. HOMO-LUMO energy gap is 0.20392. From this HOMO-LUMO value, ionization potential, electron affinity, electronegativity, hardness, softness values are calculated. This is the Mulliken atomic charge of 4-NAF2-I 2-chlorophenylamino thiazole. In this data, some of the carbons are negative charge and other carbons are positive, and all the hydrogens are positive. This is the calculated IR spectrum of 4-NAF2-I 2-chlorophenylamino thiazole. This is the calculated IR spectrum data. The NH stretching vibration mode is observed at 3600 range, and the NH bending vibration mode is observed at 1629. The CC stretching vibration mode is observed at 1300 to 1600 range, and the CC bending vibration mode is observed at 500 to 900 range, and the CH stretching vibration is observed at 3100 to 3300, and the CH bending vibration is observed at 1100 to 1600. Conclusion. The DFT calculation on the structure and the vibrational spectrum of the title compound has been carried. Using this optimized geometry, the vibrational frequencies have been found to agree well with the literature reported values. Calculated HOMO-LUMO energy show that charge transfer occur within the molecule, which is responsible for the bioactive property of molecule. Atomic charge distribution were calculated by determining the electron population of each atom. Thank you.
Okay, we still have a lot of time. So anybody, any questions?
Is there DFT calculation help to find out the reactivity, which is the most reactive functional group among this? Can you tell? Janisha?
Yes, sir.
Maybe I would like to add something to that question. So you have calculated so many parameters just by using the energy difference between HOMO and LUMO. Then what information we get? Like, is there anything useful for a synthetic chemist from your studies?
LUMO values, energy gap is low, the bioactive of the compound is high.
So this compound has been already reported, right? So people have done the bioactivities also. Or is this a brand new compound?
How this study helpful to find the functional group activity of this molecule? Which is the most active functional group present in this molecule? Janisha, can you hear?
Yes, sir.
Can you, from this your study, can you say that your molecule, which is the most active functional group?
Sulfur, the thiazole ring is the most active functional group.
So how you're concluding? My concern is from DFT study, can you conclude? That's what. Is there any, can you prove some evidence? Okay, fine.
Are there any other questions?
Janisha, then why this molecule you have chosen, or what is the objective of your work? Why did you choose this? You didn't tell us what is your, why did you do selectively this molecule? Why did you choose, and what is the importance of this molecule? All those things.
The bioactivity of compound of this compound.
Okay, so maybe then we can move to the next presenter. Who is the next presenter?
Sir, I think Anashafar is not present. So Subi will be presenting next. I request her to share.
Sorry, Anashafar is presenting. She told she will present from Dinisha's laptop.
Okay. I request Anashafar to present, please. Janisha, can you stop sharing the screen? Anashafar, SP, please begin the presentation.
So they are not around. Maybe next one we can proceed. After that we can. By the time
I don't see her.
The next person is ready, sir. S. Subi.
Yeah, they can present, and then Neetu, can you coordinate the?
Yes, sir.
S. Subi, you can take over.
Yeah. Okay.
There is a constant disturbance from somebody. I don't know if you all can mute.
Good evening, everyone. Is it audible, ma'am? Is it audible, ma'am?
Yes.
Yeah, okay. My
You have some
presentation
background
topic.
noises coming, so you. Fine, carry on.
Okay. My presentation topic is synthesis, characterization, depth calculation, molecular modeling, and antioxidant study of novel 5,4-methoxyphenyl 3-pyridine 3-eel 1-hydroxypyrazole. The novel compound 5,4-methoxyphenyl 3-pyridine 3-eel 1-hydroxypyrazoles are synthesized and characterized by IR, H1N, and C13 NMR spectroscopy. The electronic properties and geometrical properties of 5,4-methoxyphenyl 3-pyridine 3-eel 1-hydroxypyrazole derivative was computed theoretically using B3LYP 631G DP basis sets. The HOMO and LUMO energy gap explain the charge transfer within the molecule. The optimized structure, all the compounds shows the in-plane and out-plane molecule. The compounds exhibited good docking score against the 4 mm height liver cancer. The antioxidant study also evaluated good IC50 value. Then introduction, heterocyclic compounds have played an important role in pharmaceutical chemistry due to their biological activities. The compounds containing a pyrazole ring have shown useful biological properties and have been developed as fungicide, herbicide, or plant growth regulators. The biological importance of pyrazole derivative was emphasized during the period 1941 to 1945. The presence of the pyrazole ring is an important therapeutic agent. The combination of DFT calculation of chemical shift or harmonic vibration with nuclear magnetic resonance and IR Raman experimental parameters. Quantum mechanical calculations of energies, molecular geometry 5,4-methoxyphenyl 3-pyridine 3-eel 1-hydroxypyrazole were carried out by using B3LYP 631G method. Numerator reports have been made citing the success DFT compared to conventional methods in computing molecular and chemical properties such as geometries, vibrational frequencies, and thermodynamic properties. Then the general procedure for the synthesis of 5,4-methoxyphenyl 3-pyridine 3-eel 1-hydroxypyrazole. The 5,4-methoxyphenyl 3-pyridine 3-hydroxypyrazole compounds were synthesized by adding the 5,4-methoxyphenyl 3-pyridine 3-eel 2-propane 1 and hydrogen hydrate and glacial acetic acid refluxed for 8 hours in water bath at 80 degrees Celsius and cooled. It is given an orange-yellow crystalline solid. The solid product was filtered and washed with water. Then the spectral analysis of 5,4-methoxyphenyl 3-pyridine 3-eel 1-hydroxypyrazole. The elemental analysis, the carbon found range 71.70, hydrogen is 5.21, nitrogen is 60.72. Calculated for 71.68, hydrogen 5.30, nitrogen 16.60. The molecular formula for the compound is C15H13N3O. Then the FTIR spectrum shows the peaks are here. The 1,196 gives N stretching. Here 1,680 gives C double bond and stretching, and 1,338 gives VN stretching vibrations. In H1 NMR spectrum shows all the 13 hydrogen atoms present. These are the hydrogen spectral values given. Then the computational method, this is the optimized structure of the compound. The structural characteristics and the fundamental vibration modes DFT calculation are carried out by Gaussian 09 software package. Geometry is optimized depth level employing the B3LYP keyword. Using the correlation implement with the 631G basis set. Optimized structural parameter is gas phase were used in the vibrational frequency calculations at depth level to confirm the structure as minima. Using gas view molecular visualization program, the vibrational frequency assignments and the parameters were made. Then Mulliken This is the Mulliken charge of 5,4-methoxyphenyl, 3-pyridine-3-il 1-H-pyrazole. Mulliken atomic charge of reported compound were calculated at the same level and the values are tabulated below. The more electronegative values, N1 atom is minus 0.582 and N2 atom minus 0.250, C4 atom minus 0.169 and C7 atom minus 0.027 and N8 atom having minus 0.373. Then the antioxidant study, the DPPH assay was used to evaluate the free radical scavenging activities of pyridinyl pyrazole derivative. The synthesized compound antioxidant activity were also determined with measuring the IC50 value. The result will explore the pyridinyl pyrazole derivative showed potent DPPH radical scavenging activity compared to the standard ascorbic acid. The compound which exhibited good radical scavenging activity because the compound having substitution with the electron withdrawing group enhanced antioxidant activity against DPPH free radical and their IC50 value were found to be 366 μm. Then molecular geometry, this is the HOMO and LUMO picture of the compound. The optimized molecular structure of the compound is given. The optimized structure parameters such as bond length, bond angle of these compounds calculated by this method. Then molecular modeling, molecular docking between ligands, that means the compound and the protein 4 mm height were analyzed and visualized using Hex 8.0 docking software. The 2D poses of compounds are visualized using the Discovery Studio 3.5, visualizing a greater binding interaction with the receptor protein 4 mm height. The result clearly explores the less binding energy of this molecule, indicate a greater interaction with the receptor protein. On the basis of docking result, the compound possesses good docking score, that is 238.35 kilojoule per mole, and it highly active, so we conclude that it possesses high agreement with the liver cancer cell line. And this is the picture of 2D and 3D structure of the compounds, docking compound. Then conclusion, the geometry of 5,4-methoxyphenyl 3-pyridine-3-il 1-H-pyrazole was optimized by DFT method using B3LYP631G basis set. The complete optimized geometry of the compound was obtained at in vitro depth calculation. Mulliken atomic shows charge distribution, HOMO and LUMO energy gap is so small, therefore low energy is needed to transfer the charge from HOMO to LUMO. The compound possesses highest antioxidant potential whose IC50 value is 366 μm. The compound pyridinyl pyrazole derivative screened for better binding docking score. Thank you.
So the experimental part is also done, right? This compound was prepared and its antioxidant properties were evaluated. Okay, and then you see a proper correlation between theoretical studies and the experimental results. Yes. Hello, can you hear me?
Supri, are you there?
She's disconnect.
She has muted, I think. Shubhi, can you unmute?
Okay, so then we can move to the next presentation.
Sir, we'll go to the next presentation.
Yes, I think it's better because we're running out of time.
PJ Vaishnavi, is she present? Vaishnavi?
Yes, I can present. Give me 1 second, please. Am I audible? Hello?
Yes, you are audible.
Yeah, okay, sure. Okay. Can you give me 1 minute, please? There is an error with the internet just now. I was logged in using phone. Can you just give me 1 minute if it's not a problem? Hello?
Yeah, do it quickly.
Yeah, sir. Sure. I'm not able to share the screen. Hello? Excuse me, ma'am.
Is there a net connection issue or just you are not able to?
Hello, ma'am. I'm not able to share the screen here.
Sunil, Sunny, can you help?
Sir, I have provided sharing rights to her. It has hers and only the issue might be the system issue system is creating an issue.
Vaishnav, you have been given permission. Vaishnav,
Maybe you can send it to some of
Yeah, sir, but
us
share
and
screen option. Yes, sir. When I click share
you
screen option, it's not
or you
getting
can share
connected.
to us any of
It's
us
like
so that
I'm in the this thing, sir. Not able to.
otherwise you send the PPT, we can play from here.
That can be done, sir. I will mail you immediately now. To Shaktivel, sir, can I mail or to whom, sir?
Send.
Yeah, should be okay.
Okay, I can do that.
Or maybe to Nimisha or Neetu, so they can share.
Still, how many of them is there, Nimisha?
Sir, one more left, sir.
One more.
Meanwhile, I think Anashafar can present.
Okay.
And there is one more name in the list, Ramuthai.
Sir, he is absent, sir. He's not
coming. Okay.
Okay. 1 second.
Still, I think
So the mail is getting sent, sir. Just give me 1 minute.
or Vaishnavi can present next, maybe in between the other person.
Yes, sir.
Neetu, the other person is
Sir,
ready.
then, yes, sir. Then Anashafar.
Yeah, ask them to present so that we can save the time.
Anashafar
Anashafar,
also
can you
had
present now?
some issues, right? Is it fixed now?
She told she's ready to present after Vaishnavi.
Okay.
Now,
Yeah.
Ask her if she is present.
yes, sir. I will.
Anashafar is it's not seen.
Yes, ma'am.
Yeah, I can see her. Can you present, Anashafar?
Sir, I have mailed you the PPT, sir. Can you just please check it? Hello?
Yeah, I'm
Yeah, yes.
downloaded.
Okay, sir. Thank you. Thank you.
So, Vaishnavi, you stop sharing. Vaishnavi,
Yes, sir. Tell me.
I am sharing the screen for you.
Okay, so I can present right now, no, sir?
No.
Okay, I'll do that. Thank you.
I see that Anna Shaffer is also trying to present.
Who?
Anna
Yes, sir.
Shaffer. So she's, I think, trying to upload.
This is Vaishnavi presentation. So,
Okay, sir. I think we'll go with Vaishnavi first and then Anna
we'll
Shaffer.
go with Vaishnavi.
So, is my voice audible now? Hello?
Yes. Yeah.
Yeah, sir, but the presentation I'm not able to see, sir. It's not.
Yes, sir. I think it will take a while. I see
Okay.
that it started uploading. Wait for maybe half a minute.
Sure.
The presentation is hanging around.
Oh.
Sir, cancel it and do it again because I see that time Anna Shaffer was also trying to share. Maybe it's giving. So you close it and then again share it.
The problem is my computer is hanged.
Oh.
Sharing, let's see now. It's okay. Now sharing, I can know this.
So maybe, Sunny, can you stop my presentation so that the other person can present? Sunny? Because my computer is hanged.
Okay.
Sir, Anna Shaffer can present now.
You have sharing option.
Is Anna Shaffer ready for presentation? Then she can present.
Anna Shaffer, can you present?
Yes, ma'am. Good afternoon. Molecular structure, vibrational assessment, homolume, molecular charge, analysis, and deep.
Anything, Anna Shaffer?
Excuse me, your presentation is not visible.
Sharing.
Not sharing. Not sharing.
Your presentation is not visible.
Now we can see, but it okay.
You can start now.
Anna Shaffer, are you talking? We are not able to hear anything.
I think she has muted, ma'am. Anna Shaffer, can you hear? Your voice is not audible.
Introduction.
Okay.
Introduction. Benzimidazole is an aromatic heterocyclic organic compound. The synthesis of benzimidazole-based polyheterocycles draw the attention of paramedists from last few decades the function of important pharmacophore in medicinal chemistry and pharmacology. The biological activities of benzimidazole and thiazole are such as antimicrobial, antifungal, anti-inflammatory, antiviral, antioxidant, anti-cancer, and anti-ulcerative, etc. When benzimidazole ring fused with thiazole ring, which will increase the biological activities of the moiety. In the present study, quantum chemical computations will be performed within DFT using B3LOT 631G model to investigate the molecular structure, IR vibrational spectra, and homoluma in a jigger. Computational method. The structure, characteristic, and fundamental vibrational modes DFT studies are carried out in the compound 1-benzyl 2,2-phenylaminothioate 4-vinyl benzimidazole using Gaussian 09 software packages. Theoretical computations can be performed using Beck-T parameters Liang for B3LP level of theory supplemented with the standard 631G basic set. The methodology involved in DFT includes electron correlations and hence in the Dessert method for obtaining theoretical charge density. The optimized structure of 1-benzyl 2,2-phenylaminothioate 4-vinyl benzimidazole. The bond length of 1-benzyl 2,2-phenylaminothioate 4-vinyl benzimidazole. The molecule of an atom SN2C2, the bond length is 1.84334 and the C2 to N3 is 1.31040, N3 to C4 is 1.40063, C4 to C5, the bond length is 1.36601, C5 to N7, 1.33525, C5 to N12, N 1.40230, C14 to C8, 1.40190,
N12 to C15, 1.47018, C17 to C18, 1.40438. Bond angle of 1-benzyl 2,2-phenyl aminothiazole 4-vial benzimdazoles. The bond angle is of the benzimdazole ring which contains sulfur, carbon and hydrogen. The bond angle is 113.52317. Nitrogen, carbon, 115.77048 in thiazole ring. Carbon, carbon N 121.35150 in benzimdazole ring.
Can you hear?
Ma'am.
Okay, the table we can see. You can go to the next slide and explain the results. Okay.
HOMO structure of 1-benzyl 2,2-phenyl aminothiazole 4-vial benzimdazole and the LUMO structure of 1-benzyl 2,2-phenyl aminothiazole 4-vial benzimdazole. Under molecular orbital analysis, the highest occupied molecular orbital is HOMO and the lowest unoccupied molecular orbital is LUMO. HOMO to LUMO energy is calculated B3LYP 631G level and energies of HOMO and LUMO is minus 0.23546 and minus 0.03278 and energy gap is 0.20268. LUMO is an electron acceptor that represents the ability to obtain an electron. HOMO represents the ability to donate an electron. Molecular atomic charges of 1-benzyl 2,2-phenyl aminothiazole 4-vial benzimdazole. Ion spectra of 1-benzyl 2,2-phenyl aminothiazole 4-vial benzimdazole. The IR spectra of 1-benzyl 2,2-phenyl aminothiazole 4-vial benzimdazole. The aromatic structure show the presence of carbon to hydrogen stretching. The frequency is 3600.32 and carbon to nitrogen stretching 336.1. Carbon double bond nitrogen bending 1672.40. Carbon to carbon bending 1072.40. Carbon to sulfur stretching 875.48. Nitrogen, carbon and hydrogen bending 478.18. Nitrogen to hydrogen plane bending 489.40. Carbon to hydrogen stretching 1036.58. Carbon to carbon bending 456.7. Conclusion: the optimized structure of 1-benzyl 2,2-phenyl aminothiazole 4-vial benzimdazole was identified using Gaussian 09 software packages. The molecular structure analysis and vibrational frequency of the fundamental modes of the optimized geometry has been determined using DFT calculations. The lowering of HOMO and LUMO energy gap explained the eventual charge transfer interaction takes place within the molecules, and it showed the titled compound is bioactive. Thank you.
So the bond angles and bond lengths, these are calculated values, or did you compare it with the actual X-ray crystal?
Calculated, sir.
Say it again, calculated values? Are these calculated values?
Yes, sir. From the calculated values.
And did you compare this with the, if that crystal structure is available? Are they compared, the values?
I can't be able to hear, sir.
No, I'm asking you, if the actual crystal structure is available, did you try to compare the experimental values with the calculated values?
No.
If not the crystal structure,
just only I started, sir. I didn't compare.
Okay, so this compound is known. Is it prepared in lab already?
Yes, sir. Yes, sir.
Okay, so did you at least compare the IR spectrum, the theoretical spectrum with the experimental spectrum?
The result did not come, sir.
No, which result? You said you have made this compound, isn't it? Have you made this compound in the laboratory? No? Okay, so any other questions?
Anushafer, hello, can you hear? Can you hear me? I don't know. She is not responding. So we can move to the.
She's there, but no
Yeah,
response.
maybe network issue. So then maybe we can go to the next speaker.
Okay, next person is Vaishnavi.
Yes. So I need the previous person to remove. Yeah, sure, I can add. Is my PPT visible?
Yeah. Yes.
Okay. So good afternoon. I'm Vaishnavi. Topic of my presentation is conversion of bio-derived furfuryl alcohol to furfuryl acetate over various solid acid catalysts, followed by adsorption studies using DFT.
Can you go to presentation mode?
Hello, sir.
Can you go to presentation mode?
It is in the presentation mode, sir. Is it not? Is it proper now, sir?
Slideshow mode, you can try.
No, I think sometimes it happens. That's okay. You can continue. We can see the slides. That's okay.
File is too heavy. It's better to see to present.
Okay, so today 3/4 of the energy resources depend on fossil fuels, which are natural gas, oil, and coal. As we all know that the fossil fuel concentration is depleting, we have to find an alternative source of energy, which is biomass, where forest residues and non-edible agricultural waste can be substituted for petrol, oil, or chemicals. And this is sort of a green and sustainable.
Sorry to interrupt. Can you go to the editing mode? And then whenever you want to go to the next slide, you have to click it. If not, we won't be able to see. Okay. So now, so you keep it in this mode and then, now it is visible.
Sure. Okay, sir.
Okay. You keep it in display and then present.
Okay. So as I told, this biomass can be an alternative source of energy for fossil fuels. Biomass is derived from biological matter that can be converted into energy. Components of biomass is agriculture, forestry, and waste. So here we have analogous model of conversion of biomass feedstock to final products, which involve 6 major steps, where starch, hemicellulose, cellulose, lignin, oil, protein are converted into various chemicals, in which building blocks is a major step, where furfuryl is one among the 30 most potential candidate, where it can be transformed into various secondary chemicals involving various functional groups that can be again transformed into intermediates and final products. So furfuryl, which when converted into furfuryl alcohol using hydrogenation, this furfuryl alcohol also becomes a potential chemical where it has various application in resins, biofuels, or additives, fragrances, and in the synthesis of various platform chemicals. So my transformation is conversion of furfuryl alcohol using esterification to furfuryl acetate using solid acid catalysts. So the application of furfuryl acetate is, they are mainly used in flavoring and fragrance industries, and also it has a potential application as a biofuel, which is yet to be yet to be explored. The literature where using this conversion, we have only 2 catalyst system reported. One is natural Montmorillonite clay, which is one of where furfuryl alcohol is one of the alcohols among 30 alcohols studied, and acetic acid was used as a starting material. So thorough studies for this reaction is not done in this objective, where a natural Montmorillonite clay was used, yet they could achieve a yield of 65%. Another report is ion exchange with heteropoly acid encapsulated in MOF, which is Ziphate, and they could achieve a yield of 78%.
It's not moving.
Yes, ma'am. Is it proper now?
Now it is on. We are on the second slide only.
Now, ma'am?
Are you keeping it in the editing mode, not in the slideshow?
Yes, sir.
Can you actually go and click that particular slide?
Right now, which mode, which slide?
Now we are in second one, introduction slide.
Okay. So is this the next slide is available?
No.
Yes, now we can see.
Now it's available.
Okay, I'll do like this.
So
okay,
you have to do like this. Okay.
Now it is available.
Okay. So now So next, okay, here I have already told about literature studies. Now, in the catalytic activity study, I have screened various catalysts with various physicochemical properties where zeolites such as H-beta, Y-zeolite, ferrierate was used, silico-aluminophosphate is SAPO11, and mesoporous material sulfated zirconium ALSP15, and one amberless 15, which is a macroreticular polystyrene resin. All these catalysts with different physicochemical properties were screened to come into conclusion which nature of active site is responsible for this transformation, which was not claimed properly in the previous literatures. And the reaction was done in batch mode, and the product analysis was done by GC and GCMAS. The typical synthesis of sulfated zirconia, one of the catalysts was done by precipitation method, and where various molar solution of sulfuric acid was exchanged with the zirconium hydroxide to get Bronsted acidity, followed by calcination. The sulfate species were found to leach, hence to avoid this issue, the leachable physisoft sulfate species were washed by washing the material at 80 degrees Celsius for 6 hours, and the final material was represented as sulfated zirconia X molar, which is sulfuric acid concentration, which W represents washed. And other materials, SAPO11 and ALSP15 were synthesized using the reported literature. H-beta, ferrierate, amberless 15, Y-zeolite were procured commercially. The XRD pattern of all the materials have matched with the literature, reported literature, even in the case of sulfated zirconia, where with increase in sulfation from 1 molar to 4 molar, in specifically 2 molar wash, 2.5 molar wash, and 3 molar wash, there was a presence of monoclinic peaks coming along with the tetragonal peaks. This is due to the a moderate amount of sulfation done during the process of the synthesis. Same image also was obtained for the same, and the nitrogen adsorption isotherm were obtained for all the screen catalyst, where amberless 15 showed macroporous porosity, ALSP 15 and ALSP 15 showed type 4 isotherm with H1 hysteresis, ferrierate, Y-zeolite, SAPO11, H-beta, all these zeolites, and silico-aluminophosphate with SAPO11 showed microporous material, which is type 1. The case of sulfated zirconia, all the material showed H2 hysteresis type 4 H2 hysteresis, and the particle size was around 5 nanometer. Again, when it comes to I have presented all the data with respect to surface area and acidity with weak, moderate, and strong integrated data. Here, all the zeolites had very good surface area, around 800 to 700 meters square per gram, and sulfated zirconia and amberless 15 had very low surface area, which is and also the acidity in the case of all the zeolites. When it comes to strong Bronsted acidity, it was too high, wherein in the case of ALSP 15 and sulfated zirconia, the acidity ranged over the distributed over the range of temperature. Here we have TPD profile, where it can be clearly seen how the sulfated zirconia has acidity ranging over is distributed over the range of temperature. So the sulfur content has come into is complementing the acidity value of the sulfated zirconia. We can see here in this plot. Next is catalytic activity screening and comparison of all the catalysts tested. Here, amberless 15, when it comes to furfuryl acetate yield, gave a highest furfuryl acetate yield around 18 at 70 degrees Celsius, reaction at 4 hours at catalyst concentration of 1.58%. And the issue is furfuryl alcohol usually polymerizes in the presence of temperature and high acidic sites. So to get rid of this polymerized species which are undesired, we have to burn off them at high temperature. Amberless 15 has thermal stability of 120 degrees Celsius, which makes it not so good catalyst. So next best catalyst is sulfated zirconia, which was chosen for the other studies. Surprisingly, this zeolite showed lower furfuryl acetate yield because though it had given competitive conversion, the selectivity towards furfuryl acetate was reduced because of the formation of these polymerized products called humins. So it can be concluded that from this study that mild acidity is required with mesoporosity and high thermal stability to be for the catalyst to give a very good furfuryl acetate yield. Next, optimization study for the for sulfated zirconia was done, where effect of sulfation was done with various sulfuric acid concentration post-washing. So, after calcination, the material was washed. So it was found that for sulfated zirconia 2.5 molar material gave.
Your time is up. You have to be quick.
Yeah. So
Conclude.
that was done. Effect of sulfation, temperature for reactant mold ratio, catalyst loading was done, and optimized results were obtained. And the recyclability study was done. As the physisorbed material was washed away, there was no issue of leaching of the material. So the catalyst gave excellent recyclability studies, and ferroelastic yield on time result study was 95%. So, according to the catalytic performance in respect to turnover number, sulfated zirconia, SACO 11, ALSP 15 had 126, 75, and 49 TO number respectively. Hence, these three catalysts were studied to get the adsorption energy using DFT. So, DFT calculation was performed by ORCA, model building was done by Avogadro, mode of calculation was single point energy. DFT calculations were performed using B3LYP function and LAN L2DZ basic sets, and for three best catalysts, which is shown here in the case of turnover number, sulfated zirconia, SACO 11, and ALSP 15, where all these three catalysts have different nature of active sites. So the calculations were done by comparing the adsorption energies for each substrates using this mechanism, reported mechanism. So here we can see the comparison of adsorption energy profiles with different catalysts. As we can see here, sulfated zirconia, which is in the red color, has given the lowest adsorption energy, followed by ALSP 15 and sulfated zirconia. Sorry, SAPO 11. This shows that among the three best catalysts screened, sulfated zirconia has supported the result. There is this experimental results, and sulfated zirconia had least adsorption energy profile compared to the other two best catalysts. So this is a supporting data obtained for the experimental result. Also, energy to remove one hydrogen was calculated for all these catalysts, and it was the trend was energy to remove is highest for ALSP 15, followed by SAPO 11 and sulfated zirconia. Sulfated zirconia had least energy to remove protons, which means sulfated zirconia is a better, stronger acid compared to SAPO 11 and ALSP 15. Even this result obtained from DFT calculations has supported my catalytic performance experimentally done. So the adsorption energy profiles and energy to remove hydrogen has all supported my experimental results. Summary and conclusion is various solid acid catalysts were screened, zeolites, silicoaluminophosphates, resins, mesoporous materials, etc., where all these had different nature of active sites. So it could be concluded at moderate number of acidity and even weak and moderate strength of acidity, high thermal stability and mesoporosity are the optimum qualities required for the catalyst to get a high ferroelastic yield, which is around 95% at very less catalyst concentration and very low ferro alcohol to acetic acid mold ratio. There was no leaching issues found, and also the catalyst could be recycled for 4 cycles. DFT calculations were performed for the adsorption studies which supported the experimental data. So we can conclude that sulfated zirconia is a potential candidate as it has shown the best catalytic performance at the most desirable reaction conditions. So this promotes the green chemistry principle. Thank you.
Thank you, Vaishnavi.
Yes.
I think we can have only one question, if anybody.
Vaishnavi.
Yes, sir.
Good work. You are done with the catalysts like sulfated zirconia with other catalysts like zeolite and other things.
Yes, sir.
Okay. What was the calcination temperature of sulfated zirconia?
Sulfated zirconia was calcined at 650 degrees Celsius, sir.
650.
Yes, yes. So monoclinic phase is about we will observe monoclinic phase. But when we sulfate it, we get tetragonal phase, sir. Because this.
That's what I am asking. That what is the after sulfated? What is the calcination temperature?
650 degrees Celsius, sir.
650.
650. 650.
Yeah, I understand. 650 is too high, isn't it? Because temperature is supposed to be 400. I know that it's if you calcine more than 400, you will get a monoclinic phase.
Yes, sir. Sir, below 500, sir, we have amorphicity, sir. More the catalyst material will be more amorphous. So when we go above around 550 to 650, crystallinity is observed with the change in the phase from tetragonal to monoclinic, sir.
But you are comparing with one is a superacid, that is a sulfate is considered as a superacid.
Yes,
Okay.
sir.
And zeolite.
Yes.
Zeolite beta both have the similar acidity. But
Yes,
your
sir.
DFT calculation, you are comparing with the best active catalyst is you are mentioning that aluminum SbA15 and SAPO 11.
Yes, sir.
But both aluminum SbA15 and SAPO 11 are known to be a weak acid or moderate acidic nature. It is known
Yes,
to
sir.
be. So why you are not comparing with the zeolite beta or any other zeolite which are embellished?
Yes, sir.
Why you are
basic.
not compare and what is because their acidity will be very close to sulfate zirconia.
Yes, sir. Then actually, when we see, yes, sir, when we see the number of acid sites, sir, they're all similar. SAPO 11, AlSp15, and sulfated zirconia have around 0.20 millimole per gram, wherein the other zeolites have nearly 1.06 acidity, sir. What we found is the strength of acidity above 350 degree, it is dominated in the case of zeolites, wherein it is, in the case of sulfated zirconia, AlSp15, it is distributed, sir. So the strong Bronsted acidity in other zeolites, in SAPO 11 are less compared to H beta or Y zeolite. These will contribute to polymerization, which will reduce the performance of the catalyst, because these polymerized products will saturate on the active sites and lead to the active site saturation.
Yeah, I agree with that. My concern also same that since you said that strong acidity, normally I agree that perforol will go for polymerization.
Yes,
why
sir.
not it's happening in the sulfate zirconia? This is what I might concern.
Yes, sir. Because the number, say the total number of acidity and also the strength is lower compared to zeolite, sir. When we integrate this with respect to in the TPD profile, we can see, sir, here I have shown sulfated zirconia and AlSp15 have lower.
You have followed the acidity with the help of the only ammonia TPD.
Yes, sir. Yes, sir. Yes.
Have you followed with, because there is also another concern, you know that very well. There is a pyridine absorption which helps for the understanding that whether the nature of the acidity, whether it's
Yes, sir. We can differentiate Lewis acidity and Bronsted
acidity. Have you ever
acidity.
tried to understand that what is the nature
Yes,
of
sir. Yeah, I have done 2 to 3 samples for pyridine FTR, sir, because the number of acidity, active acidic number in the sulfated zirconia is very low, 0.20, sir. So it is very difficult to differentiate those two. So I thought I'll mask these Bronsted acid sites using some masking agents and perform.
We cannot say that. Even the small, even the less than 0.1 millimole of acidity is there also, we can distinguish with the help of pyridine IR.
Yes, sir.
Pyridine IR is a wonderful technique. I mean, I'm not that see, I agree that there is a difficulty, but then we cannot say that we cannot distinguish. Okay. So because
sir, that we can.
You have the, see, your TPD shows the very good acidity, sulfate zirconia. And another thing is with the sulfate zirconia, we have what is the concentration of sulfur favor the more
content?
Yeah, sulfur concentration.
Yes, sir. See, I have done this ICP-OS analysis. I have showed the data, sir.
No, I'm not asking about ICP analysis. What is the molarity of sulfuric acid which you have used in
sir, I have started from 1 molar, and 1 molar, 2 molar, 2.5, 3 and 4. Interestingly, though the sulfuric acid concentration exchange was 4 molar, I didn't find any destruction in the material with respect to XID or difference in any porosity. So the sulfated zirconia was very resistive for the activity on this overloading of sulfate species, sir. It had retained its structure over higher concentration of sulfuric acid washing.
So higher concentration, is it retained the structure or?
Retained, sir. That's I have shown in XID.
But then I understand, but I understand because my question is, which is the best catalytic activity among the various concentration which you have used in that? That's not my question.
Yes, sir. 2.5 molar washed material, sir, which comes between 2 and 3. This had given very good results, though it had both monoclinic and tetragonal phase with respect to XRD. These peaks didn't have any significant effect on catalytic activity, yet this optimum value of 2.5 molar washed
no, you cannot say that like that because have you ever tried with purely monoclinic system?
No, sir, I have not tried it, sir.
Yeah. Without that, we cannot say that it is no role. Okay, it is a heterogeneous system. We cannot say that no role.
Yes,
and
sir,
the
yeah.
leak doesn't have any role. We cannot say that. There
Sir,
are-
yes, sir. This 1 molar sulfated zirconia, we can see which I've represented in green color. This and 2.5 molar sulfated zirconia gave same result, sir. But the 1 molar where sulfate species leaches, here 2.5 sulfate.
all that catalysts were calcined at 600 degrees centigrade. That is also matter. Anyway,
Yes, sir.
that we are before saying that there is no role, we have to see that what is the percentage of combustion and other things.
Yes,
okay?
sir. Yes,
Fine.
sir.
Anyway,
Yeah.
all the best.
Oh, thank you, sir.
Others can if anything.
Okay, maybe I think we can stop because it's already 3:35. Okay, so we'll close it, sir. Or is there any other questions?
Sir, all the presentations are over.
Yeah, if all presentation over, I think Dr. Naveen and Dr. Deepa madam, you can discuss. I have shared the phone number. Dr. Deepa madam is there?
Yes, sir.
So I shared the phone number, madam, with so you can discuss that best presentation. You can.
Okay. Okay, sir.
Thank you. Thank you.
Yes, sir. Yes, sir. Thank
To
you.
all of
Thank
you,
you.
request to keep remain another 15 minutes. We will be starting the keynote lecture. Next keynote lecture by the Dr. C.S. Kobina sir from NCL Pune. So all of you keep remain. Okay. Thank you. Thank you, Dr. Naveen, for a kind help.
Thank you, sir. Thank you very much.
Thank you, Nimisha, for a kind coordination.
Thank you, sir.
இல்ல பார்த்தேன் நான் பார்த்தேன் Dana? Dana, are you there? Dana? Dana, are you there? Hello? Hello, can you hear?
Yes, sir.
Dana is here?
Sir, I
Dana
think she
Sushant?
has some network issue.
Yes, sir. Now I can hear.
Now she has come.
Okay.
Okay. So shall I start?
No, wait. You are ready. That's what I just want to ask you.
Okay.
Okay, fine. I think Gobinath sir will join in another 5 minutes.
Good evening, Saktivel.
Yes, sir. Good evening, sir. How are you, sir?
Good, excellent.
Yeah. Thank you very much, sir, so much for joining us with us. We have completed oral presentation. We had around 30 oral presenter also. So
By
today,
student.
yeah, by the research scholars and some faculty, college teachers. So around 15 we completed.
Okay.
So after then evening also there is a oral 5:30 also.
In fact, I am co-author of one of the poster.
Yes, sir.
I am co-author of one of the poster.
I saw, sir. I saw, sir. Thank you for sending your student also. It's, morning we had Dr. Ashok Ganguly and A.K. Tyagis and Professor Sambat had.
Okay.
So thank you. So our colleagues all are there. Dr. Bakishmi, Dr. Binijaj. Anyway, they all met you when we were there.
Good evening, sir.
Good evening, Vidhi madam.
Yeah, good evening, sir.
So you will be sharing the session.
Sure, sir. So can I?
Yeah. Just a few minutes, sir. We will start in just a few minutes.
Sure, yeah. Maybe I'll just share my presentation.
Yeah.
That things are okay.
How is everything at NCL, sir? Now they started?
Yeah, now we are doing okay, and so I hope you can see.
Yes, sir. Yes, sir.
Yes, sir. We can see.
Right? You can.
It's moving. Yes, sir. It's fine, sir. Perfect, sir.
Good. Yeah.
I think
here it is okay. I mean, now I think Maharashtra has improved. Now Kerala has to improve.
Yeah, I think Kerala no problem, sir. I think they are testing more. So it's people are taking care. So they are testing more. That's main concern. Fine. Okay, sir. I think Dana, are you ready?
Yes, sir. Yes, sir.
Bhagesh, madam. Shall we start? Group, sir?
Yes, sir. Yes, sir.
I think Swaminathan sir said that carry on. He is the ISCA's president.
Okay, sir.
Fine.
Good afternoon, sir. Gopinathan, sir. Good afternoon.
Good evening, yeah.
Sir, shall we start?
Yeah. Dana, please proceed.
Yeah. Good evening. Moving on to next technical session. The technical session 4 will be chaired by Dr. Bini George, Assistant Professor, Department of Chemistry, Central University of Kerala. She has been the former faculty in Applied Science Department, St. Francis Institute of Technology, Bombay. She has also gained international industry experience as chemist and quality assurance representative in UAE. She has been recipient of Young Scientist Award of the State Committee of Science, Technology and Environment by Government of Kerala. Her research interests include polymer chemistry, nanochemistry, and organic synthesis. I welcome ma'am to share this session.
Thank you, Dana, for this. For me, this much introduction is not needed here. And first of all, I congratulate Professor Shaktivel, the organizer and the co-convener, Dr. Bhaglashmi, for organizing this program and giving me an opportunity to chair this session. It is my immense pleasure to welcome and introduce Dr. C.S. Gopinath. He is a chair and chief scientist of NCL Pune. For the Department of Chemistry, Dr. C.S. Gopinath doesn't need any introduction because he was here with us in 2019, and in the first seminar for the catalysis workshop, that day itself, sir offered all research help from NCL Pune, but due to COVID pandemic, our students couldn't utilize that. Still, I'm remembering that the first time he offered this. And for the newcomer students and for the participants, I would like to introduce sir. Sir got his PhD from IIT Madras in 1993, and he has joined in NCL Pune in 2000, and he's initiated serious research in surface studies, especially photo emission studies, catalysis, inorganic, polymeric, magnetic, and electronic materials. And currently he is the head of the Center of Excellence and Surface Science in NCL Pune. And yeah, sir has the main thing I have noticed in his areas of expertise, catalysis, material chemistry, and nanotechnology. And they are the bridging the material gap between industrial catalysis and surface science that I have noticed. Okay, that in that everything will come. Okay, and sir has received many awards. He is elected fellow of Indian Academy of Science, Bangalore in 2011, and he was a visiting professor of University of Lille, France in September to November 2010, and also awarded professorship there. And he was a recipient of Humboldt Fellowship in 1995 and recipient of Bronze Medal of CRSI 11th National Symposium of NCL Pune in 2019 and recipient of the Scientist of the Year Award from the NCL Pune in 2006 and Dr. S.S. Deshpande National Award from Holkar College in 2013. And coming to his professional and major accomplishments here, as I have already said, he has initiated from that catalysis from 2002 and currently the head of the Center of Excellence and Surface Science in NCL Pune. And his main project was a fabrication of molecular beam instrument, and that was a collaborative project between NCL Pune, India and Fritz Haber Institute, Berlin. And that molecular beam instrument is fully developed independently by their group and employed the vapor phase and reactions in metal surfaces. And they have developed many new materials for solar energy harvesting through water splitting and for DSSC materials. And he has collaborated with many international scientists from USA, Germany, France, Japan, Korea, Australia, and several prestigious institutions in India. And coming to his he was a member of the many editorial board members of Journal of Chemical Technology, editorial board member of Journal of Chemical Sciences, Springer, and he has many research publications, and he in an year he will review almost 50 articles here, and he is a member of many this one RSC or many scientific journals or scientific societies, and he has supervised more than 25 research students, and his citation index is 6,900, and he has more than 2,220 research papers and H factor of 48. That he gives his research output. And with this short introduction, sir, I welcome you to deliver this solar energy conversion through photocatalysis with specially designed nanomaterials for this webinar.
Thank you very much, Vinny Madam. That's really a very long introduction. And,
sir, you deserve it.
Thank you so much. Actually, I hope you all can hear me very clearly, right?
Yes, sir. We can hear it, sir.
Okay.
Professor Swaminathan, ISCA president also is here joined.
Oh, very nice.
Okay. Oh, I forgot to mention about the process. Morning he was there.
Good morning, sir. Good afternoon, sir. Good afternoon.
Yeah, good evening. Yeah, good evening. So now it is more than 4 o'clock. So, so good evening to all of you. So let me start my talk. In fact, in yesterday's speech, actually, our Prime Minister Modi actually, so he informed that government is going to start that national hydrogen green hydrogen mission. Actually, in fact, the present government has realized the importance of hydrogen. Actually, so that's one thing I want to first underscore. Actually, and they are also ready to invest money in this particular area. Actually, which is going to be going to take up in a big way very soon. Actually, in fact, the rest of the world actually. Good amount of hydrogen research is already going on actually, and I believe in India also it is going on actually, but then we have to do it in a big way actually. So I am glad to say that actually CSIR has already announced that we are going to do a hydrogen mission program actually. In fact, I am glad to say that I will be coordinating and NCL will be the nodal lab actually. So Dr. Ashish Lille, who is the present director, who will manage the entire program actually as a nodal director. So I am really glad to be associated with that. So with that brief introduction, let me jump to the topic of my talk actually. In fact, my group has been working in the photocatalysis of water splitting for, I don't know, maybe about 7-8 years at least. In fact, we put a lot of efforts in the beginning actually, right from 2009, I would say actually. So we have been doing a lot of work actually, but from 2014-15 onwards, we are kind of successful, and now we are publishing regularly in this particular area. Actually, at least a couple of papers every year we are publishing. So I can see that there is very good potential, especially in terms of India. I mean, if I have to say, actually, India is blessed with the solar energy throughout the year actually. For at least 80 to 90% of the days are really sunny across India in several states, and so we need to, it is high time that we need to make use of this solar energy for chemical conversion also. Already India is doing a pretty good, I mean, it has invested a lot in photovoltaics actually to capture sunlight and then convert into electrical energy. But then that's one part, and in fact I must tell you that to all the students also, that the contribution of electrical energy from solar photovoltaics to the grid, actually central grid, actually it is going to increase, and it is going to increase in a very tremendous way actually. So it is high time that we should make use of this energy for chemical conversion also. So my talk is going to be centered around that particular aspect actually. So all of you, I'm sure, know about the photosynthesis, or at least heard about the photosynthesis. So on the left side, if you see the photosynthesis, mechanism is briefly given actually. So in the first step, light from solar light is absorbed by the, there are so many light absorbing components are there actually, and then water is split into oxygen, and then the hydrogen and the electrons are stored in NADPH. Then the stored hydrogen is actually utilized in the Calvin cycle, which is the dark reaction, to hydrogenate carbon dioxide into sugar and sugar molecules. So this is basically about that photosynthesis. So here the first step is going to be really, really critical. Of course, second step is also critical. I don't deny that actually, but then the first step actually provides the essential hydrogen, what is required for the hydrogenation of carbon dioxide. Okay, so this is very, very important. Basically, I mean, these are all redox reactions, during the excitation, I mean, sunlight, maybe please ask everybody to mute their mic actually. Yeah.
Sunny, can you mute all of them?
Yeah.
Sunny?
So, yeah. So,
hello. Yes, sir.
Can you mute all of them?
Okay, sure. I'm doing that.
Okay, thank you.
Thank you, Sunny. Yeah. Okay.
Sorry, sir.
No issues. Yeah. So here actually the critical thing is actually, I mean, whatever amount of light is absorbed, so each photon absorption excites an electron from valence band to conduction band. So that's what happened. And then whatever excited electrons has to be utilized properly, because one electron utilization mean, I mean, 2 electron utilization mean we will able to generate 1 hydrogen molecule actually. So that's the fundamental parameter here actually. But then unfortunately the natural photosynthesis works at only 1% efficiency. That means 100%, if 100 photons are absorbed, only one photon excited electron is actually utilized. So that means, still the natural photosynthesis works at an efficiency of just 1%. Indeed, it works at 0.9%. It is not even 1%. Okay, so that is the reality. But then, how can we make use of this concept to split water and then produce hydrogen in a substantial amount? That is the challenge actually. So here actually I am going to restrict my talk to how nanomaterials can help achieve efficient water splitting to hydrogen is the central theme of my talk actually. So in fact I am going to introduce at least two aspects actually. One is actually how nanomaterials can be used, and then in what form we have to use. Okay, so these are the two key things I am going to convey today actually. In fact, all of you or at least most of you probably know that the photocatalysis of water splitting was announced way back in 1972 by two Japanese researchers way back in 1972 actually. So this is the particular slide what I am showing actually. So here actually, in fact, this is the photoelectro chemical concept actually, where the titanium electrode is shine with UV light, which has a wavelength of less than 415 nanometer. So while shining UV, actually there is an electron excitation happens from valence band to conduction band, and the electron flows through a small applied bias potential, and then it reaches the platinum counter electrode where the water splitting happens and the hydrogen is generated. I mean, in 1972, you can imagine that a very small amount of hydrogen was, shown actually. So this was, kind of the first proof of concept was demonstrated by two Japanese researchers, and their names are known as Honda and Fujishima. Okay. Now, actually, even after almost 49 years are over, and we already entered into the 50th year of the discovery of the photocatalysis of water splitting actually, but even now actually we are nowhere closer to commercializing this actually, and not even commercializing. I mean, there is I would say that no significant progress, I would say actually. I mean, there is some progress is there, but then it is not to the level what is expected in a period of 50 years actually. That's what I want to underscore actually. So what is desired is given on the right side. I mean, we have plenty of sunlight and we have water also, and our job is only to produce a good photocatalyst which can absorb sunlight and split water to produce hydrogen. So this is, in a cartoon wise, it is shown actually, though it is shown in a very simple way, but it is an extraordinarily challenging reaction. I must say that actually. In fact, a breakthrough catalyst. I mean, if somebody can find a catalyst that can split water at a very efficient level, and which is also sustainable and which can work for years together in direct sunlight, nothing like it actually. I am sure that will be at least considered for Nobel Prize. So that the importance of hydrogen actually lies in in influencing the economy actually, because right now our economy is based on all the carbon fuels actually, see petrol, diesel, all these things actually. So whenever, I mean, all of you realize that whenever there is an increase in petrol or diesel price actually, all the other commodities price also increases, because transport depends on petrol and diesel. So not only that, petrol and diesel, when you employ, actually you are going to produce a lot of carbon dioxide. Okay, so that's the very worst thing what we are already doing. Actually, we need to stop somewhere actually. So this is the place where hydrogen is going to be very important actually, because hydrogen, when you burn, you are going to get energy and only water as the side product. So you are not going to harm atmosphere in any way actually. So that's the best part of it actually. Okay. Why hydrogen energy from renewables is important? Hydrogen gives, when we burn hydrogen actually, it gives 120 megajoules per kilogram compared to about 44 megajoules per kilogram of petrol actually. So you can see that easily 3 times higher energy we can get from 1 kilogram of the hydrogen fuel. And then, as I said, actually it is ecologically neutral, because when we burn, it gives energy plus water only as a side product. Hydrogen is also safe actually. In fact, we are all happy to load our cars with a compressed natural gas cylinder actually. Still we drive and we don't mind actually, but then people don't want to put a hydrogen cylinder actually. We all still consider that hydrogen is a bomb. Actually, it is going to explode very fast, but that's not correct actually. In fact, the city of Paris actually, they particularly load the cars with hydrogen cylinders, and then it is available in the central city of Paris actually, just to get rid of the fear that hydrogen is not a bomb, it can be employed safely. Okay, so of course you need to employ safely. So that's one thing I want to convey. But hydrogen has to come from renewable resources such as solar energy, wind energy. So currently, actually, hydrogen is generated from reforming technology, steam reforming technology, which converts, for example, methane or methanol or whatever. Actually, one of the carbon containing hydrocarbon actually use and reform to get to hydrogen actually. For example, methane reforming actually, you can produce about 5 to 6 gram of hydrogen. For every 5 to 6 gram of hydrogen what we produce, we add 44 gram of carbon dioxide to the atmosphere. So can you imagine that for the 5 to 6 gram of hydrogen, we are adding 44 gram of CO2 to the atmosphere? Because it is, we don't realize, because there is no smell, there is no color attached to carbon dioxide. So we are happily allowing carbon dioxide to add to the atmosphere actually, which is, causing all problem actually. There is too much rain or too much drought, sometimes fire in some parts of the world actually, all are due to the, too much amount of carbon dioxide now. Because as of today, the carbon dioxide level in the atmosphere is, it has crossed 415 ppm, if I'm correct. And the world is desperately trying to stop that, excess addition of carbon dioxide, because, otherwise, actually, in the next 20 to 30 years, actually, the average temperature, actually, the pre-industrial revolution, actually, what was the temperature? From there, actually, we have already added about 1 degree. And it is moving towards 1.5 degree actually. So that increase in global temperature is going to cause a lot of problem actually. So that the whole world is trying to stop that to whatever extent possible. Okay. Having said that, actually, let me move into the, a little bit of fundamentals actually. So here actually the water splitting reaction actually, if we have to do by, thermal methods or even by any heterogeneous catalysis method, actually, the amount of energy involved is going to be really, really high. So for example, the pure thermal method, actually, the splitting of one one OH bond from water, the gas phase form of water to, OH plus hydrogen, that itself requires about 495 kilojoule per mole. And then to split another OH bond, you require almost another 425 kilojoule per mole. So, you can imagine that, this much amount of energy, if I have to provide, I have to heat water molecule to a temperature around 1500 degrees centigrade. So is it really worth doing that? So by thermal method, it is not possible unless you get that heat energy freely. So water splitting is basically an uphill reaction. Also, backward reaction should be prevented because, water is more stable than your products of hydrogen plus oxygen. Okay, so that's the important thing. But then how plants are doing this water splitting very, very nicely. If you see the bottom picture actually and the photosynthesis, so here you can see that actually the moment water splitting happens, the oxygen is let out to the atmosphere. So there is no chance of hydrogen and oxygen recombining. Not only that, the hydrogen what is produced is stored in NADPH, and it is utilized when it is needed for the carbon dioxide reduction. So these are the two best things with the natural photosynthesis. But while in the artificial photosynthesis, what we are trying to do actually, here actually we are, if you see this curve, actually first thing is actually it is endothermic. So delta G change is positive. This is a positive actually, plus 237 kilojoule per mole actually. So this is the endothermic reaction. So that is, that means your products are less stable than the reactant. So a good catalyst, what is catalyzing water splitting in sunlight, can also do the reverse reaction. Okay, so that's the first thing. So that means, you need to separate the products very quickly. So that's one of the very, very important thing. So nature works at very low quantum efficiency of 1%, and there is a lesson to learn. Okay. So let me just introduce a few more points actually. So photocatalysis can be defined as the reaction assisted by photons in the presence of a catalyst, usually a solid catalyst. Of course, there are, homogeneous catalysts are also available actually, but then, then there are other problems with homogeneous catalysts, which I don't want to go right now. It is basically a conventional redox reaction we can call, because, we produce, we excite an electron. So an electron and hole is available. Electron is available for reduction and the hole is available for oxidation. So basically a simultaneous oxidation and reduction reaction occurs. And the redox couple capable of promoting both the reaction. And titanium and zinc oxide is the most employed catalyst actually, but it can absorb only UV light. So there are many efforts to make it as a visible light absorbing catalyst. Actually, there are many efforts. So I will not go into that. Also, various methods have been tried to improve the visible light absorption. So now we'll go slowly in deeper and deeper. So now what I'm showing is the sunlight, the spectrum of sunlight. So this spectrum of sunlight actually, I mean, the everyday sunlight, what we are, what we are using actually, it contains about 5% of UV. That means below 400 nanometer, somewhere between 300 to 400 nanometer, but essentially it is between 370 to 400 nanometer. Between 300 to 370 nanometer, there are photons actually, but very, very small percentage. And then the visible light, 400 to 800 nanometer actually, so which contains all the VGR photons, about 45 to 47%. And then the rest is near IR and IR. Okay, so this is what the composition of sunlight. And here, I mean, invariably for photocatalysis, we use a semiconductor, solid semiconductor actually. So this works on the basis of the principle of, excitation of electron from valence band to conduction band, which is, given by the excitation of electron from the orange curve. And then this green arrow shows the band gap of the material. And then it should also have a minimum requirement of, the conduction band minimum should meet the hydrogen reduction potential. And then valence band maximum should meet the water oxidation potential, which is about 1.23 volt. So these are the minimum requirement actually. I mean, these are the bare minimum I would say, but then there are, of course, there are many other parameters. I will go into the detail later. So to pictorially show what happens actually, there are many semiconductors, materials are available which can absorb sunlight. Okay. So when the sunlight falls on the material, there is an electron excited from valence band to conduction band. So an electron and a hole. So hole mean, there is nothing actually. I mean, absence of electron, we call it as a hole actually. So this electron and the hole pair is generated in the first step on absorption of sunlight. Okay, so that's the first step. In the second step, actually, this electron and holes has to be separated to as far as possible towards the reaction sites. So that is going to be the very critical thing. If it recombines, there is no job, because when it recombines, it simply leads to fluorescence. Okay, so fluorescence is not going to help us actually. So we have to work on generating or producing a material that will minimize the recombination and to enhance the separation of electron and holes towards the reaction site. Okay, so that's the critical thing. And in the third step, actually, the electrons and the holes, what is produced, reaches the co-catalyst site where electrons are utilized for the hydrogen generation and the holes are utilized for the oxygen generation. So these are the three key steps involved in any photocatalysis. With reference to water splitting only, I am going to talk actually. So I am going to restrict my talk only towards the water splitting. Okay. So here, as I indicated in a red square, you can see that the second step is going to be really critical, because for the first step, for photon absorption, there are thousands of material available. Then we have very good co-catalysts are also available actually. Even the very cheap co-catalysts are available which can do the reduction and oxidation. So the key step is actually managing the second one of charge separation. When we excite electron, it should not again recombine with hole and so that it goes back to the valence band. So that has to be avoided. So when we excite an electron, actually there is a kinetic energy associated with that. That kinetic energy has to be utilized for the water splitting to produce hydrogen and oxygen. So that is going to be the key step in this particular photocatalysis. So here, so what are the difficulties we have to find out a good working catalyst or breakthrough catalyst? First of all, one material is not going to solve the problem. So that's one thing, because one material, if you can solve actually, it's going to be wonderful actually, but then one material means one band gap. So that means the photon absorption is going to be maximum around that wavelength. But then the sunlight contains UV visible near IR. So can we absorb maximum amount of sunlight across all these three range? So that means one material is not going to work. So you may have to combine 2, 3, or even 4 materials actually. So that's going to be the first thing actually. So that means that itself is going to be critical. The second thing is actually, if we have to combine 2 or more materials actually, how we are going to combine? Because they're all going to be solid shade, powder materials. When we combine actually, there is going to be a lot of barriers actually. Because in fact, I will come to this point little in the next slide actually. A composite can absorb maximum range of sunlight wavelength, that is fine. But however, charge transfer, because once we excite an electron, that the electron has to move from one particle to another particle before it can be consumed actually. Okay, because it has to reach the redox co-catalyst site. Okay, so that means it has to travel to some length actually before it reaches the co-catalyst. So it has to survive for that period. So that's going to be the key. Okay. Then the third is actually, of course, as I said, actually charge recombination should be minimized. So can we enhance the lifetime of the charge carriers? So this is another way of thinking. Okay. And then of course, surface area, crystallinity, all those things are going to be really needed for the high performance actually. But then, when we say too high surface area, then it is going to be, invariably there will be defects, solid state defects. Okay, that's also not good. Too high crystallinity, that means your material, the particle size is going to be too big. That's also not going to be good. So it has to be optimized. So that's another thing. When you have 2-3 photocatalysts and then co-catalysts, all these things has to be integrated electronically. So that's going to be another challenge. Okay. Apart from all these things, actually, the material has to be stable. It should not undergo any, degradation like photocorrosion. Actually, that means your material itself should not undergo any oxidation or reduction. So that is the last challenge. So that the idea is to optimize all such parameters in a workable catalyst. So this is going to be the challenge of the photocatalysis. So the main critical factor that controls the photocatalysis is given here. What I mean is actually, we can see that, upon light absorption, there is an electron excitation from valence band to conduction band. All those things happen actually. So all these red arrows, whatever I have indicated, they all are not good for the photocatalysis. That means it will lead to, recombination. So with all recombination or all factors that enhances recombination, they are all bad actually. So the main issue here is actually, if you see the photophysical process, that is the light absorption by semiconductor, because light is simply absorbed by material, and then electron is excited into conduction band. So this is simply a photophysical process. If you see the photophysical process, they are all working in the range of femtosecond to picosecond to nanosecond. Whereas if you see the photochemical process, they're all working in microsecond, millisecond, and second. So there is a big time gap differences there. Several orders of magnitude of time differences there. So even if it is nanosecond for the photophysical and microsecond for photochemical, actually, at least 3 order of magnitude differences there actually, which is not a small factor actually. So how are we going to connect this? So it is something like, to put it in a very simple language, I should say that actually, we are dealing with powder materials. That means, there are small granules or, particles are there actually that needs to be connected. So that means, see, for example, when we pass electricity through a copper wire or aluminum wire in our house or home appliances, actually, the wire is continuous. Okay, so the electron can flow very easily in a wire. But then the same thing we have to achieve in powder material. If we have to achieve the electron conduction in powder material, they have to be, there should be good quality junction, so that, electrons will not recombine with holes. Wherever there is, breakage between, or not good quality junction, they are going to be, trapped, or they will not be utilized, because they have, please remember that they have a very small lifetime of nanosecond or less than that. So here actually our job is to prepare a nice catalyst actually with good junction properties actually. So that's going to be the key role here actually. So how do we achieve that? So that's one major issue. In fact, this particular slide shows one an important observation. Not to worry about all the details, actually, just concentrate on the blue square what I have shown with 75 milligram. That is 75 milligram of the photocatalyst was taken to do the water splitting, and you see that the quantum efficiency, apparent quantum efficiency, what was reported is 6.3%. They increased the catalyst quantity from 75 milligram to 150 milligram. That is shown in the red square. You can see that the quantum efficiency has come down more than 50%. It has decreased from 6.3 to 2.7%. I mean, see that 75 to 75 milligram to 150 milligrams, a simple doubling of powder catalyst, if it decreases the efficiency, what would happen when you operate at 1 gram and then 1 kilogram? Forget about it. So these powder catalysts are not going to work at large scale at all. Okay, so that's the first point I want to underscore. So how are we going to scale up? I mean, even if you find a good catalyst, good photocatalyst, good powder photocatalyst, how are we going to employ in an effective way? Okay, so that's the predominant question. So this is the point where we started looking at the nature. So if you look at the nature, actually, all the leaves are doing photosynthesis for millions of years very nicely. What is important, actually, you take any leaf, it is a single piece. We can consider that as a thin film, or at least a film, not a powder actually. But I mean, if you look at the microstructure of the leaf, there are so many, holes. I mean, the pores of different size. I mean, nanopores to micro size to macro pores. All sides of pores are available actually, but everything within a single piece of leaf actually. So can we connect our powder catalyst in the form of a film and then do the reaction? So can we do that? So all the photocatalyst component must be integrated nicely in a single piece of device. So connecting particles is important. So we started working towards that. So this slide is particularly to show the microstructure, what is available within the leaf structure. I mean, when the leaf, I mean, practically the leaf was dried and then looked at under microscopy. Actually, you can see that variety of so for example, this leftmost actually shows about 20 micron size, 20 to 40 micron size globules are there, and then 100 microns or somewhere from 50 to 100 micron size pores are there, and even smaller pores are there actually. I mean, the bottom H and I panel shows that it is of the order of nanometer. So that means from nanometer to microns and even several micron actually, I mean closer to millimeters. So that kind of pores are available within the leaf architecture. So one beauty is actually, I mean, once the incident light goes into the inner layers of leaf, actually it will not able to come out actually. So that means once the light absorbs into the leaf, it will be scattered internally and it will be eventually absorbed by the leaf components, and that will be utilized for the photosynthesis. So that is one good part about the leaf. Okay. So let me skip this one actually, because I have completed 30 minutes. So I want to show something important. So here actually, I mean, so though in leaf actually, all the components are connected very, very nicely without employing any wires. Okay, so that's something very important. So how can we achieve that in an artificial device? So what we did is actually we selected a method called CELAR method actually, successive ionic layer adsorption and reaction method. So this is called CELAR method. So what we do is actually we take one of the wide bandgap semiconductor called titanium zinc oxide, make it as a thin film of about 8 to 10 micron. The semiconductor is already porous. Okay, so that's the first requirement we need. And once we make the film, dip that titanium film in cadmium solution, what I have shown on the leftmost column, leftmost picture, first beaker. So once I dip in cadmium solution, a single layer of cadmium ions are adsorbed within the pores from top to bottom of that 8 to 10 micron. Then subsequently, I dip it in sodium sulfide solution. So what happens, wherever there is cadmium, the sulfide gets absorbed and then forms cadmium sulfide chalcogenide. Okay. Once I repeat this process again and again, so I will be able to increase the particle size to the required level. In any case, that particle size cannot exceed the pore size. If the pore size is 3 nanometer, I cannot make a particle size of more than 3 nanometer. Okay, so I am the pore size is restricting the growth of the cadmium sulfide chalcogenide, which is one of the best it absorbs sunlight to the best possible extent. Okay, so similarly, lead sulfide also can be produced this way. So in one of the devices, what we did is actually about 20 cycles of cadmium sulfide and about 10 cycles of lead sulfide we made actually, and it was demonstrated. I will show one of the small video also later. So here what the importance is actually the cadmium sulfide is assembled in the pores. It is not I made outside and then integrated. it is assembled, that is cadmium ions are first intercalated, followed by sulfide ions. So cadmium sulfide forms in the pores. So when it happens, actually, it is directly depositing on the surface of the titanium. So that means when it is directly depositing, the quality of junction is going to be perfect. Okay, so this is exactly what we wanted actually. So to simulate, very high activity. So this way we are successful in creating very high quality junctions of photocatalyst materials. And so now we actually, again went back and analyzed, what is so important about photosynthesis. In photosynthesis, actually, we have, photosystem 1 and photosystem 2. They are, they absorb visible light at different wavelengths. So, it can be considered as two different semiconductors. They are energy arranged in such a way that it absorbs lights of different wavelength, and then electron always flows from one, photosystem 1 to photosystem 2 actually. So that's always happens. So it always flows in one direction. So can we design a system that mimics nature? That means, combine two or three different semiconductors and the energy arranged in such a way that so that your synthesis methodology should be like that. They have to be deposited in particular order so that energy flows, electron flows only in one direction. So can we mimic that? So that's the first challenge. And then of course we have to choose the right semiconductors for this purpose, so that you can maximize the absorption of photons from different wavelength region. It may be UV, it may be visible, it may be near IR, but you have to plan very nicely and choose the right semiconductor. That's the second challenge. And then when we use SILAR method, actually it produces a device without without employing any wires actually. That means the junctions what we create between say titanium and cadmium sulfide, they are two different materials. So that means the junction is called heterojunction. Okay, homojunction is the material of the same phase. Actually, for example, if I create titanium of two different phases, anatase and bruchide or rutile, so then it is called homojunction. But it is two different materials, so it is called heterojunction, and they are connected without any wires in between them. So this was another aspect. And then though the leaf actually absorb very small amount of light actually, but here our job is to enhance the amount of light absorption to the maximum possible. So that's what we are using different semiconductors which absorbs in different wavelength, and then it should also absorb very nicely. Good amount of light has to be absorbed. So that means the absorption coefficient has to be really high. So that's another challenge. And then of course, as water splitting does, the oxygen is immediately liberated into the atmosphere. Only hydrogen is used for the carbon dioxide reduction. So can we do a similar thing here? So that was another challenge. So that this breaks the thermodynamic barrier. So what we did is actually by keeping all this thing in mind, actually we have developed a device actually where I have shown a digital photograph here and named it as 1, 2, 3. The one is nothing but mesoporous titanium. The second one is titania intercalated with lead sulfide followed by cadmium sulfide. The third one, you can see that gold titania as 0.28% of gold is deposited on titania first and then followed by lead sulfide and cadmium sulfide. You can see the color difference between say, device 2 and 3. Device 2 is perfectly yellow, but the device 3 is greenish yellow. That is because the gold absorbs sunlight around 550 nanometer and gives that Plasman resonance. Okay, and you can see that particular device, that device 3, which is gold titania, lead sulfide and cadmium sulfide, which is given in red color, clearly shows that it absorbs in the UV region below 400 nanometer, and then it absorbs good amount of visible light up to 650 nanometer, and then it absorbs lead sulfide absorbs near IR photons. So that means it absorbs light of all wavelength of sunlight. So that was the wonderful thing. And then we also looked at the material, the device what we have made, and you can see that titanium, gold, cadmium, sulfur, lead, everything is dispersed right from top to bottom layer of the device of about 8 micron thickness actually. So the entire 8 micron thickness pores are occupied with lead sulfide and cadmium sulfide. Can you imagine what is the weight of the cadmium sulfide, lead sulfide, what we have intercalated? It is just 1%. The 1% of lead sulfide plus cadmium sulfide is doing the wonderful job of absorbing light producing plenty of electron and holes and doing the water splitting. So that is the success of this thing. Okay. So we evaluated the this device for the water splitting reaction, and this particular graph shows the amount of hydrogen produced in terms of micromole. This is for 1 square centimeter device, which contains material of about 2 milligram of the photoanode material. I mean, including titanium, cadmium sulfide, lead sulfide, everything together is 2 milligram of the photoanode material is coated over 1 square centimeter. That gives the best result is about 500 micromole per hour. Okay. And it gives an efficiency of about 5.6%. That means, about 6% of the photons are actually utilized to produce electrons and the holes that are actually consumed by the water splitting. Okay, so this is I want to show you that a small video where we have employed this device and then irradiated with this simulated sunlight. The moment I switch on the simulated sunlight and it is shining on the device, actually the yellow portion is the photoanode device, and then there is a small amount of platinum is coated there. So at the junction of the co-catalyst and photoanode, you can see the hydrogen continuously bubbles actually. So this is the success of this particular work, I must say actually. So as long as the light is there, actually this reaction goes on, and we can see the activity at least for 100 hours. Of course, we need to demonstrate for thousands of hours, which will happen eventually. So basically, here actually what we are able to show is actually the photocatalyst. I mean, the light absorbing quantum dots are integrated nicely in the pores of titanium, so that high quality junctions are created. That helps for the electron hole separation. And then the small amount of gold actually that also absorbs sunlight, but then it gives the energy to the immediate surroundings, so that electron excitation happens in the immediate vicinity, so that enhances the electron excitation. So overall, actually, we are able to produce much more amount of electron that leads to, that electrons are actually converted into hydrogen. So that is the importance of this particular work. Okay. The same concept actually we have extended with another semiconductor actually, where the cadmium sulfide is doped with manganese. So that means actually, cadmium plus manganese solution is mixed, and then we dip in that, followed by sulfide. So what happens is a small percentage of manganese is doped actually. In fact, I am taking this particular material is employed to generate white light. Okay, so white light is actually due to the fluorescence. Okay, but here actually we did in such a nice way actually. We have the manganese doped cadmium sulfide with different particle size, but within the device. Okay, because our pores are ranging from 2 to 6 nanometer. Actually. So what happens is actually when we created the light absorbing quantum dots of manganese doped cadmium sulfide, it can see that you can see that the orange curve what I have shown for the UV visible absorption of the manganese doped cadmium sulfide, you can see that at least up to 520 nanometer it absorbs light very nicely. Whereas the cadmium sulfide integrated titania shows absorption. The absorption coefficient is also significantly less for the device, and up to 460, 470 actually. So here what happens is actually, light absorption, light emission is shown actually with the light absorption is shown by dotted line, and light emission is shown by photoluminescence method. And what is important here is actually the light absorption and light emission, there is an overlap. So with the cadmium sulfide alone, there is a limited overlap, but with manganese doped cadmium sulfide, you can see that that triangle what I have shown in gray color, it enhances. That means even the emitted light is reabsorbed by the lattice, and it produces more amount of electrons. That electrons are again utilized for the water splitting. So with this particular device, the quantum efficiency has gone from 5.6 in the previous device to 7% efficiency, even without employing gold. So there is a novel concept brought out in this particular work actually. In fact, recently we wrote a review on how can we increase the hydrogen generation actually with thin film method actually. So this review, focuses only on the thin film method actually. Only, very selected work is were chosen. So just I want to read actually. So in fact, photocatalysis, as I mentioned earlier, actually, the efficiency is still low. But then by adopting these small changes, actually, we are able to increase the efficiency at least 10 times. Okay, what was 0.1% becomes 1%. If it was already 1% in powder, then it could become 10%. So that means, by adopting such small changes, one will be able to improve an order of magnitude increase in efficiency. That's the first thing. So then it becomes really, really important. Okay, so right now, actually, I mean, many groups are using different variety of methods actually, where they end up producing very small amount of hydrogen actually. So that is not going to work out. In fact, that we have also clearly mentioned that powder approach is not going to solve the problem. I mean, please consider adopting the thin film method. So that is the suggestion we have made. And so with that, let me stop my talk, and then I want to make possible suggestion, especially for those who are working in the area of photocatalysis. So consider seriously to move from particle suspension to thin film measurement to increase the rate of reaction through effective light absorption and charge utilization. So this will lead to better quality publication and possibly some patents also. And then try to mimic nature with your catalyst and the experiments. You don't have to do the experiments in your laboratory light. Actually, start doing the experiment in the sunlight. Okay, so that's another suggestion. Water splitting experiments also may be carried out with cheaper sacrificial agent, because right now actually without sacrificial agent the reaction rate is really low. So that I agree. But then cheaper sacrificial agent like cellulose, glycerol, biomass, there are variety of agents are available. So one of them may be used. So carry out the experiments in direct sunlight, because ultimately the goal is to convert sunlight into chemical energy. So that has to be done. Okay. So I also request, please stop investing time in dye discoloration. Often people write degradation. It is not degradation. It is only discoloration, because you are simply breaking the dye molecule into 2 or 3 or 4 pieces. You are not actually oxidizing the carbon to carbon dioxide. They are smaller fragment. That's all. Okay. The color disappearance mean actually extended conjugation is broken. That's all. Nothing else. The carbon components are still in your solution, which you have not oxidized. So I cannot consider this as a degradation, but it is a discoloration. Okay. So this is not going to solve any problem actually. Maybe, I mean, it gives an idea of whether your catalyst is good enough or not. But then you have to move to at least, alcohol to aldehyde, alcohol to ketone. Can you do that in direct sunlight? That's going to add value to your work. So with this, actually, let me conclude my talk. Actually, in fact, when we published our first paper in 2017 in Scientific Reports, Nature India brought out a small note on our work actually. So they themselves brought, and then followed by it was kind of, I got a lot of advertisement for our work actually. So even in NDTV there was a small note on our work, and many couple of at least 2-3 magazines brought out an interview, newspapers. So I was really surprised that this work got so much notice by the media actually. So I was really happy. So basically, see, sustainability is the key. Actually, we need to invest in finding sustainable solutions. So with that, let me stop, and I want to thank my wonderful group of students. Actually, I am really blessed with I mean, my students are gems, I would say. Actually, I mean, nothing less than gem. Actually, I mean, they're all pretty much enthusiastic, and they contribute in a very brilliant way. Actually. So I thank all of them, and of course I thank all the funding agencies also who have supported my research. Okay, thank you. And this is the beautiful garden what we have in front of NCR. So let me stop here, and I'll be happy to take any question. Thank you very much. Yeah.
Thank you, sir. Wonderful lecture. Bini madam.
Any questions?
You are muted, Dr. Bini madam. You have muted.
No, you have to unmute.
You have muted.
No, still you are on mute.
Dr. Sunny, they can unmute, no?
Hello. Yeah. Hello. Yeah. So, sir, thank you very much for your inspiring and what I have to say, not wonderful, that very thoughtful talk that is very useful for our young researchers. Be with the nature and do some good to the society. Like that, we can. Your talk was very inspiring. That with that we can take our economy. Okay, now everything is to the new generation. Everything in the technology is in their fingertip, but they are not close to the nature. But with this, your message, and your research students are gems. Okay, that is what, like that. Your research group, I wish your research group should produce more fruitful, and the society useful innovations.
Thank you.
And with this, I didn't see the chat box because your talk was very inspiring, and that's why now I see the chat box for the questions. And
Maybe either they fully understood or they did not understand anything.
Then it was very from fundamental to this advanced things and society useful things you took us. It was very inspiring. I thank you very much on behalf of the Department of Chemistry, Central University of Kerala, and the organizing team. I extend my sincere thank you. And now the session, sir, now the session can be open for the questions.
Hello. Hello.
Yeah.
Hello.
Yes,
sir.
yes,
I'm Pro Swaminathan.
Yeah, please go ahead, sir.
Sir, the talk was excellent, and given the basic principle and as well as all these requirements for solar energy utilization by using the photocatalyst. So it was excellent. But students are many, immediately they are tempted to test only the degradation of dye as soon as they prepare the photocatalyst. That is a usual thing, but better to go for these things. But I would like to ask one thing, that the sacrificial agents, when we use it, whether that is advantageous or direct one is advantageous, getting hydrogen and oxygen.
Direct one is definitely advantageous actually, but then right now actually, what is the issue is actually because the hydrogen production involves 2 electrons, whereas oxygen production involves 4 electrons. And so the overall kinetics is slowed down because of this process actually. So the overall water splitting is slow because of this particular kinetically sluggish oxygen generation step. So to overcome that, people are still using the sacrificial agent, but then, instead of using methanol and other costly sacrificial agent, if we can use cellulose, which is available in plenty, or biomass, or glycerol, which are very, very cheap, and if we can extract only hydrogen out of that, it is still okay.
Okay, right, sir. So I think your lecture will be very useful for the youngsters to go for the solar energy utilization. Thank you very much, sir.
Thank you.
Okay, right.
Now the session is open for questions. Young researchers and other this one eminent participants, you can have your interaction with the Dr. C.S. Gopinath.
Anybody may want to ask any question, I'll be happy to answer.
So there is one question is there, instead of this can we use ADO dyes for the catalytic? One question from Shimna Biju.
Shimna Biju, okay.
Instead of decoloration, do research on degradation, can we use this catalyst for ADO dyes?
So, this is a good question actually. For example, some of the compounds are, harmful to the environment. Okay. For example, especially the fluoro compounds are harmful to the environment. So if we can decompose that compound, also it is good, but then decompose up to the, last component. Okay. Don't just, break it into 2 or 3 pieces actually. So you have to completely oxidize that compound. That is, all the carbon should go to carbon dioxide. That kind of, complete degradation is required actually. So that is something I want to say. Okay. See, for example, pesticide. Pesticide is one of the important issue actually. So can we decompose the excess pesticide what is in the field, or so can we do a simulation in the laboratory actually, that is use the pesticide molecule and show complete degradation into say carbon dioxide, water, all those things, then still good actually. So similarly, there are many compounds that are harmful to the atmosphere actually. So if we can show degradation of that compound, that is also fine. So that means, finally you have to go to the carbon dioxide and measure that.
Shimna is there? And any other?
Yes, thank you,
yeah,
sir.
yeah,
Thank you
yeah.
very much for your information. But thank you very much. Actually, we are doing the research on the azodite degradation. That's why I asked this question. Thank you, sir. Thank you very much.
Thank you.
Anybody else? Hello?
Yeah. I mean, this is one typical problem, none of the students want to ask. They may have question, but they don't want to ask.
Yeah, you can type on the chat box. That morning session also the same thing happens, sir.
I think somebody else, I think I only read the mail. I would like to ask one question. What about nitrate in cadmium? Your starting material is cadmium nitrate. That's a good question actually. But only cadmium gets absorbed, not the nitrate actually. Nitrate is, highly ionic and it is in solution. The cadmium have, the absorption capacity to absorb, and then nitrate will remain in the solution. And similarly, when cadmium is absorbed on the surface of the catalyst or in the pores, wherever there is cadmium, sulfide gets absorbed. Okay, so though it is sodium sulfide, only sulfide gets absorbed, not sodium.
Sir, I have one question.
Sure.
So you have asked us to focus on the thin film. Like people like me, like those who are hardcore materials, in the conventional materials, how the nano wiring, now the people also focus on the nano wire, how whether the catalyst of nano wire or nano size, will it have the better photocatalytic activity, or we have to make a thin film only will have the better?
No. See, all the nanomorphologies are going to be helpful. For example, especially the 1D and 2D materials. That means your wire is going to be under 1D, and then 2D mean planar, like graphene oxide. All those 2D layered materials are also going to be useful, especially for electron conduction. That is, for example, in the 1D material of any nano wire or rod, or that kind of thing. Actually, the electron conduction is going to be really, really fast. Okay, so that advantage we should make use of it, but in the right way. So can we make a nanorod, or can we make a nanorod within the pores? Is it possible? For example, you take any of your mesoporous materials like MCM41 or SBA15, where you have long channels. So can we grow the nanorod, what you are thinking, in the pores? If that can be achieved, your activity is going to enhance easily an order of magnitude. That I can guarantee you. Okay, so you can think of how to do that. Okay.
Okay, sir. Thank you.
Sir, as sir said, they want to ask many questions, but
Okay.
Sir,
we have time, enough time. Yeah.
Hello, sir. Hello, sir. I am Raman. Sir, your presentation is very good. Fine, sir. Fine, sir. Okay, sir. Very nice to meet you again through this webinar. Sir, what about the cost effect? Whether it is, you are decomposing something. And then finally, what about the cost, sir? Whether it is more costly comparing to...
No, cost factor is going to be very, very favorable here because, see, the material what we are making, the photocatalyst, the light absorbing quantum dots, you are actually putting only just 1 or 2% inside titanium. So titanium is inside and all there are. In fact, see, most of the youngsters actually, all the creams what they are applying on the face, like Fair and Lovely, all those things, 90% and above is either titanium or zinc oxide. It is so cheap. Okay, so that's the first thing.
Yes.
And then in that titanium or zinc oxide, you are putting just 1 or 2% of this light absorbing material. Again, there are more of oxide, sulfide, all of things. So it is again cheap. And then you are using sunlight. Okay, you are not using any artificial light. So that is available free. Water is almost free. Okay. So what else you need? So your device is going to be really, really cheap here. Of course, the making charge is there. And then the chemical charge, everything is there actually. But then, if we can actually say conversion of A to B, and alcohol to aldehyde or alcohol to ketone, if we can do, wonderful, why not? So you take isopropanol and can convert into a acetone. I mean, this is one a model reaction I'm talking actually, but then there are many reactions can be done. Okay, so if we can do that, that's wonderful. Okay.
Very nice, sir. Thank you, sir. Thank you, sir. And thank you, the organizers, for having given me this chance due to our work, sir. That is why I'm joining this webinar at the last time.
And that Raman quite long time.
Okay, sir.
Yeah.
Welcome, sir.
Any other question? There is one.
Yeah. Thank you, Dr. Bini Jaj, for sharing the session, and thank you, Dr. Govinas, for the wonderful session. We had a very nice session, and like motivating session. It is like how one should do the research. I mean, what kind of problem one should address, not just taking the problem and do the show that, not only just show for the publication and things, what we need to take it up. That is that kind of lectures. Not many of them do it. It's a wonderful, sir. Thank you so much for joining in the webinar, and thank you, Dr. Bini Jaj, for sharing the session. Thank you once again. So we'll go to the next session. That is an invited talk by Dr. Sopna Nair. So thank you, sir.
Sakti, I may leave in another few minutes because I have another meeting to go.
Sure, sir. Okay. And
Yes, sir. Thank you very much.
Yes, sir. Thank you, sir.
Thank you, sir.
Yeah. Before moving to the invited talk, there are a couple of announcements. Tomorrow, the first lecture will be by the Professor Ajay Veenu from University of Newcastle, Australia. It will be at 9:35. Can you keep silent? Can you unmute, all of you? So tomorrow, the first lecture by the Professor Ajay Veenu at 9:35, and second lecture will be by the Professor P. Ramasamy from Mauritius at 10:45. Then third lecture by the Professor P. Selvam from IIT Madras. Sir, Swaminathan sir, kindly note that tomorrow Professor Selvam want to present at 11:45. Yes, he has an emergency meeting with the Dean, so that's why change of schedule, kindly note. Okay, please go ahead. Dana?
Sir, I will carry out. The next invited lecture, it will be chaired by Dr. Bhaglakshmi ma'am, Assistant Professor, Department of Chemistry, Central University of Kerala. I request ma'am to chair the session.
Thank you, Misha. So good evening, one and all. We are in the last part of the today's webinar, the last technical session. Actually, one more oral presentation is there. However, the technical session, that invited lecture, this one is the last one for this today. So I would like to introduce our another professor, Assistant Dr. Sapna S. Nair. She is Associate Professor and Head of the Department of Physics in Central University of Kerala. We know that everybody knows in Central University of Kerala, she is a very dynamic researcher, and not only researcher, she is a very dynamic person. She is doing very well in the university. We are very happy to have Dr. Sapna S. Nair here for our webinar. To talk about her credentials, she has worked as a postdoctoral investigator in I think she is a recipient of BOLSA's International Postdoctoral Grant, and also she is also a recipient of BOLSA's POPH grant awarded by European Commission in 2011. And during her postdoctoral work, she took a very big project. It cost more than multi-million money. Indian rupee, it cost more than 2.75 crores. Okay, that much money project. She has worked in that project as a principal investigator. That is very very important thing that we should be proud about that. And it was related to no lead in microelectronics. It was a topic. So this was the very good important credential which we have to state about our Professor Dr. Sapna S. Nair. And to talk about other credentials, she has received fundings from various funding agencies like UGC, DST, DBT, and she has more than 7 projects, total cost around 73.5 lakhs around. Not only that, she has also published many papers, more than 60 papers, among which 2 or 3 papers has got more than 250 citations. So that it means citation is more, means that paper is read by more researcher. Means it is a very good research, and the results are also very appreciable. It is that meaning. So that kind of very highly reputed publications is produced by her. She has produced around 5 research students, PhD students. They have completed, they have been awarded PhD, and she has also written 2 books and more than 15 book chapters, and very important, she is also a recipient of patent. Very good patent is there. It is a process and product patent that is there. And her research area concentrates on contents, matter physics, applied physics, especially in energy materials, multiferroic, magnetoelectric materials, ferrofluids, biomedical applications of nanomaterials. All these things are her research area. And to talk about her another these academic, administrative credentials, we can talk like that. She is one of the I think only one. I think she has been the head of the department. Under her headship, department has received FIST fund in physics department. It is a very proud moment for our CUK. So we are here to hear from our very dynamic and eminent Professor Dr. S. Sapna Nair here. Let us hear from her for this technical session. Over to you, ma'am.
Okay, thank you, Dr. Bhagyalakshmi. A very warm good evening to one and all. Actually, my research area is nano-energy harvesters, and mostly I'm focusing on lead-free materials, for which I received a big grant, as Professor Bhagyalakshmi was mentioning about. So it was a European strategic project to remove lead from all microelectronics. So knowledge in microelectronics was a big strategic project by the European Commission. I was part of that. And maybe because of that, I got several grants afterwards as principal investigator, Aveiro and Porto in Portugal. And later, after coming back, I started some collaboration for biomedical applications too. So some of the sensor that we make are used for biomedical diagnosis and disease marking. So these are my research areas. Today, I will be talking mainly about the sensing and energy harvesting potential of lead-free materials, lead-free piezoelectric as well as multiferroic materials. So is it audible to all?
Yeah.
Is it audible? So
Yes.
can I start the presentation? Yeah.
Yes. Please.
So. So, is it full screen now? Visible to you?
Yes, it's visible.
Okay. So, thanks a lot. And this is my topic title: Nano Energy Harvesters for Next Generation Implantable Sensors. When we talk about implantable sensors, we have to make it sure that these materials are non-toxic. That's why I'm speaking about lead-free all the time, because next generation is going to use these materials widely for Internet of Things. So that is why it is all important. So Internet of Things. So we are not going to the era of Internet of Things. Internet of Things already started way back, maybe 10 years before itself, but now it is going to invade in our life more frequently, because we are going to get connected to everything. So not only the smart devices were connected much before, just like tablets, mobile phones, computers, laptops, and all. These were connected much before, but we were not able to communicate to the non-smart things. Just like if I want to communicate to my bag or my something like a file, so then we need to have some smart devices which need to be implanted on top of the not smart things. So we need communication possible. So for that we need some sensors. So that is why sensors are all important. Now see this particular slide, we will be able to, okay, so let me see the options for the, okay, let me use this mouse itself. Okay, sorry for that. That option is not visible here, that marking option. So here we will be able to see that in maybe near future, within 1 to 2 years of time, because these things are going in something like a dramatic speed. We even cannot imagine how fastly these things are growing. So this industry, Internet of Things, is growing in such a speed that maybe in 1 to 2 years of time, all these things that we are going to imagine, even if out of imagination, these things will happen soon in our life. We will be able to communicate with our washing machine. Now itself it's possible. So non-smart electronic devices and non-electronic devices, everything is going to be made possible because of this drastic revolution that are going to happen in nano energy harvesters as well as in nano sensors. So that is why it is very important to give a big focus on these particular technologies, because it is the futuristic technologies, and world will take these technologies soon. So different kind of sensors. To make this Internet of Things happen, we need different levels of sensors, because sensors really assist us to communicate with all these devices. And energy harvesters, because sensors will not work as its own. We need energy harvesters. It need energy harvesters and then connectors. Then it cannot have, because we need to give command, and command should go into that, and it should respond to that command. And we need storage and memory devices. So these are part of this, whatever be the machinery that make the non-smart things smarter, so that it can communicate with us. Okay, so there should be feedback systems, actuators, batteries, because sometimes we need batteries. If it's not a continuous, okay, if the harvester is not giving continuous energy, then we need batteries. So we need all these, but if we are making a sensor with large batteries, it will make my system very robust, and it will not be that much useful. If I want to use my COM, and if my sensor itself is bigger than the COM, that will make things a little bit difficult. So go batteryless will be the motto of the next maybe a few years time. So we have to focus on self-powering. So energy harvesters, which can power each of the small tiny circuits inside the sensors, will be the need of the hour in this aspect. So in this aspect, I have to say, we have to look for materials, novel materials. We should not focus something which is giving a feeble property and try to improve the property. But we have to drastically change the material properties. So properties are really important. So we have to focus on what kind of materials that will be useful for these. So as you know, transistors are going to shrink to its ultimate size maybe in the coming 2-3 years time. Itself, IBM already claimed that. So we have to understand that most of these circuits are going to shrink it to its ultimate dimension. So then how far we will be able to miniaturize the sizes after that? So then multifunctionality will be the first point that will come in our mind, because one element itself should be useful for multi aspects. So in that case, vertical space utilization can be made maximum. So that will make the number of elements reduced. So in that way, we will be able to reduce the things a little bit further, because we need smaller devices, we need higher capacities. That is our dream always, because maybe 20 years back, computers with maybe megabytes of storage. Now we don't want anything of that kind. So even our palm tops are having terabytes capacity. So it's like that. So these kind of novel thinking. So out of the box thinking will always bring all these things because individual units are going to shrink to its ultimate size. Then afterwards, it will be very difficult for us to shrink the components, but reduce the number of components will be that. And the second thing, go batteryless. Batteries are going to take much of its size, volume. So if we can make each of the components standing without batteries, that would be wonderful. So these are the thought points before I go into my talk. So for this, I will have to say we have to focus on materials which will harvest energy, but material which can sense, materials which can be used for storage and memory applications. So these kind of all these multi-scale applications will make it converge to some class of materials which are piezoelectrics, which are ferroelectrics, which are magnetic, and so multi-ferroics is one among the best choice in those aspects. So I'm going to start with my talk with this short introduction. So multi-ferroics are the materials that I will be talking about in this particular webinar. So energy harvesting, a lot of choices are there. Solar energy harvesting is there, thermal is there, then other kind of wind and other non-conventional type of energy harvesting choices are there. But the issue is that when we are trying to make the components reduce to maybe nanometer scale, most of these other non-conventional techniques will fail. So in that aspect, only the solar, because now nano road-based solar cells are there. So I still can look into solar cells. But the immediate option that will kick in our mind will be the vibrational energy harvesters. So vibrational energy harvesters that can harvest energy, vibrational energy harvesters that can send something, and the same if it can serve as a memory element. That kind of materials would be of choice for this industry, IoT industry, maybe in the near future. So harvesting energy from vibration. So piezoelectrics, that is what piezoelectricity. Piezoelectricity is something like a material which can convert the stress signal into voltage and vice versa. So obviously it will be able to tap energy, and maybe measuring it as voltage, we will be able to convert that into energy. Electrical circuit. Excuse me. Excuse me. Is it getting broken?
Ma'am, no problem. You can carry on. We have muted. We have muted.
So we will be able to use these kind of vibration energy harvesters for harvesting energy and sensing something. I will show what are the things that can sense, and then if it can be used for memory applications, that will be wonderful. So that is why I am going to start with this. Then whenever we talk about piezoelectricity, the main candidates that will stand before us will be lead-based candidates like lead zirconium titanate, lead titanate, and lead-based products. So as I was working in a project in which European Commission was trying to wipe out lead from all microelectronic devices, then I have to say that for futuristic implantable devices, I should not even talk about lead, because lead is a toxic material. Everybody knows about that. So lead-based components, we have to forget. Whatever be its whatever be its the efficiency, the conversion efficiency from because that is called the piezoelectric coupling coefficient. Whatever be the high coupling coefficient that these lead-based materials has, I have to go to the lead-free materials, because I'm going to focus on the implantable sensors for which biocompatibility is one of the major criteria that need to be evaluated first. So in this aspect, the neobate family and titanate family will be the best alternative to the lead-based components. Although we have a compromise of the piezoelectric coupling coefficient, that is all okay, because we will be able to improve that by different optimizations, and we will be able to use these for applications. So sodium potassium neobate, which is commonly called as KNN, and bismuth zirconium titanate, calcium titanate. So these are the material in which after lead-based materials, maximum piezoelectric coupling coefficient was reported. So these were the materials of my choice where I have started with this work. And I will have to say this cartoon shows all these words because these same nanotubes were used as phase sensors, transducers, and then energy harvesters that is possible. Its basic principles is evaluated, and this is a BBC years and years ahead one video they forecasted where implantable sensors were Wi-Fi implantable sensors. It should make our hand itself as receiver. So this kind of things will happen soon. So this entire work can be summarized in these slides. So in the initial talk itself, I have been telling about the miniaturization. Miniaturization is the motto, but how far we can miniaturize. So we have to think out of the box rather than going into the reducing of the individual components. We have to think about something else, multifunctionality. So that need to be the third point. So the material should be magnetic, it should have magnetic characteristics, it should have ferroelectric characteristics, it should have piezoelectric characteristics. So that is why these materials were of choice, these magnetoelectric composite materials of multiferroic composite materials, because individual multiferroic materials fail to deliver high magnetoelectric coupling coefficient, which really determines the energy harvesting potential of these materials. So we have used simple techniques because this is a new university, rather sophisticated techniques were not available for the fabrication. So we completely relied upon chemistry-based synthesis techniques for the synthesis of nanotubes, multi-wall nanotubes, and nanorods, and multi-wall nanorods. So these were the materials that we have used, and we tried to evaluate its piezoelectric coupling coefficient from a single nanotube. That was a bit difficult to measure, but we measured with PFM and conducting cantilever AFM, and we could obtain. So this was the way how we have measured that. It was a bit difficult to convince most of the technicians available here to do this particular work, but we could get 300 microvolt from the single cantilever, single nano cantilever during this measurement. So multiferroics are the materials in which we have the ferroic orders, two ferroic orders, ferroelectric as well as ferromagnetic or perimagnetic ordering is there, or antiferromagnetic, that also is possible. And we are aiming at very good magnetoelectric coupling coefficient. That is the main point that we will be looking for, because high voltage, if we are getting by giving a magnetic field, so that means that this magnetoelectric coupling is very high. So composite multiferroics, that was the choices, and we have tried to use this strain mediated magnetoelectric coupling because the coupling is mediated through strain. So strain, if we are giving a stress signal to the piezoelectric materials, that stress signal will be going as voltage, and it will be transferred to the magnetostrictive materials. So magnetostrictive material will change its size. So the converse also is possible. So we will be able to generate voltage in the other way, and we will be able to give voltage and reduce the dimension in the other way. So both are possible. So that is why these materials are of high interest. So piezoelectric itself is interesting materials because it can convert stress into voltage. But this, by giving magnetic field, even without a stress, if we are giving an AC modulating magnetic field, we will get voltage. So that will be wonderful, because without giving a direct stress to the nanotubes, we will be able to tap the output voltage. So we tried with all these 3-0 composites, 2-0 thin films. These 3-0, 2-0, they are 3 is the matrix of the ferroelectric materials, and 0 is the magnetic components, and 2 multi-layers magnetic and ferroelectric materials will be coated on top of each other, and one coaxial nanotubes. That was actually we introduced first in KNN based system. In non-electric systems, some of those were investigated before, but we have introduced these two. Partial structure and partial coaxial nanotubes were introduced as a geometry first time by our group. So these are the ferroelectric characteristics, and then the second component that we have used as magnetic component were cobalt ferrite and met glass. Met glass is an alloy which is having composition which is given here. I selected this particular composition because this particular composition gave very large magnetostriction, and that is why, because magnetostriction is the main criteria, it will give a very good magnetoelectric coupling coefficient when we think about the voltage harvesting potential in our mind. So this shows the magnetostriction. These were having very high magnetostriction at if annealed at a particular temperature. So that is why we have an electric coupling coefficient because of the high magnetostriction important to that. So
I'll check with Swapna.
Sir, ma'am has to.
Yeah, I'm checking.
Ma'am, am I audible? Ma'am, please. Okay. I'm just providing her the course rights. Ma'am, please unmute yourself. I have provided you course rights. Now you can unmute yourself.
Okay. So it showed that it cannot be unmuted myself. That's why. I'm sorry. In between, I don't know what happened here.
Fine. No problem. Share the PPT.
Yeah. Right. So. These were the geometries that we have opted, and the bulk composite films and the fabrication techniques that we have used mostly were sol-gel spin coating as well as sol-gel spray pyrolysis techniques. And these are the results in the bulk composites. These are the structural characterization and the microstructural analysis. The important things is the magnetoelectric coupling coefficient. So I will just show the other properties. They are showing the ferroic ordering, and the magnetic properties are maintained in those, along with the magnetoelectric coupling coefficient. That is very important. In this bulk composites, we received a magnetoelectric coupling coefficient of 0.028. This is the value in bulk composites, while in 2.0 nanoparticulate thin films, we got a magnetoelectric coupling coefficient of 3.5 volt per centimeter roasted. The materials were the same. So only the geometry only was altered, and we got something like 100 times the magnetoelectric coupling coefficient when we moved into the 2.0 nanoparticulate composite. And in multi-layers, it was 0.4. And in 1.1 coaxial nanotube arrays, it was 12.1, the maximum. So we could understand that it is not just the materials. The geometry really influences the magnetoelectric coupling coefficient, maybe because of the interface bonding, and maybe the interfaces were weak in 3.0 because it is a nanoparticulate system, and the number of nanoparticles and the phase differs. We got very good values in the coaxial nanotube arrays. So that particular material was used for sensing. So piezoelectric and magnetoelectric multimode energy harvesters as well as sensors were tested on these piezoelectric and magnetoelectric nanorod arrays. So we made KNN CFO coaxial nanotube arrays by multi-step sol-gel wet chemistry route, and we used anodized alumina as the templates, and these are the SEM micrographs, the stepwise synthesis of the nanotubes, and we use these particular techniques. these AFM cantilevers to harvest the energy. Means they use 5 nanonewton as the force and they measure the voltage. So the same thing we tried, and my students Chitralekha and Ajit Kumar were doing this work. While doing this work, I thought of doing a direct comparison between the thin films as well as nanotubes, because it is always advantageous to get the results in same slide. So we made thin films as well as nanotubes on the same slide itself. So we first coated the nanotubes. On top of that, we made the thin films, and using the AFM cantilever, through nanolithography, we made cracks in the films where the nanotubes are visible. So you see the one-to-one correspondence while the voltage harvesting potential is concerned, only through where the nanotubes are visible, we were getting very high voltage. So it shows that the voltage harvesting potential of nanotubes were much higher, because the same solution was used for the thin films as well as the nanotubes. So same conditions were maintained, but we will be able to see a direct difference, multi-mode, maybe 2-order difference is there for the voltage harvesting of the nanotubes as compared to the thin films. So a very high D33 as well as a very high voltage harvesting potential was there for these nanotubes and coaxial nanotubes. So this was reported in nanotechnology recently, and maybe after gaining these particular values, we tried to make it as coaxial with cobalt ferrate as the inner layer and the KNN as the outer layer, and we have evaluated in the same way the magnetoelectric voltage. So this shows the sensing potential of this particular nano energy harvester. It can harvest energy and it can sense the AC modulating magnetic field. So while the AC modulating magnetic field was given, the magnetoelectric voltage had frozen up to 300 millivolt. From a single nanotube, we could extract 300 millivolt with an AC modulating field of 100 ohm. So this can work as a magnetic field sensor, but actually to make it useful for a Wi-Fi signal sensor, we have to work a lot on that. And I got a project recently from CRG in this aspect for making this useful for very small magnetic field detection. So the detection of magnetic field, now we have started with the moderate magnetic field detection, but in that we have to go for milli-oersted range magnetic field detection. So we have to do that particular work. We are doing that particular work right now, and this shows another candidate, KNN glass KNN, the multi-layered structure, and this shows, and we have made it as a cantilever and tried to see the resonance and sub-resonance effects of these particular cantilevers. And while looking, we will be able to see that the magnetoelectric coupling coefficient just shooted up to 1500 range at a very small frequency of operating frequency of 750 Hertz. So that will make this cantilever highly useful for a low frequency application, because tapping potential is very high. 1340 was the value. And this is the reason, because of the very high magnetostriction that happened in the annealing process. So these results were published in Applied Physics Letters recently, and our group published the maximum value 1321 in KNN net class KNN multi-layer structures, and we could harvest 9.5 volt per centimeter roasted at sub-resistant condition and 1321 volt per centimeter roasted at 750 Hertz. 750 Hertz is a low frequency as far as the applications are concerned. So we will be able to use this for low frequency applications as well. So that is why this kind of cantilevers assumes high significance in these aspects. You will be able to see the results in a nutshell here in KNN CFO nanoparticulate. So here we have used the same setup, same solution, same salt gel solution for the synthesis of all these. The particular composites, trilayers, as well as the coaxial nanotubes. But we will be able to see the difference. The same material, same process, but the geometry only was tailored, and we will be able to, we were able to tune the magnetoelectric coupling coefficient from 0.0 to 8 volt per centimeter Oersted. That means 28 millivolt per centimeter Oersted to the range of 12.1. These are again KNN CFO, so 12.1 volt per centimeter. And we were able to get sub-resonant value of 9.5 volt per centimeter roasted in multi-layers of KNN, net glass KNN, while the same when we made as micro cantilevers and tried to see the particular voltage harvesting potential, it gave a very high voltage of 1321 volt per centimeter roasted. So these are the conclusions. It's not only the material parameters, the magnetostriction and piezomagnetic coefficient. The geometry also is very important. The connectivity also is very important. And these were the novelty. These were the coaxial nanotube arrays were the first magnetoelectric system which was reported based on KNN. Until now, it remains the only coaxial system with KNN as a piezoelectric phase. And we have introduced net glass as a candidate. So is it audible? It shows some discontinuity in between.
No,
is it audible? So these were the new system that we have proposed. Yeah, so the KNN based nano multi-layered, it is something like multi-walled nanotube system and multi-watt nano road systems. These were the first magnetoelectric system reported based on KNN, and it remains the only one-dimensional coaxial system with KNN as a piezoelectric phase till now. And these are the first multi-layer cantilever based on KNN, which could be used as energy harvester based on the particular composition of net glass. It delivered the highest magnetoelectric coupling coefficient till date in Nord-Stream cantilevers. And there were very few systems reported with 2-0 geometries, and we could tailor the properties of this 2-0 geometry also, which is easier for us to adopt rather than going for the nanotubes, because to harvest energy from nanotubes, we need sophisticated measurement techniques, and sensor industry will be after that, obviously, because that is part of the nano energy harvesting potential. So these were the results. We could harvest energy, and the same element could be used as a magnetic field sensor. So sensing was there, energy harvesting potential was there, and they are ferroelectric as well as antiferromagnetic, and some of those were ferrimagnetic because they were used, and net glass also was used. Ferromagnetic were there, ferrimagnetic were there, antiferromagnetic were there. So they were magnetic, and the magnetic properties were very good, and magnetostrictive properties also were very good. So they can be used for memory elements and storage elements if properly used. But that particular aspects I never worked with. I have to go into that direction later because the ferroelectric polarization was not high because of the Pauling effects. So I didn't focus on those particular aspects, but I was focusing on mostly on the sensing and energy harvesting potential of these materials, which was proved beyond doubt. And we got a very high magnetoelectric coupling coefficient, and some of those materials gave the highest ever coupling coefficient in those lead-free systems. So these were some of the publications that we have made from these couple of 3-4 publications in applied physics leaders, then Scripta Materialia, then Ceramic International, RSC Advances, and some other in JMM and like. So these all works actually my PhD students did. My whatever be the role was very minimal because I just spoke about something. They have done all these hard works, and these were the team that made all these works feasible as well as time-bound. In a time-bound way, they have worked a lot, especially the works that I have shown: Ajitis Kumar, Chitralekha CS, and Vivek S. These were the 3 students who were actively involved in this particular work of nano energy harvesters and nano sensors. So these sensors, if it can sense milliostat range magnetic field, that can be used as a Wi-Fi sensor in the next generation implantable devices. And we have tested the biocompatibility as well. So these are the background works, and maybe in near future we will be able to use these nano cantilevers as self-start and self-powered material for harvesting energies as well as sensing the magnetic field. So it is, I will go to the acknowledgement slide. So couple of funding from BST, DBT and UGC, and then some of the close associates like Professor M.R. Ranagram and Venkata Sharavanan, then Mundakumar sir, then Dr. Shaiju from myself, and my old postdoc mentors for the BFM and nano cantilever voltage measurements in the University of Hawaii. So maybe thank you all. Sorry for the intermediate issues with the Wi-Fi connection. So maybe you can ask questions.
Yeah, fine. Thank you, madam.
Thank you, ma'am. Actually, it was really interesting. So towards miniature devices. So to be smart and small, even if we are small, you should be smart. That is what ma'am is trying to explain. Actually, it is really very, it's a new field, emerging field. Many researchers can take up this topic and then they can come up with a very good research, I hope. I think most of you, even ma'am is interrupted, you are in connection only. I hope, because it is magnetically connected, even though if you are not there. So let us go hear from the participants. Any questions? Participants, would you like to ask ma'am?
Dr. Swapna, I have one doubt. I mean,
yes, yes.
You are doing it the cobalt ferrite.
Yes.
So the cobalt ferrite, you are trying to stabilize cobalt in +2 oxidation state? Is it
Actually, till now we didn't experience any issue if we are going in sol-gel route, but for co-precipitation route, what you told is correct. 3+ and 2+ is shift, and the magnetization was very weak. And in sol-gel technique, we never experienced that issue. We got very high, means close to the theoretical value we got as the magnetization.
Method means what is the precursor you are using basically?
We were mainly focusing on nitrates, and ethyl glycol was using as chelating agent, and we used very small quantity of water in that, and glycol was the major component in that, because during the optimization we could see that if we are using water more, there was a chance of getting precipitation of alpha epitope phase, which will drastically reduce the magnetization. So
also spinal
yeah, 90:10. Yeah, that was the optimized quantity for water and ethyl glycol. Yeah.
Even the spinal controlling, the spinal phase can also always, you can get it in the cobalt.
Yeah, actually, cobalt ferrite inverse spinal condition, to get completely in inverse spinal condition, it is a bit difficult, because there is a chance of getting shifting from cobalt 3+ to 2+, and it will dangle in between A and B side. So there is a chance of getting that half normal to half inverse spinal. But here we were able to get that in the pure inverse spinal itself. So we got close to the theoretical maximum magnetization for those materials.
Thank you.
Ma'am, what about the conductivity of these materials? Whether they can conduct electrical conductivity?
Yeah, we have done only dielectric and AC conductivity measurements. The DC conductivity measurements were not done, but the cobalt ferrite is rather conducting as compared to the piezoelectric phase.
Okay.
It is rather conducting. All the ferrites, nickel ferrite as well as cobalt ferrite, it is it showed 2-order larger conductivity than the piezoelectric phase, which is completely the ceramics insulators. So these are showing semiconducting nature.
I have read some paper related to this, not exactly this KNN, but related to this, some materials are there which they are very good conductors, the spinels. And not inverse
Neobates are still better conductors as compared to the titanides and other group of ceramics. But there are some issues for the neobates that I have to say, because we struggled a lot during my postdoctoral time. Initial 3 years, I struggled a lot to get the KNN in right phase, because there is a chance of phase separation. So without hot press sintering and densification techniques, it was very difficult to get KNN as single phasing. But we optimized a lot and introduced a new sol-gel technique, which gave us completely phase pure KNN without phase separation. So there, that KNN had very high ferroelectric characteristics as well as piezoelectric characteristics. So if we go a little bit away from that morphotropic phase boundary, then every chance of losing both piezoelectric as well as ferroelectric properties. So it was a very small boundary. We have to be very careful about those materials. And metglass itself was a very tough material because cobalt 74, that particular composition, if correctly maintained, then only we will get that much high magnetostation. If some small change in that particular ratio is there, then the magnetization will be completely lost. So that was another headache in that. So
even
optimization.
Getting that coaxial characteristics also, it's all the magnetic properties.
Coaxial nanotubes we made with two-step Sol-Gel technique. Actually, we really used only wet chemistry route in that. Electrophoretic deposition also we have tried, but I didn't include those slides in that because that gave little bit lesser quantity of magnetoelectric coupling coefficient. As far as we are concerned, we were happy with the Sol-Gel because the wet chemistry based techniques gave us better results. So we focused on the wet chemistry based techniques only. Electrochemistry we didn't use.
Similarly, what happens if a current carrying conductor is placed in a magnet? That's what we learned.
Okay, ma'am. Actually, any other questions from the participants?
Yeah, I think somebody asked something.
Somebody is a force with the formula of F equal to B by L sin theta. If you place a current carrying conductor in a magnetic field, it will experience a force. That force formula is B equal to B by L sin theta.
Do you have any questions?
Any doubt?
I think he is talking to somebody else.
No, what I'm going to have.
Maybe he might have forgotten to switch off the mic. It often happens in conferences. I have seen that. Yeah, if somebody wants to ask some questions. So these are the. I had a short video because it is out of scope of this because of that I didn't show that, which shows in near future that our palm can be used as mobile phone's receiver. So that particular photo I have shown.
Slide you showed.
So it may use this kind of nano energy harvester cum sensors, widely implantable sensors. So we have checked with the fibroblasts, skin fibroblasts regarding the biocompatibility, and it showed very good biocompatibility.
We have to move on to the next. There are another 8 world speakers are there, so we can have more interaction.
Yes.
Maybe
thanks a lot, Dr. Shaktivel, for inviting me for this particular talk because it was a very good opportunity for me to talk in CUK because it's the first talk that I'm giving in CUK. Maybe outside I have given a lot. Okay, thanks a lot.
Thank you, ma'am. Thank you very much. Thank you very much for the very interesting talk. I hope everyone would have enjoyed. Thank you on behalf of the webinar committee. Thank you, ma'am. Organizing committee. Thank you very much, ma'am.
Okay, thanks a lot.
Sir?
Yeah, Yamuna madam has not joined. Can you
oral
call?
Presentation?
Yeah, she is a judge along with Dr. Bini George.
Okay, sir, I will call her.
Bini madam, you are there, no?
Yeah, I am here, sir.
Yeah, I think we can go ahead it by that time because I was calling her, Yamuna madam. Ashwin, Dana?
Yes, sir.
Have you got coordination from any Ashwin, who is going to present first?
Sir, Manohar Jople.
What is the number? Number is
It's
Dana.
OP29, madam. OP29.
Okay, OP29. Okay.
Yamuna madam, are you there? Just Bini madam, just 1 minute. I will try.
It's okay. It's okay, sir. Let her join.
Let's see that. She was telling some problem. Let me. Sorry, it became late.
Otherwise you can have one and she can join. No?
I just that's right.
Yeah.
Just a minute. She is joining, madam. So the first participant, first oral person, you can.
OP29.
Who is that? Ashwin?
Manohar.
Manohar. Yeah. Can you please share your PPT? Okay.
Yes, sir. Yes.
We'll just.
Shall I give the introduction?
Yeah. Wait. Just a minute. Okay, madam.
Hello.
Then I just
wait.
Sir, my presentation is now visible.
Yeah, you are visible. Yeah.
Yes, sir.
1 minute. Yeah, Dana.
Sir, I will start.
Yeah, can you proceed? And only when Yamuna madam will join soon, by that time we can give the brief introduction. Okay.
Okay, sir.
Now you can give the start. Bini madam, you can share. Dana, who is Dana or Nimisha? Who is introduced?
Oh, my turn, Nimisha.
Yeah.
Okay, we are moving on to OP session. So the judges for the oral presentation will be Dr. Bini George, Assistant Professor, Department of Chemistry, Central University of Kerala. Already we have introduced her in the previous technical session. Dr. Yamuna R. She completed her PhD from IIT Kanpur. She has served as Principal Investigator for CSIR, DST, DRDO, and MHRD Center projects. Her area of research include liquid crystalline material for fuel cell applications, nanomaterials for firings, lead acid battery, nonlinear optical material, etc. She has guided many MSc projects and PhD students. She has also several national and international publications for her credit. She has served as an associate professor in Department of Science at Amrita Vishwavidyapeetham. Currently, she is the associate professor at Department of Chemistry, School of Engineering, Coimbatore. On behalf of the webinar committee, I welcome both Dr. Bini George and Dr. Yamuna for the judgment of the OP session.
Thank you, Nimisha.
Yeah, madam, please, you can judge till madam join. Okay.
Now Manohar.
First, we will have OP29, Manohar Jople.
Madam, you can keep the time limit and everything you can control. Other students will help, madam.
Yeah.
Yeah, Dana and Nimisha will help you.
Yeah, sir. Yeah. Manohar, you know the rule.
My presentation is visible now.
Yeah. You have to present for 8 minutes and 2 minutes here question answer session. Yeah.
Okay, ma'am.
Please.
Myself, Manohar Kacharam Jopre from Art, Commerce, Science College, Trambakeshwar. I welcome to you, ma'am, for this evening session. Today, I am going to present a review article on magmite and effective solvent free catalyst for organic transformation. A review. In introduction, I have found that recently the catalyst is widely used in the field of the organic synthesis for fast and easy conversion of the reactant to its product. Every time there is a requirement of the fresh catalyst phase for the, in case of the homogeneous, but in case of the heterogeneous, we can able to separate this catalyst phase. But in homogeneity, it is not with the possible. The magmite is the suitable for the many of the organic transformation because of its more selectivity nature of the catalyst. It is the more efficient, eco-friendly, and green catalyst for the many of the organic synthesis. The most of the cases, there is a loss of the activity of the catalytic phase when it is used for the multiple time for the same transformation or other new reactions. The magmite is in 1927, this word is derived, and that is also called as the gamma ferric oxide, having the wide application in the field of the magnetic material, which is used in the ceramic alloy, resistance, resistivity, recording material, absorbers, nanoparticles, biomedical field, and it is also used because of its ferromagnetic property of the iron oxides. The organic transformation is very important in present day due to the wide application of this compound in the field of the agrochemical industrial, then pharmaceutical, polymers, textile, and many more. There is this is because of its easy convert and its the catalytic activity and its inertness is the important. What is the structure of this magmite? The first polymer is the alpha, the ferric oxide, that is also called as the hematite, which is the most stable, and the second is the magmite, that is the gamma ferric oxide, which is the less stable than the hematite. The first, there is the preparation of the magnetite phase, and then it is a different range, and then cool in the desiccator. So the easily we are getting this alpha is obtained above the 440 degrees Celsius, while the cubic spinel structure of the gamma hematite is reported, and the morphic change of that particular phase is obtained from the gamma to alpha above the 450 degrees Celsius. The magmite phase is prepared by using the hydrothermal double hydroxide, then thermolysis and Sol-Zol technique, as well as the spray pyrolysis technique. There is the different techniques which is used to verify this particular structure that majorly include the X-ray diffraction, FTIR, EDX, then the VSM, then same time PGA technique that is used for the characterization of this magmite phase. Here, the many of the reaction which is proceed by effectively by using this organic, this magmite catalyst in case of the organic transformation. There are this is because of it is wide application as the solvent-free condition. There is no requirement of the solvent when we mix the two reagents together, that it gives the due to the catalytic phase that reactants are converted to their products. So there is no contamination is found in that particular case. So the 100% pure component or the product will be obtained due to the solvent-free reactions. So the quantized gamma ferric oxide attached to the cellulose enomer, that is the effective catalyst for the Michael type reactions, as well as the hydrogenation reaction, which is the furol is converted to the furol alcohols. The nitrogen doped graphene catalyst is used for the oxidation of the aldehyde to its corresponding carboxylic acids. The magmite catalyst is the solvent for the solvent-free organic transformation, in which the silica nano composite, it is a green and the diverse catalyst which is reported by Ghosh and other researcher. Then synthesis of 1,8-dioxo decahydrogen derivative under the Solon-free condition. It is reported by Muhammad Ali Ghussemedia. The nanostructure magmite supported silver catalyst, which is also reported by for the styrene epoxidation. Then synthesis of NRL imidazoline catalyst for the copper nanoparticle on the nano-synthesized silica coated magmite. There is some application of this I have found from the many of the papers. Oxides form of this magmite catalyst having the wide application in the different field of the science and the chemistry. This is widely used in the color imaging, then ferrofluid, then bioprocessing, and the frequency absorbing material in the crafting aircraft. It is prepared from use as the super paramagnetism, porosity, and the temperature inhibitors in the number of the cases. These are the other applications that gas sensor, Solon-free catalyst, green synthesis, recyclability, and magnetic control delivery has the number of the application, but we have concentrated on Solon-free catalyst. The conclusion, it has been summed up that wide application of this, the magmite in the electronic, biomedical, then the recording devices, gas sensing, and it is also the number. There are a lot of the studies required in case of the Solon-free catalytic reaction, but there are some reactions which is due the Solon-free condition, and one-pot synthesis is also possible by using this particular catalyst. So most of the organic transformation takes place in presence of the nanoparticle and doped and modified form of this particular catalyst. The most important property of this catalyst is in the many of the transformation when the use in surface activities recovered, and so the same material is recycled and used for the another reactions also. It is a wide application of the field of the imaging, sensing, and frequency receiver in this ceramics. That should be there. And there is also the versatile study is important in this particular field of the chemistry. I thank to my principal, Arts, Commerce, and Science College, Trambakeshwar, Nashik. These are some references which I have referred for this particular preparation. Thank you.
Yeah.
If any doubt, you will ask.
Yeah, thank you, Manohar, for your presentation was good. You have synthesized two different systems. Yeah, can you come to that slide? Yeah, and
synthesis.
Your synthesis here, that it was nice. You could do that with a scheme. Anyway, it's okay. And yeah, that can you just explain the application study part you did? Conversion of. Can you come to the previous? Not the structure here, that application part of your two catalysts.
Yes.
You have synthesized it too. Yeah. Am I correct?
No, ma'am. I have taken the review of the other synthesis. I have collected that.
Only
review.
You have.
But I am going to prepare this because of my research is on oxide. So that I will interest to the AP. So that I have collected some data related to the AP and their.
No, this is just a review only. You didn't.
No, ma'am. I am going to use this. I have already synthesized the other material, but I have collected this data for my research.
What will be What will be your future study?
Yes.
What will be your future study from?
No, ma'am.
This is
I am going to use this particular property of this AP and their wide application, because I am going to prepare some mixtures related in which I am going to the use of this AP along with the copper and nickel. So I am going to make the mixtures of these metals, and their oxides should be used as in the organic reactions or as a catalyst for organic transformations.
Okay, and how long you are doing?
Yeah, I am doing from since 6 months.
Oh, you have just joined. Okay. Anybody? Yes. Now the session is open for the questions. Yeah.
Hello, madam. Can you hear me?
Yamuna, you have
Good
joined.
evening,
Ma'am, now you can take.
Yeah. Manogar,
Yes.
yeah, good. Can you tell me, have you measured the magnetic property for this compound?
Ma'am, it's a literature, this only. That.
Yeah, you have not measured any magnetic property for your compound synthesized one?
Yes, I have my super paramagnetism. I have already mentioned super paramagnetism property.
Have you measured for this one? Which is the experiment you used to measure that one? You got that magnetic measurement?
Ma'am, this is the review article, so that I have not done any kind of the work on that particular case. So that I have just collected this from the other researcher. I have collected data related to the AP because my topic is on the ferric oxide. So I am going to use this ferric oxide along with the other material. I am going to make the composition, and that should be used for organic transformation. So I have collected this all related to the organic transformations.
Okay, I think, Madam, I think this review will go for next one. I think it's better. Okay, thank you, Manohar.
Okay, thank you, sir. Thank you, ma'am.
Welcome, Dr. Yamuna, Madam. So, sorry that you had
Thank
a
you, sir.
difficulty.
Sorry for coming late.
Already
Yes,
a little late, so we initiated.
Pramod will be there. You will be noting down the time, na? You will send the message. Pramod?
Yeah, yes, ma'am. Yes, ma'am.
Yeah, okay.
Only students, research scholars and students kindly note for the best oral. Okay. Thank you.
Then Tana, Nimsha, who will be?
Ma'am, next is Sumaya Banu, OP24.
Yeah.
Ma'am, is my screen is
You can go
visible?
ahead. Yeah, PPT is visible.
Okay, ma'am.
You
Good
know
evening.
So all of you restrict to 8 minutes. Your talk should be 8 minutes. And Dr. Yamuna, Madam, since you are not in the beginning, so just for your information, they have to present for 8 minutes and 1 or 2 minutes for the question and answer. And yourself and Dr. Bini Madam will be the judges, panel experts. Okay. And just to keep the time very strictly. Okay. Thank you. Please.
Thank you, sir. Good evening, ma'am. Good evening, sir.
Good evening.
Good evening.
Good evening, sir.
Yeah,
Such
you
a
can
wonderful webinar. You have arranged such a wonderful webinar, sir. Thank you, Shaktivel, sir. Now let me get into my topic. I'm a research scholar from Coimbatore Institute of Technology, that is Coimbatore, ma'am. My topic is 2-hydroxy 1-naphthaldehyde sulfonamic acid fluorescent chemosensor for highly selective and sensitive detection of silver metal ion in food sample, ma'am. Let me give some introduction about sensor, ma'am. Sensor is a device or a molecule which detect or measure a physical property, records, indicate, or otherwise respond it generally as an electrical or optical signal. There are different types of sensor, such as heat sensor, pressure sensor, motion, moisture, electrochemical gas sensor. I am working in fluorescent-based chemosensor, ma'am. Fluorescent-based chemosensor recognize biological environmental importance of metal ions. They can recognize cation as well as the anion. Among the various analytical methods, fluorescent has been a powerful tool due to its simplicity and high detection limit and application towards bioimaging. Let me tell shortly about the design of a fluorescent chemosensor. It consists of a fluorophore, a linker, and a ionophore. In this ionophore, the metal ion, it may be the metal ion, cation, anion, or neutral species which may be attract towards it. The role of fluorescent chemosensor is to image the target and to construct a chemosensor. Next, the design of fluorescent chemosensor is fluorescent unit covalently linked with suitable spacer and a guest binds on the receptor. This is known as receptor. Okay, let me tell the objective of my work. We have synthesized a 2-hydroxy 1-naphthaldehyde sulfonamic based skip based compound And this compound was characterized by C13, proton and mass spectroscopy, ma'am. After that, this compound was taken for metal detection of various metal ions, 24 from sodium, aluminum, calcium, lithium. 24 metal ions were taken for this study. In that, specifically, this metal was sensitively selective towards Ag metal ion. So the studies, the metals what I have mentioned, aluminum, cerium, cadmium, lanthanum, these type of metals were taken. In this, the receptor was specifically sensing only the silver metal ion with the solvent of pH of and H2O 1:1 ratio. This was taken, and this was carried out under a neutral pH condition, ma'am. After that, to make confirmation that only silver metal ion has been involved or any other metal ion does interfere in this, so we have carried an interference study, that is competition of metal ion with in this our receptor and different types of metal ion. This blue bar represents the receptor with other metal ion, but in other condition when we add silver metal, it shows the enhanced intensity, fluorescent intensity. From this, we confirm that there is no interference of any other metal ion. And next, we have carried a reversibility cycle test to know whether a material has a reversible property or not. Initially, when a receptor only added, it shows the fluorescent intensity around the range below 1000. When we add a silver metal to it, it shows an intensity of 3000. And again, this reversibility study was carried with EDTA, ethylene diamine tetracetic acid. So again, the metal EDTA binds with a metal ion. So again, it shows the intensity of the receptor. Again, on adding of Ag, it showed the enhanced fluorescent intensity. This cycle was carried for 10 times to know the reversible property. And again, to know the ratio of metal ion as well as the ligand and the metal ion, we have carried Jobs plot studies. This shows this 0.5 shows that the equal concentration. It means 1:1 ratio of binding takes places between the metal ion and the ligand. Ligand represents a receptor. And the application was we are concentrating only on the detection of silver metal ion. The food sample were collected. According to WHO, there is only a limited amount of silver ion should be taken for the human body. When there is excess amount of silver ion, it causes Parkinson, Alzheimer, many diseases. So we have taken some food sample and we have recovered how many amount of silver have been found in the food sample. Conclusion, a novel fluorescent chemosensor was synthesized by condensation method, and it was characterized by C13 proton mass in gamma spectroscopy, and it was selectively detective towards Ag plus metal ion following turn on off on process. It means enhancement, which is resulting for enhancement. Meanwhile, we found that there was no interference of any other metal ion. Furthermore, we are working for the biological application for the bioimaging when a material has been injected, showing fluorescence images in when there is a presence of silver metal ion. Thank you, ma'am.
Yamuna ma.
Thank you, ma'am.
Yamuna ma.
Ma'am.
Yeah.
Student?
Ma'am?
How many ligating sites are there? Denticity of your ligand?
It is monodentate, ma'am.
It's monodentate?
Yes, ma'am.
So which is the ligating site?
The ligating portion is which is having a lone pair of electron from 2-hydroxy-1-naphthaldehyde. We are having OH group, ma'am, and from sulfonilic acid we are having SO3H group, ma'am, and by the Schiff base condensation C double bond N is present over there, ma'am. So this nitrogen also will be help in binding, ma'am.
Okay.
Okay.
Hello. Ma'am. Yamina ma'am, your question is over? Yeah, over?
Over, ma'am.
Okay, okay. Sumanya Banu, yeah, you did, your presentation was good, and for the application side, yeah, you did it from food samples.
Yes, ma'am. Yes, ma'am.
Yeah, which are the food samples you did? Can you just brief the procedure?
Yeah, surely, ma'am, I'll tell. Actually, we are concentrating on food samples like grains, ma'am. Barley, whole grains, ma'am. Barley, wheat, ragi.
And what was the procedure here that you adopted for the analysis?
Ma'am, same fluorescence spectroscopy only we have.
No, what was how you have isolated the food samples directly you take and do, or what?
Actually, we from this we'll prepare the extract, ma'am. Okay, we'll take
Can
the
you
food
just
samples.
explain this one procedure? Because that application side, it's better you could include that, how you did.
Surely, ma'am. Next time I'll include, ma'am.
No. Now you can brief it, what you did with the food sample. Suppose wheat or grain is the, because in the medical field that many diseases that silver use at Parkinson's, Alzheimer's, that is important.
Yes, ma'am.
How you did that sample? Suppose
Actually,
you have the grains, how you will do that?
Actually, we'll take the whole grains and we'll break it down into powders, ma'am. From that powders, we'll take of 5 gram of the grains, and we'll add 10 ml of distilled water, 10 to 15 ml of distilled water, ma'am. We'll allow for heating, and we'll allow for heating up till 7 to 8 ml, ma'am. After that, we'll filtrate the extract, and we'll take up the extract, ma'am. And with the help of the extract, what we'll do now? Initially, we'll add that extract and we'll run the fluorescence spectroscopy, ma'am.
So directly, and only that analysis method from the extract.
Extract we'll do, ma'am.
And did you do any other technique to this one, cross check that?
Actually, we are following
Did
the
you
same
do
technique.
quantitative fluorescence spectroscopy or
Quantitative only we are.
And how much amount you got from that food samples? And data was not given.
Yes, ma'am. I'm actually working 0.5 gram of sample was taken.
No. That how much silver was there? That contaminated silver was there.
Ma'am, according 2.0 ppm was present, ma'am.
2.0
ppm.
2 ppm was there for
yes, ma'am.
for all samples.
For
how many samples you did?
We did for 3 samples, ma'am. Ragi, wheat, barley, ma'am. It was in and around.
And all of them got 2.
2.0, 2.5, 2.8, ma'am.
And the only fluorescence spectroscopy was used to.
Yes, ma'am. For this analysis, we used only the fluorescence.
No, you could use some other technique also, because I was working in industry. That's why this is here.
Have taken AS atomic absorption.
Okay, now you can think on that now. Okay, that's from my side. Okay.
Thank you so much, ma'am.
Any other questions from the participants?
We can move on to because the time limit is time.
Okay, thank you, ma'am. Thank you, sir, for a good opportunity.
Pramod, next one.
Dana, can we go to the next?
Yes, ma'am. Next is OP25, Reshma ji. Reshma, please.
Hello, ma'am. Am I audible?
Yes.
Can you see my screen?
All the oral participation you should be there till end. Okay.
Ma'am, is my PPT is visible?
Yeah, PPT is visible, and you know the rule now. 8 minutes you have to present and 2 minutes interaction. No?
Yeah, yes, ma'am. So can I start?
Yeah, you can start.
Good evening, everyone. Myself Reshma ji, research scholar at Amrita Vishwavidyapeetham. Here I am presenting one of my research topics titled as dehydrogenation of 1-phenylethanol catalyzed by nickel diphosphine complex, which I done under the guidance of Dr. Naveen. So let me go to the introduction part. The acceptable dehydrogenation process provide an efficient and atom economical route for alcohols to synthetically useful carbonyl compounds without the use of a sacrificial hydrogen. So since this is a very vast significant reaction is having a very vast significance, we can develop a variety of homogeneous catalysts using the precious metal centers like ruthenium, rhodium, iridium, osmium. And they show better catalytic activity. And if you are tuning the catalyst with the structural features and applying different reaction conditions, we can also use sustainable metals like iron, cobalt, and manganese. They also exhibit better catalytic reactions. In this catalytic reaction, we are using phosphine ligands due to their steric and electronic factors can have an influence on the catalysis. So we are working with the nickel complexes that is inspired from one of the some of the previous work done by John et al. And Sang et al. In their work, they were tell that if you are providing some exotic ligand system or under special reaction conditions, we can achieve a desired reactivity using nickel system. So we prompted with the nickel-based catalyst, which can efficiently catalyze dehydrogenation of alcohols under mild to moderate reaction conditions. And here we are using diphosphine nickel chloride because they have simple synthetic routes, and also they have stability and well-stabilized catalytic protocols. So in the study, we are having a study on catalytic efficacy of the nickel diphosphine system in the dehydrogenation of 1-phenylethanol to acetophenol under acceptance conditions. So let us go to the experimental part where we are purchased some of the ligands from Sigma Aldrich. Some of the ligands were and complex we prepared under nitrogen atmosphere using slung line technique. This is a general protocol of the catalytic reaction for the given compound of nickel phosphine catalyst. We are adding a base in these two necklace length phos with a water condensed at nitrogen atmosphere. Along with this, we are adding 2 ml of toluene, and the reaction was kept stirring for a couple of minutes, and then after we are adding 1-phenylethanol of a given amount, the catalytic mixture, and it was kept at 120 degrees Celsius preheated oil bath and kept stirring for vigorously for more than 16 hours. And the whole reaction was maintained by continuous bubbling of nitrogen gas. And after scheduled period of time, after more than 16 hours, it was kept for the reaction was kept for cooling, and it was open to air, and the product isolation was done by running the catalytic mixture through a silica gel column using ethyl acetate, and the product yield was analyzed by gas chromatographic analysis and the proton NMR studies. So we have made nickel diphosphine complexes almost 7. So these are the different nickel diphosphine complexes and we used for this study. So here we can see that the nickel diphosphine complexes, we are using different substituents like methyl, ethyl, isopropyl, phenyl, and also we have on concentrated on the nickel phenyl group. There we changed the spacers like we used methyl, ethyl, and propyl spacers. So these are the 7 nickel diphosphine complexes we used in our studies. Now then we done the different analysis using gas chromatography and NMR studies. From these studies, it is found that the nickel complexes are substituted with diphosphine ligands having phenyl substituents is having better activity. They have the ability to convert phenylethanol to acetophenol almost around 52%. If you are going to the methyl and isopropyl group, it has seen that methyl substituted group is having only the ability to convert 12% of acetophenol, and for isopropyl, it is seen that it has the ability to convert 40%, whereas for the ethyl group substituents, it is 30% conversion is possible. And which means, which indicates that the significant influence of an electronic effect of the ligand on the stability and react to the catalyst system. And also we tried different reaction conditions on our system. In that found that if the nickel chloride is used in the absence of a phosphine, any of the phosphine ligand, we didn't find any reaction conditions. And also if the sodium ethoxide is also used in the absence of any nickel system, there is also no detectable conversion. And also, then we concentrated on one of the phenyl, since we found that the phenyl constituents are more better, so we changed the spacers. So in that spacers, we found that the propyl spacer is exhibiting better activity of yield of 34% of conversion of acetophenol, whereas if we convert with the methylene spacer, we found that methylene spacers can only dehydrogenate 21%. So the whole study, we've come to find that ethyl spacers with the phenyl substituent is found to be better activity towards the catalyst reaction. So the better activity, stability, vector activity of the C4 is due to their higher stability, that is due to the presence of a stable 5-member coordination ring, and also due to the ideal beta angle in the system, that is they make them electronically stabilized. And we tried the whole reactions in different stoichiometric ratio and different reaction conditions. So this is that since we found that the phenyl group is more giving more conversion, so we changed the reaction conditions by changing the temperature, time limit, and the percentage of concentration catalyst, and found in that. And also along with the proton NMR, P30N1 proton NMR spectral studies, we found that if you take the C4 complex, we found that there is a signal at delta 57.1. If we can find a significant shift in the signal when we are adding 2 equivalent amount of 1 phenylethanol, and also when we are heating to 5 minutes for 60 degrees Celsius, we found that there is a peak at delta 33, indicating the formation of a new compound that is most probably an alcohol species. And also when we start the catalytic catalytic reaction on the initial stage, we can see that there is the same signal at delta 33, and it's suggesting that the formation of the same intermediate, that is alcohol species, since in the catalytic condition. As the reaction is proceeding towards the end, we can see that there's a new signal present at the delta 198.5 along with the signal at 33, indicating the partial dissociation of the intermediate compound. From all these studies, we came to conclude that the catalytic reaction was found to follow a homogeneous pathway involving a nickel hydride species, and also due to the gradual disintegration of the catalytic species, there is deterioration of catalytic activity was observed, resulting into low to moderate conversions. And also, if we are tuning this reaction in a better way, we can efficiently promote good bit upgrading of ethanol to N-butanol, which is having a great importance. And also, from my studies, it is concluded that the catalyst dichloro 1,2-bis diphenyl phosphanoethane nickel, when loaded with 50 more % sodium methoxide in 12 at 120 degrees Celsius, exhibited highest concentration of 52%. And our work has been accepted for the publication in Acta Synthetica Solvenica. And at last, I want to express my gratitude to my research guide, Dr. Navi, Assistant Professor, Department of Chemistry, Ahmedabad Vishwavidyapitham. Extend my gratitude to Professor William D. Jones, Department of Chemistry, University of Rochester, for his guidance. My sincere thanks to organizers of National Webinar on Recent Advances in Solid State Chemistry and Allied Science for providing me this opportunity to present. And my gratitude to Ms. Meenu Kumar and all lab mates for helping me with all this synthesis part. And my gratitude to Department of Chemistry and the Vishwavidyapitham and the university for providing me the facility to complete my research work. Thank you.
Can I interrupt, Dr. Bini?
Yeah.
Rashma,
Yes, sir.
you have to, this is a hydrogenation or oxidation reaction. How do you confirm this is a hydrogenation?
Hydrogenation reaction, because on continuous passing of nitrogen, we can tell that there is removal of hydrogen.
Is the reaction carried out under the nitrogen atmosphere?
Yes, it's completely under the nitrogen atmosphere.
Okay. I have one more doubt. This is that why did you choose this molecules? Because see, you know that phenyl ethanol 2 benzophenone, acetophenone, it is relatively easy by presence of aerial oxidation. But okay, you are chosen for the dehydrogenation without, that is without oxygen atmosphere. That's a good, show the nickel efficiency. But why specific to this reaction? Can you, any reason?
In this, the nickel is in the nickel 2+ oxidation state of the air stable. That's why.
No, I'm asking for the reaction part. Because dehydrogenation type of reaction, isn't it? You have chosen.
Yes, sir.
Yeah. What is the driving force which choose that dehydrogenation reaction? Because nickel is known as a very good hydrogenation reaction in presence of hydrogen atmosphere. Yes, it is also good for dehydrogenation reaction. But the choice of the molecules, what is the reason? That's what I think about it. Thank you.
Okay. Yashma, sir was asking about the application part. Why did you choose that?
Is there any rationalization behind that? Okay.
Because the dehydrogenation reaction nowadays is using with the higher metals. That is very expensive and not that possible to use. So we want to just have a try with the.
Fine. Okay.
Yeah. Then sir, do you have any other question? Sir,
Fine. I am fine.
Yamina ma'am, are you there?
Yes, ma'am. Reshma,
Oh, yes, ma'am.
have you confirmed the synthesis by using single crystal XRD? Anything have you done?
No, ma'am.
You have not done it.
Ma'am, we didn't complete the work. It's still on process.
Completed.
Still, we are working on this, ma'am.
But
Working on this.
But you have communicated, no?
Yes, ma'am. But with this data, we are communicated. But more about this structural activity, we are still working on it.
Reshma, she is asking about the starting material, not the intermediate that you are planning to isolate.
Yes, I mean, sir is there. Okay.
Actually, sir, I didn't get the question.
Reshma, Yamuna ma'am was asking the characterization part. What you have synthesized?
Yes, he mentioned that she doesn't have a single crystal.
Okay. And the GC.
What is your question?
Yeah, actually, I asked her whether she has done any single crystal XRD study for that nickel complex, because she has done with the pause pin. So if she would have done it, then she can know bite angle and all those things.
No, I didn't done anything.
Okay, Reshma, which experimental technique you used for the confirmation of that conversion phenyl ethanol to acetophenol?
That is through GC, ma'am.
Through?
GC techniques. That is from the different signals we can find.
No. Madam, question is, what is the conventional method used currently? It's not how you are doing it, okay? What is the conventional method?
Spectroscopic techniques.
I think she didn't understand the question. Fine.
Okay, okay.
GC, quantitative GC you have analyzed for estimate the conversion?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Can you just brief it how you and how you did and how much was the percentage of conversion?
We done with when we do the GC, we get different signals. From the area of curve, we integrate it. Area under curve.
No, for your product, this one, how much you did? What was the efficiency that I am asking?
That is
conversion.
Maximum conversion is 52% at 16 hours. For one of the complex, the different complexes showing different conversions.
Okay. For your product, you got to approximate 52.
52%. If we are doing it 16 hours, we are doing it more hours, nearly to 24 hours, we can get 56%. But after 48 hours, we cannot get any change in 56%.
Okay, that means your reaction is complete after 24 hours, 48 hours.
No, the catalyst is starting disintegration. That's why I didn't get the reaction after 48 hours. There is no conversion.
And what about the recyclability?
That I'm not sure.
Then okay.
It's a homogeneous catalyst. I think that's the problem.
Yes, it's a homogeneous catalyst.
Oh, homogeneous. Okay. Sir,
Okay.
no more about that. Okay. That's all from my side.
Yeah, I think. Yeah, fine. We can go to the next one.
Thank you, sir. Thank you, ma'am.
And we can restrict to 10 minutes. It's just 1 or 2. Fine, because we have more. Most students are there still. Dana?
So next we will have OP26, Mohammed Hashim.
Mohammed, unmute. Mohammed, you are not, you are muted. Yeah, your voice is, yeah, your voice.
Audible, sir?
Yes, yes.
Okay. Is it visible, sir?
Yeah, proceed, proceed,
Okay.
proceed.
I'm Muhammad Hashim, research scholar from Cochin University of Science and Technology, under the guidance of Dr. Manoj E. Here I'm going to deal with the topic structural, spectral, and theoretical investigations on bis thiocarbohydrazones of 3,5-diiodosalicylaldehyde and their biological in silico studies. The interaction of small organic ligand molecules and metal-based drugs having greater efficiencies and reduced toxic side effects with biological molecules provide one of the attractive area of coordination chemistry. Shift-based ligands are one of the most important class of flexible and versatile polydentate ligands, show high efficiency in chelating transition metal ions. People are working from last many years on the synthesis and characterization of transition metal complexes with thiosemicarbozones because of their wide range of medicinal applications and their ability to coordinate with the transition metal ions. And thiocarbohydrazones are high multidentate homologous and form various polynuclear complexes and known for their anti-cancer potentials. So ligands chosen are very important. The electronegative atoms like nitrogen, sulfur, oxygen atoms connected to the ligands may increase the density and thereby refine the coordination prospects. So my aim to explore the biological potentials of multidentate carbohydrazones, thiocarbohydrazones, and their complexes. For that, to synthesize and physiochemically characterize a novel carbohydrazone and a thiocarbohydrazone ligand, and to perform the DFT analysis of the synthesized ligands, and to perform the in silico docking analysis of the ligands for their anti-cancer efficiencies as well as their potential against COVID-19. So we have synthesized the ligands by treating 3,5-diiodosalicylaldehyde with carbohydrazide or thiocarbohydrazide in methanol in the presence of acetic acid upon 2 hours of refluxing to yield the compounds. So we have synthesized two ligands, H4L1 3,5-diiodosalicylidene carbohydrazine as well as 3,5-diiodosalicylidene thiocarbohydrazine. This is the MALDI spectra of the ligands. We have characterized the ligands using UV visible spectroscopy, FTIR, and MALDI-TOF mass spectrometry. We have got single crystals of carbohydrazone ligand from DMSO solution on slow evaporation. From the crystal data, the bond distance of 1.2 angstrom for this CO reveals the ligand exists in ketone tautomeric form. This is the crystal packing of the ligand, shows different interactions. And we have optimized the ligand structures using Gaussian software with B3LYP LAN L2DZ as the base set, and calculated the total energy as well as some of the energy parameters of the compounds. From these computational studies, we have calculated the HOMO-LUMO energy gap and found that the 3.7 electron volt for the carbohydrazone ligand, whereas the 3.5 to 7 electron volt for thiocarbohydrazone ligands. And electrostatic potential mapping helps to visualize the charge distribution. It shows the electron density within the molecule. Here the slight reddish yellow color, and also here the yellow color indicates the electron rich region of the ligand having the electronegative atoms. It could be an electrophilic attacking region, or it can be able to coordinate with the metal centers. And this blue region indicates relatively the deficiency of electron. Molecular docking. Docking is a molecular modeling technique that is used to predict how a protein or enzyme interacts with molecule or ligands. As DNA is the primary intracellular target of an anti-cancer drug, molecular docking studies were performed to predict the binding efficiency of the ligand with the receptor binding sites of BDNA dodecamer, which is 1 BNA is the PDB ID, which is obtained from protein data bank. Here the ligand is subjected to the molecular docking with the bDNA and obtain different docking poses of the ligands. And this the docking results shows that the DNA binds comfortably with the ligands with the various interactions like hydrogen bonding, hydrophobic, and electrostatic interactions. So here H4L1 shows negative 11.93 kilocalorie per mole binding energy, as well as the thiocarbohydrazone shows minus 12.65 kilocalorie per mole of binding energy. So the molecular docking studies of the ligands with this bDNA.com reveals that the ligands can bind more efficiently with the DNA and can be a potential candidate for anti-cancer therapeutic purposes. And also from this docking pose, it reveals the ligand fit comfortably as a groove mode of binding with the DNA. And it needs to be confirmed through the experimental studies. And also, the COVID-19 is a dangerous disease rapidly spreading all over the world today. So chloroquine, hydroxychloroquine, favipiravir, remdesivir are some of the WHO recommended repurposed drugs for the treatment of coronavirus. So here the molecular docking studies were performed with SARS-CoV-2 main protease, which is the enzyme essential for the replication of virus. Here, along with the ligands, these drugs also subjected to molecular docking with 6Y2F, which is obtained from the protein data bank, for comparing the binding potential of the ligands with these drugs. And the docking results confirm the excellent binding potential of the ligands with the proton. Here the ligand H4L1 shows negative 7.80 kilocalorie per mole, which is comparable with chloroquine and hydroxychloroquine. But in the case of thiocarbohydrazone ligand, it shows minus 9.20 kilocalorie per mole, which shows an excellent binding capability better than that of the all other drugs, including remdesivir. So the ligand can be a better candidate for the treatment of coronavirus. So I conclude that two novel ligands of these thiocarbohydrazones have been synthesized and characterized. Analysis of frontier orbitals of the ligands were performed. Biological implications are studied by in silico molecular docking study, and both the compounds show better binding scores with 1BNM. And thiocarbohydrazone ligand exhibit excellent binding potentials with the SARS-CoV-2 main protease. And I acknowledge Professor M.R. Pratapachandra Kurpu sir, Dr. Manoj sir, my supervising guide, and Professor K. Srikumar sir, HOD of KUSAT and STIC KUSAT for the analysis, and the organizers of the seminar. Thank you.
Munama.
Mohammed?
Yes,
yeah, Mohammed. Yeah. Can you go back to that previous slide, Ma? Yes, see.
Oh. Hello?
Go back to that.
Which one?
And the DFT study. Yeah. Which software do you use for this one?
Gaussian 09 software, ma'am.
Software, okay. That green and then red color region, what it shows?
It's a negative and positive lobes, ma'am.
Which is negative and which positive?
Red is negative and green is positive.
So what does it imply?
It implies that this is the donor. It's a donor part, ma'am. This is actually a HOMO -1, so it is capable of donating electron. This is a donor, like that it implies, and this is the acceptor, like that. This HOMO and LUMO lobes implies.
Okay, have you measured the cytotoxicity of your compound?
No, ma'am. I need to do that.
Ligand?
No, ma'am. I need to do that. That's my future plan.
Okay, okay. Okay, madam. I have done it.
Yeah. Muhammad, this is due to the COVID pandemic situation, it's a good work. And what is your future plan? As ma'am asked cytotoxicity and
Actually, ma'am,
because you did only 1 minute. You did only computational and docking studies here. How you will execute this work in the for this clinical studies, and what is your future plan?
Yeah, actually, my compound shows excellent binding capability using these in silico studies. So my plan is to do the DNA binding with the ctDNA and observe how my compounds binds with the DNA. And
What
actually,
technique you will, how you will
by
do that?
using fluorescence titration as well as the UV absorption titration. Actually, I have taken my fluorescence spectroscopy for my compounds and it shows fluorescence. So my next plan is to do the fluorescence titration with the ctDNA, and I need to prove that this molecular docking study is acceptable with that with the experimental study.
Okay. Yeah. That's from my side. And any other questions from any participants? Ma'am, then can we move to the next? Emina ma'am?
Yes, ma'am. Yes, ma'am.
Okay.
Yes, ma'am.
Okay, ma'am. Next
Thank-
is OP 27, Dr. Ajit. Ajit sir, please.
Okay, yes, madam. Madam, please permit me for sharing the screen.
Dana, can you tell that?
Okay, yeah. Yes, I can. Okay. People, is it visible?
Can you share it now?
Yes, I shared, ma'am.
Yeah, now it is visible.
Is it visible?
Yeah, now it is visible. You can proceed.
Okay, ma'am. Thank you. Okay, good evening to all of you. Myself, Ajit Nagarkar, Department of Chemistry from Arts, Commerce and Science College, Trimbakeshwar District, Nashik. My topic for today's presentation is synthesis of biologically active heterocyclic compounds, that is 2-benz-imidazolone, 2-benzothiazolone by using green catalysis method, that is mainly L-proline as a catalyst. First of all, I want to give a small introduction about the catalyst. Catalyst, it is a substance which accelerates the rate of chemical reaction, or it convert the reactant into a desired product without affecting the product as well as reactant. Advantages of the catalyst: it speed up reactions, some chemoselective reactions, regioselective reactions, stereoselective reactions are possible only by using the catalyst. Yield of the reaction increases by using catalyst. Low energy required. So these are the advantages. Rather than that advantages, there are also some disadvantages. Major advantages is environmental problems, because we are adding one external agency in that reactions. So there is it may be a metal or non-metal, but the chemical composition increases, which affect environmental issues. Cost of catalyst, it is the additional cost which is included in that reaction. Few catalytic reactions require sophisticated instrument. Catalyst poisoning, it also a very big issue in catalytic reaction, which affect the yield of the reactions. So this is the overall background of the catalyst. So there are mainly, again, the one method is added, that is green catalysis or organic catalyst we use in this reaction. It is better. So here my research study is mainly focused on that green catalysis, and in that also a proline. I focus mainly on the proline. Why proline? It is very easily available. A steric compound, chiral nature, having secondary amino group, act as an catalyst as well as ligand. In 1971, Schering, AG, and Hoffman reported first catalytic reaction by using L-proline. Aldol condensation, asymmetric synthesis are very well known catalytic reaction by using L-proline. Advantages of this catalyst: environmental problem, no any issue for the environmental problem. Cost of catalyst is very low. No need of any sophisticated instrument. Chiral in nature, so chiral reactions are also possible. Reusable, easy to handle, and easy to work up. It is a very best advantage of this catalyst. So, as a basic catalyst, there are also various derivatives of the catalyst are by using this proline, and its derivatives are also used for various specific reactions. Are also, these are some catalysts which are very well known in past literature. So I am going to focus on my work here. My work is the carbonylation of this orthophenyldiamine, and to synthesize 2-benz-imidazolone as well as 2-benz-oxazolone, 2-benz-thiazolone, like as that. These are very important biologically active compounds which are used for various drug synthesis. It mainly application included intermediate in production of pharmaceutical compounds, chiral auxiliaries in many important asymmetric synthesis, and synthesis of various heterocyclic compounds. These are some reported methods for the carbonylation of this OPD and its derivative. I'm not going to detail of this. Limitations: why I choose this my catalyst for the reactions or this purpose? Because the known methods using phosgene gas is one of the major component of this carbonylation reaction. Phosphoric acid also there, metal catalyst also there. But the main drawback of these reactions are phosgene is very highly dangerous for use in laboratory scale as well as industrial scale. In phosphoric acid reaction, high temperature is required. Yield is very low, lengthy work process. So by considering all these drawbacks, I am trying to apply my methodology for the synthesis. Here, in this reaction, pilot reaction, I use orthophenyldiamine and urea for the synthesis of my target product. The ratio of the reaction is OPD 1.2, urea 1, 20 mole% of L-proline as a catalyst. Time required for the reaction 12 hours. This is the overall conclusion after my basic study. I will go for that study. Here, before finalize the condition, I have tried various solvent for the reaction: THF, ethanol, acetonitrile, dioxane, acetic acid, DMSO, DMF, as well as glycerol also. But in overall all this study, I found toluene as the best solvent for the reaction and give very good yield as well as easy workup procedure. For any chemical reaction, workup procedure is very important, because maximum the product we achieve in that, or the loss of product mainly found in that workup procedure. So in the toluene, when I use it as a solvent, the procedure is very easy. In study of effect of catalyst concentration, I had started from 0 to 5, 10, 20, 30, 20 to 20% of catalyst by changing the time hour. So I want to share that in up to 12 hours and 20% catalyst, this is the best condition. Here I got 84% read. In 30% loading, only 3% yield of the reaction increases. When I increase the time limit, then also there is not too much efficiency of the reaction. So I finalize the condition 20% catalyst, 12-hour time for the reaction. Here, by using this standard condition, after finalizing the standard condition of reaction, I prepare various biologically active these compounds with good to moderate yield. In this also, sir, I want to notice that sorry, one important thing, when there is a donating group in the benzene ring, then reaction yield is very good. When there is a methyl group, it is 87%. When there is
You have,
but here also
you have 30 seconds remaining. Yeah,
oh yeah, ma'am. Yeah, I conclude. But here, if there is a nitro group, withdrawing group, then the reaction is very low or the yield is very negligible. This is the NMR spectra. At 11, it shows NH proton, and here it is the proton of benzene ring. C13, here 155 for carbonyl carbon, and remaining are there. Important observation, high rate of conversion with good yield. No reaction for nitro group, that is withdrawing group. More than 100 degrees Celsius reaction not possible. Advantage of work, use of mild condition, no metal catalyst, good process, easy to work. Thank you. Thank you very much.
Yamuna ma'am. Yamuna ma'am, are you there?
She's there. Yamuna madam?
Maybe some network problem.
Yeah.
Yeah, she's there.
Ajit,
Yes, ma'am.
yeah, you synthesized all these products, whether are we characterized that all the product?
Not yet, madam. I characterize only 4 to 5 products. Only 4 products. Now I am going to characterize remaining also. But ma'am, TLC and the TLC is the main tool which I found that these are the that proper product. But now for a 100% confirmation, I am going for NMR as well as C13. Only 4 products I have characterized here. And due to the lack of time, I have mentioned only here one detail of one product.
Okay.
So have you checked the IR?
IR?
Do you have a NMR with you or no? You don't have
only
it?
NMR and C13 NMR, sir.
Okay. But do you have IR? Basically, IR will give the functional changes, modification of the compound. Isn't it?
Yes, sir.
Have you found it? Because I have not seen any of your slide with IR.
No, I have not mentioned any IR slide here, sir. Because rather than IR, NMR, the basic peak of NMR and C13, that mainly NH peak and carbonyl peak.
Yeah, I understand, but you don't have a NMR of all the samples. When you don't have all the samples, at least you can confirmative of change of functional group can be confirmed through the IR, no?
Okay, yes, sir. Yes, sir. Yes.
Okay.
Yeah. What sir said is correct. First functional group first you have to characterize with the IR.
Yes,
NMR
sir, yes.
and it's available in your institute.
Yes, ma'am. Yes.
And IR is there.
Yes, IR is also there.
Yeah. Then if the facility is available, then why you didn't do that? And for the separation is after the synthesis here that how much was the yield and what separation technique you used? You got only one product after the conversion?
Yes, ma'am. Only one product. There is no any side product. And ma'am, in that toluene solvent, the important and main observation is that after cooling, the product comes out as a solid. So that is the best advantage for me to work up this process. But in DMS or DMF, it is not possible. So there lengthy process is there.
Okay. Okay, that's all from my side. Any other questions from participants? Can
we can go to next one.
Yeah.
Thank you, sir. Thank you, ma'am.
Okay, ma'am. Next is OP28, Pavandeep. Pavandeep, please.
Pavan P, are you there?
Yes, sir. Yes, sir. Hello, sir. Are you listening me?
Yeah. Share the PPT.
Ji, okay, sir.
All the participants, keep ready your PPT immediately. Okay. Okay. Fine. Pavandeep. Okay. This is Pavandeep Kaur. Okay.
Ji, haan ji, sir.
Okay. From University of Kashmir. Okay. Okay. Fine.
Ji, sir. Good evening, everyone. My name is Pavandeep Kaur. I'm a PhD research scholar of chemistry in the University of Kashmir, J&K, India. On the behalf of National Webinar on Recent Advances in Solid State Chemistry and Allied Sciences, I'm going to give an oral presentation on the topic, a novel and potent strategy for solving major issues in food and pharmaceutical industries. All wish to have a healthy diet. In fact, we do have healthy diet, which mainly includes milk, fruits, juices, vegetables, dry fruit, eggs, non-veg, etc. Some are rich in minerals, whereas some in vitamins. Some are fibrous and some are immunity boosters. But have you ever thought, even after taking all these foodstuffs, we are not perfectly healthy? And quite often we visit the doctors. Moreover, our modern lifestyle also divides us of certain nutrients, which ultimately affects our health, and we have to consult the doctors and physicians. The reason why, even after taking milk, people usually suffer from eyesight problems, hair fall, and growth problems. Fruits, which are considered to be a good source of vitamins and minerals, even can't satisfy the people's health demands. Non-veg, which is known to strengthen the muscles and help them grow faster by acting as rich source of proteins and vitamin B, and should be taken by everyone. But what about the people who are pure vegetarian? Thus, the major health-related issues emerge which need to be sought out by food and pharmaceutical chemists. The answer to all these queries lies in bioactive molecules. Bioactive molecules, which are the molecules present naturally in the plants and certain foods, and whenever we consume food, we are actually taking in these bioactive molecules. They have become a multi-billion-dollar industry worldwide nowadays because they improve the health with negligible side effects when compared with other pharmaceuticals and drugs. Few examples of bioactive molecules are cited here. For example, we use turmeric, that is haldi, while cooking Indian recipes. The turmeric plant contains the bioactive molecule curcumin in its rhizomes, which has enormous health benefits when consumed. Similarly, tomatoes, they contain lycopene as bioactive molecule. Citrus fruits like orange, lemon, amla, etc. contains citral. Vanilla contains vanillin. Quercetin, which is a bioactive molecule, which is actually a flavonoid and is present in many fruits and vegetables. Similarly, LC-PUFAs, these are basically the long-chain polyunsaturated fatty acids, which are found to be present in nuts, seeds, oils, and non-vegetarian food. Similarly, there are many such bioactive molecules. The main problem with these bioactive molecules is that they are unstable, and the cause of their instability being poor aqueous solubility, pH, temperature, light, oxidation, reduction, and first-pass metabolism. Now, you might have understood why even after taking in different foodstuffs, some deficiency still remains there. Thus, there is an urgent need to tackle this problem. If we look at curcumin, this is the molecular structure of curcumin. which I had already briefed, that it is found in turmeric. Its potential health benefits include its anti-cancerous, anti-inflammatory, antimicrobial, and wound healing ability. But due to its aqueous insolubility, when we consume it, since our body consists mainly of water, which is a polar molecule, and we all know that like dissolves like. Therefore, taking in hydrophobic curcumin will have low bioavailability in our body. Moreover, it is unstable to heat and light as well. Thus, the potential advantages from it are not obtained as such. Similarly, on the similar lines, citral, which is known for its flavor and weight loss agent, in addition to have anti-inflammatory effect, also degrades at low temperature, has low aqueous solubility and unstable to heat, light, and air. Therefore, again, it is less advantageous for our body when taken as such. Linoleic acid, which is an LC-PUFA, that is long-chain polyunsaturated fatty acid, and is known for the proper brain, body, and bone development, has anti-cancerous and anti-inflammatory effects, but gets oxidized very easily when exposed to air or moisture, thereby generating rancidity and unacceptable off flavors, which may affect the health of consumer. Similarly, quercetin is there, which is antibacterial, anti-atherogenic, anti-cancerous, anti-inflammatory, but because of its poor aqueous solubility and extensive first-pass metabolism, it leads to the decreased bioavailability. Although many techniques and formulations were adopted from time to time in order to make them avail to the consumer, but till date, the food grade nano emulsions have no match. They are basically the kinetically stable of oil, water, and surfactant molecules. If we talk about their preparation, they can be prepared by two methods. You can see in this slide, high energy method and low energy method. In case of high energy method, it makes use of high mechanical energy, which can be provided by instruments like high pressure homogenizer, high shear mixer, and then ultrasonicator. In these methods, after mixing oil, water, and surfactant, the mixture is subjected to any one of these three instruments, which lead to the formation of macroemulsion. Macroemulsion is the one with large droplet size. On subjecting these macroemulsions to high mechanical shear, nanoemulsions are formed. They are the one with smallest droplet size. Similarly, if we talk about its other method of preparation, which is low energy method, it requires low mechanical energy. And in this method, simply the oil, water, and surfactant mixture is stirred by using magnetic stirrer or by using simply a glass rod. Nanoemulsions basically incorporate the bioactive molecule in their core, thus protect them from the. For example, if the bioactive molecule is hydrophobic, then oil in water nanoemulsions are used. For example, it is the core part, which is oil, and there is water, and between the oil and water, there is surfactant, which is adjusted at the interface of oil-water part. Similarly, if the bioactive molecule is hydrophilic, then water in oil nanoemulsions are formed. A surfactant is basically an amphiphilic type of molecule. It has a hydrophilic head and a hydrophobic tail. Thus, both the hydrophobic as well as hydrophilic bioactive molecules, or even the drugs which are challenging, they can be incorporated in the nanoemulsions. And moreover, by incorporating them, nanoemulsion increase their bioavailability, stability, and shelf life. They mask the disagreeable taste and odor. Moreover, they act as controlled release system. Till now, we discussed that the nanoemulsion can incorporate challenging bioactive molecules, as a result of which their shelf life can be enhanced. But what about the delivery methods? Nanoemulsions are known to carry the bioactive molecules or drugs and retain their content until they reach the target tissues in the body, where they selectively release the drugs in a desired pattern. Nanoscience and nanotechnology are new frontiers of this century, which can be utilized to improve the food quality, shelf life, safety, and cost and nutritional benefits as well. Thus, we can say that the major issues in food formulations. Discussing food grade nanoemulsion without introducing to the world's most renowned and prestigious.
1 minute is remaining. Yeah?
Okay. Without this, is the distinguished professor in the Department of Food Science, University of Massachusetts, McClements. Now, if we have a look at very recent publications, by using medium chain triglyceride as oil, 2080 as surfactant, and lecithin for the stabilization. And the outcomes were found to be excellent, as the loading capacity and encapsulation efficiency were found to get enhanced manifolds. Similarly, in 2017, resveratrol, which is an antioxidant and a bioactive molecule, it was encapsulated by using nanoemulsion, and again the excellent results were seen in case of its stability and delivery concerns. In 2019, coenzyme Q10 loaded nanoemulsions were obtained, which was also very fantastic. And very recently in 2020, Liang Sun Chen synthesized the nanoemulsion loaded polymeric capsule. They actually using the they use the alginate polymeric capsules and then loaded nanoemulsion inside them. The nanoemulsion contained the ibuprofen inside it, which is a painkiller. At the end, I will conclude it. There's the nanoemulsion based carrier systems, because of their having promising attitude towards the designing the controlled release of active molecules and drugs, can find use in wide variety of food, pharmaceutical, and efforts should be made in future to further explore the utility of nanoemulsion based formulation, so that the quality of food can be enhanced manifolds, thereby serving humanity and mankind in the long runs. Thank you.
Yeah, Manama.
Which nanoemulsion do you used for your study, Ma? Surfactant? You have not mentioned anything.
New in research, I haven't yet done lots of work. I did only optimization of nanoemulsion yet.
Yeah, what kind of nanoemulsion you use? So that's what Madam is asking.
I am making oil in water nanoemulsions by using food grade ingredients like food grade emulsifier, food grade oil, and everything should be food grade.
What does it mean by nano?
Anji sir?
What does it mean by nano? What do you mean by nano?
Nano means
How
it is very GG sir. So nano emulsion basically refers to those emulsion whose droplet size ranges from 1 to 100 nanometers.
How do you evidence that there is
Sir, actually, we have DLS, dynamic light scattering instrument in our department. After synthesizing nanoemulsion, we subjected it to that instrumental studies, and from there we analyzed its size.
what is the minimum size which we can get it from the DLS?
Sir, the nanoemulsions which I have made, they have reported up to 3 nanometers as well. My nanoemulsion droplets reported 3 nanometers size as the minimum lowest possible size there.
Yeah, is it possible to get from the DLS? That's what my question.
GG sir, why not? Yes sir.
DLS can show only micron size. If I'm correct.
No sir, it can show up to nanometers on also. Sir, we have light sizer 500 DLS instrument. It shows nanometers size as well.
Okay. Anything else?
Nothing, sir.
You will be starting your work only, no? You didn't select your system, yeah? Am I correct?
G, ma'am. Actually, I will proceed with these nanoemulsion based delivery systems.
Okay.
Haven't did yet. G.
Okay. Sir, can we proceed for the next?
You can listen. Okay. Thank you.
G, thank you, sir. Thank you.
We can go to the next one. Dana?
Sir, next we will have we will have OP23. Rashmi Jairavindra. Rashmi, please.
Yes. How many more is there? Is the last one? Dana?
Yes, sir.
Okay.
Yes, sir.
Thank you, Yamuna madam. It's too late.
It's okay, sir. No problem.
Good evening, sir. Good evening, everyone. Ma'am, is my presentation visible?
You can proceed. Yeah.
Go to the slideshow and you can proceed. Yeah.
Good evening, all. I would like to present my work, Synthesis, Characterization, and Biological Studies of Manganese 3 shift-based complexes derived from imidazole 2-carboxaldehyde and orthophenylene diamine. Introduction. Schiff bases form an important class of most widely used organic compounds and have a wide variety of applications, mainly in the medicinal and pharmaceutical fields, due to their broad spectrum of biological activities like anti-inflammatory, analgesic, antimicrobial, anti-cancer, and antioxidant properties. My ligand was prepared from orthophenylene diamine and imidazole 2-carboxaldehyde. Orthophenylene diamine and imidazole 2-carboxaldehyde were mixed in the ratio 1:2 in methanol, and it was stirred for around 45 minutes, and yellow precipitate separated out, which was filtered and washed with ethanol, dried, and the yield was found to be 78%, and the melting point was found to be 185 degrees. The formation of the ligand was confirmed by spectral techniques. The from elemental analysis, the percentage of carbon, hydrogen, and nitrogen values showed were in good agreement with the calculated values. Further, it was confirmed by proton NMR spectra. Proton NMR spectra shows protons in 4 different environments. NH corresponding to the imidazole, azomethane, imidazole ring, and protons corresponding to the benzene ring. And infrared spectral studies of the ligand showed main functional groups like C double bond N corresponding to the azomethane, NH stretching frequency at 3115, C double bond N of the imidazole ring, C double bond C of the imidazole ring, and CH bending of the imidazole ring in plane and out of plane. The metal carboxylates were separately prepared by adding manganese chloride tetrahydrate to a solution of sodium hydroxide containing different benzoates. The benzoate selected, benzoic acid derivatives. The benzoic acid derivatives selected were benzoic acid, salicylic acid, parahydroxy benzoic acid, and meta-nitrobenzoic acid. And finally, the manganese complexes were prepared in situ by mixing the manganese carboxylate prepared earlier and orthophenylene diamine and imidazole 2-carboxaldehyde in the ratio 1:1:2, and the formation of the metal complex was confirmed by spectral techniques, proton NMR, IR-TG, IR studies, mass spectra, TG, and CHN analysis, and the percentage of metal was confirmed by gravimetric method. And the biological study of these complexes were done. Antimicrobial studies were done on gram-positive and gram-negative bacteria, and it was found that all the complexes showed good property when compared to the ligand. This shows the minimum inhibitory concentration, and also the antifungal studies were conducted. Acknowledgement. I would like to express my sincere gratitude to my guide, Dr. Suma, and my sincere gratitude to the organizers of this national webinar for giving me an opportunity to present my work. And these are some of the references. Thank you.
Okay, ma'am. Try to use this complex. In what way this has microbial activity, isn't it?
Yes, yes, ma'am.
So what is the applications? Where, in which area are you going to use this type of complex?
Ma'am, actually, I'm looking forward for anti-cancer properties. Actually, I've just given the sample for the study.
Yeah, have you studied for this cytotoxicity?
Yeah, even I haven't got the result yet.
Okay.
929, yes.
Ma'am, kindly go to the geometry of the your complex. Geometry. What is the oxidation state of your central metal ion manganese?
Manganese, actually, sir, it is manganese 3+.
3+. How to account for the electroneutrality? But this only is one O minus. This minus is there.
Yeah, I need to actually confirm that.
Whether how to kindly check yeah. It is not in +3 state. I think it may be in +2 state. +2.
Okay, sir. I shall check that, sir.
Yes. Kindly check whether doing by molar conductor studies. That will help you.
Okay, sir.
Okay. Thank you.
You have taken IR spectroscopy, no? In IR also that NH peak you are getting only 3100, no? You are not getting, that should be in 3300.
And, sorry for the disturbance. There is no Mn, I mean O bond, O bond. Whether you get it in IR, Mn O bond.
Sorry, sir. MnO bond
In IR spectrum.
Yes,
there is
around 520. Sorry, sir.
Rashmi.
Yes,
what
sir.
they are asking that what I have observed that the characterization part you didn't explain anything in detail. Introduction part, normally for presentation, introduction part you keep less, and this IR characterization part you can explain to them.
I didn't.
Ma'am, ma'am, am I correct?
Yes.
Yeah, because antibacterial also she didn't tell which is the best system.
Yeah,
Only
she has
you were
not-
skipping.
Yeah.
Characterization part you were skipping from one slide to another.
Actually, ma'am, antimicrobial studies, it was the gram-positive.
No, first you that their question here, this IR you just explain to them and then we can go to. This IR you just answer to their question. Yamuna ma'am asked this here.
Yes.
Why you got in 3000 region and
3100 only you are getting NH peak, no? You said.
Yes, ma'am.
So NH peak, I think it should come, okay, 3000, above 3250 or 200 at least. Near 3300 centimeter inverse, it should be there.
And there is a water is also present.
I think that she has the peak, but she, ma'am, she has a peak, but she didn't label it properly.
Properly, that's there in the, she mentioned 3100 something.
Rashmi, what I am telling is you did a good part of work. Only thing is that is when you present that you characterization part and be thorough with that, label the groups and that identify the peaks, and it's ultimately your work.
Yes.
Yeah, that part
Yes.
you take care.
Yes, ma'am.
You did a good part of work analysis also you did, and be confident and you do that part.
Okay, thank you, ma'am.
Ma'am, do you have any other?
Okay, ma'am. The time is there. It's up.
Shaktivel, sorry.
So finally we come to the conclusion section. So it's a very long day since from morning 9:30 we are continuously sitting. Thank you for the panel members, especially the external expert Dr. Yamuna, as well as my colleague Dr. Bini George, for their valuable session, and also my teacher Dr. Raman sir for joining in the presentation and giving the suggestions.
He's your teacher? Okay, good.
Yeah.
Thank you, sir. Thank you, sir. Thank you, ma'am.
Always happy to see Raman sir always in any event. He's my teacher, mentor. Today I'm here because of him support. Very happy, and thank you all the participants. Tomorrow, please join at 9:30.
One more thing that promote Yamuna, then promote Vanna and
I'm going to tell them for that because audience they are leaving. That's why I have to tell.
Okay, sir. Okay.
Tomorrow 9:30, please join Professor Ajay Veenu from Australia will be joining. And yes, Dr. Bini George has rightly said it is our research scholars. They are also equally sitting all the day, and they are calling the oral presenter and everything like Dr. Mr. Pramod, Ashwin, Bhavisha, Dana and Nimisha has a special thanks because they were holding the mic and hold the day. They are coordinating with each other. So yeah, wonderful team. Behind this all the webinars, there's my strong research scholars, mine and our department research scholars all together they are doing. It's a whole collective support of the departments. I sincerely thanks all of you. And our dean also all the time he is sitting and watching silently, Professor Pratap Chandra Krupp sir. Thank you. And all the participants, I hope you have enjoyed. And please join tomorrow at 9:25 sharply. So we have the, because again tomorrow we have a tight schedule. We have 5 eminent speakers. Out of the 3 are from abroad. Professor Ajay Vinu, Professor Ramasamy, Ajay Vinu from Australia, and Professor Ramasamy from Mauritius, and Dr. M.E. Reddy, he is joining at morning 7 o'clock from the Canada. Okay, so all of you please join and enjoy. So thank you, Dr. Yamuna, for once again.
Thank you, ma'am, for your support.
Thanks again to Nimisha and Dana for their wonderful job. See you tomorrow. Thank you, Dr. Bini, madam.
Yeah, okay, sir.
Thank you, sir. Thank you, madam.
Thank you. Thanks my co-convener, Dr. Bhaglakshmi, because I think she might be driving right now. So I have to thank her because she is well coordinated along with us. Thank you, all of you. Sunny, we can stop streaming. Sunny, are you there?
Yes, sir. I'm here only.
Yeah.
So should I stop this?
Yes. You can stop the live streaming.
Okay.
The recording also. So all of you may leave. Thank you. Thank you, madam.
Thank you.